All right, so the event is recorded now, and I think we can start. So hello everyone. Welcome to the first Quantum Machine Learning Conference organized jointly by the Quantum AI Foundation, Q India, Q Poland, Q World, Christ University, and SIP. We'll tell you soon about these organizations and also about the workshop. So at the beginning, I will give you an introduction to the workshop together with Anshul and Akash. So basically, I will tell you about the Quantum AI Foundation, about the Q World and Q Poland. Later, Anshul will tell you about the Christ University, and Akash will tell about Q India. As you can see in our agenda, so these times are in UTC+2 time zone. And the first lecture will be given by Professor Amlan Chakrabarti, and the title is Towards Quantum Intelligence. Later, we'll have a lecture given by Manush Gupta, Quantum Machine Learning using Pennylane. Later, Oskar Słowik will give a lecture about variational quantum algorithms. And then we'll have two tutorials. The first tutorial will be given by Kavitha Yogaraj from IBM, and it will be about Qiskit QML or Qiskit ML, in fact. And the second tutorial will be about using Pennylane for quantum differentiable programming, and it will be given by Antal Szava from Xanadu. And we'll finish about 6 p.m. UTC +2. So this is something that we expect now. I hope that all of you have joined our Discord server. So as you can see, there are several channels. There are dedicated channels to all of these 5 talks or tutorials. There are channels titled Towards Quantum Intelligence, Quantum Machine Learning using Pennylane, and so on. So if you have any particular questions, of course, you can try to ask your questions on a Zoom chat during the lecture, during the tutorial, so that it will be easier for the instructor to answer during the lecture or just after the lecture. But also, if you have any questions earlier or later, so before or after the given session, you can also post your questions on our Discord server, and maybe the instructor will be also able to answer. So of course, it may depend on the availability of the instructor. All right, I can see that there are already some questions. So there's information about the time zone in India and a link to the Discord server. So this link was also sent in the invitation email. Okay, are there any questions regarding the conference? So as we also mentioned on our Discord, and as you can see, this conference, this event is recorded, and hopefully if everything goes fine, we'll upload the video and publish it on a YouTube channel of the Quantum AI Foundation. So yeah, that's the plan. Okay. So if there are no questions, yes, go on.
Just one question. This is Himanshu Vaidya from Pune. The workshops that will be conducted, will there be on the programming done on simulators or actual quantum hardware?
So it may depend on the instructor of a given tutorial, but I don't think that it will be on a real quantum hardware. I don't think so.
Okay, thanks.
All right. Okay, so yeah, I think we can start. So now I will tell you a bit more about the organizations that organize this event. So one of the organizers is Quantum AI Foundation. So formally is the legal organizer of this event. So I'm a founder and CEO of this Quantum AI Foundation. As you can see, we are a charity organization aiming to support development and collaboration in science and new technologies, especially AI and quantum computing, but also other fields of mathematics and computer science and physics. And we achieve our goals by organizing meetups, lectures, workshops, contests, hackathons, and conferences like this one. So this is our first conference that is organized jointly with other entities. So if you are interested, here are some links to our website, Facebook group, fan page, Twitter, LinkedIn, YouTube channel. So on the YouTube channel, the Quantum AI Foundation will upload and publish the recording from the conference. So that's the plan. So here you can see the link to our YouTube channel. All right, the second organizer is QWORD. So QWORD is a global network of individuals, groups, and communities collaborating on education, implementation of quantum technologies, and research activities. So we have several initiatives in QWORD. So the main activity of QWORD is to organize workshops on quantum computing and quantum programming. So one of such workshops is called Bronze. So Bronze is an introductory level workshop. We've already organized more than 60 such workshops and handed out, as you can see, more than 1,500 diplomas, certificates. So I believe that at least some of you have already participated in our workshop, but if not, then of course we invite you to take part in our future events. We also organize hackathons. So as you can see, here is one of the hackathons organized by Q Turkey. Q Kitchen is a public repository for developing and sharing our educational projects and similar materials. So in fact, one of the goals of establishing QWORD was to just facilitate a collaboration and communication between quantum computing researchers all over the world. So we started in Central and Eastern Europe, but later other countries, other local groups joined us as well. So soon you will see a list of the current local groups, which are called Q Cousins. We promote equality, diversity, and inclusion. That's why there's also a sub-project called Q Women. So these are just some local groups in which women or girls can also collaborate and organize their events if they're interested. There's also dedicated channel or sub-project for juniors, for high school students, and we also prepare dedicated educational materials for students. Q University, so this is one of our plans for the future. So we would like to prepare a quantum computing course, later quantum computing semester, and maybe also quantum computing degree at the end. It's like the whole complete study program they call quantum computing studies. So currently we have one open online course on quantum computing. And if you are interested in collaboration with us, then of course feel free to join us. We also have mentoring programs, mentoring trainings for people who would like to become mentors or instructors during our events, especially workshops. We also have a Q Research department in which there are several activities. One of them is the project called Q Intern. So in Q Intern, we basically match senior researchers with juniors, with students, PhD students, young researchers. So the senior researchers propose some interesting research topics which they can mentor and in which they can collaborate with some gifted students. And students from all over the world can apply and participate, contribute to such projects as interns while being mentored by senior researchers. So we have already organized 2 such Q Intern projects. The first one was in 2020 and the second one this year. In both cases, this projects lasted about 7-8 weeks. So it's likely that next week there will be the next edition. So we also invite you to participate. In the Q Research department, we also have study groups, which also have meetings once per about 2 weeks. And basically they study some research articles related to quantum computing. I already mentioned about the Q Cousins department. Q Cousins are our local groups. Our local groups, because in QWORD we collaborate globally, but operate locally. So we have local groups currently in 18 countries. There will be more countries joining soon. So even this year we'll have already more than 20 Q Cousins. We already have Q India as well. I know that there are many people from India. So as you can see, we have local groups in Poland, we have local groups in India. and in many other countries. So we invite you to join and also collaborate closely with these local groups, which just form a keyword, in fact. So all people from these local groups can also contribute globally to prepare some educational materials, to organize workshops, lectures, hackathons, and other events. So yeah, basically that's the idea behind Keyword. QPoland is just one of the Q cousins. So also I'm one of the coordinators of QPoland. As I said, we also have Q India, of course. And if you are interested, then we invite you to join our groups. We have also a Facebook page, Twitter profile. We also have community Slack, but currently we are moving to Discord. So later I will also post on our Discord server, I will post a link to the Keywords Discord as well, so that you can join. And you can also try to contact people from your local group directly, or if there is no Q cousin in your country and you are interested in forming a Q cousin, then feel free to contact us by email and we can discuss how to organize such a local group. And that's all from my side. I see that probably there's one question. Can someone tell when will the next Q Inter will take place? I believe that it will be next year. So far we had, as I said, we had 2 Q Inter programs in July, August 2020 and July, August 2021. So I believe that the next Q Inter will be also July, August 2022. So we have to wait, unfortunately, but we'll see. Just follow our announcements, because it is possible that there will be some other interesting events even earlier. There's a question, QML operation. I don't understand this question, but yeah, anyway, I believe that it was a mistake. So if there are no more questions to me, then I think that I can now stop sharing my slides and give Zoom to Anshul, who will tell you about Christie University. So Anshul, the Zoom is yours if you're ready.
Thank you, Pavel. Good afternoon all. I will just share my slides. Just a second. So I would like to talk about CBT. So CBT is Center for Emerging Business Technologies. So first, let me talk about my university, which is, so university is Christ seem to be university. It's based out of Bangalore and have a couple of campuses in Pune and in Delhi. And this is a university which is based out of India, and close to 27,000 students are enrolled. And as you can see, it's a multidisciplinary university with a lot of programs on humanities, social sciences, commerce, management, engineering. And there is a lot of focus on research and let's say sports, music, and other activities as well. Now, coming towards the host, so CBT, basically it's a Center for Emerging Business Technologies. It's a cross-disciplinary, it's a research think tank based out of School of Business and Management, MBA, Christ, Pune, Lavasa. And when we look at it, its main focus is on emerging technologies like quantum computing. You have hydroinformatics, and then we have fintech, clean tech. A lot of new upcoming fields has been coming. So we are looking what will be their primary business applications and how we can interweave these two particular fields. These are a few of the pillars, like we run some research. There are a lot of industry projects, teaching, incubation center as well. This is the visit and the mission of Christ University, of the Center for Emerging Business Technology. So basically, as I've emphasized earlier, it's a research think tank which primarily focus on designating the knowledge. And as a part of this particular initiative, so these are few of the focus areas that we look at. In the past, we have done few international symposiums. So there was a symposium on hydroinformatics. Last month, we have successfully concluded Quantum Monsoon School in collaboration with Q World and Q India as well. Currently, you are seeing QML, quantum machine learning. This particular event is taking place. If I would like to give you a glimpse into the future events, there is a career conclave which has been planned in the emerging business technologies. Then an ideathon has been proposed to look at what will be the business applications of the quantum computing, and the ultimate flagship events will be concluded with the help of we are going to host a conference on business applications of quantum computing, artificial intelligence, and machine learning. And it will be in collaboration with international bodies like IEEE, IBM, and hopefully we will be getting support from Q World, Q India, because we constantly partner with them and try to disseminate the knowledge related to quantum computing and other related areas. So that's it from my side. I would like to invite Akash to talk more about Q India. Thank you.
Hello everyone. Can you hear me? Hello.
Yeah. Hi.
Okay.
Yes,
Okay.
yes,
So
yes,
I thought that
just a second. I will just stop sharing my.
Okay. So I have not any slides to share because what I thought is that the slides will be overlapping with Pavel's, because initial slides are almost same because we are both part of Q India, Q World, right? So I will just verbally present Q India and what we are actually doing, the activities there. So in the slides, if I put that, it will be a lot of things because we are actually doing a lot of activities in Q India. But before going to the activities, I'd like to say hello to everyone and welcome to the conference on quantum machine learning, organized jointly by Quantum AI Foundation, Q Poland, Q India, and CEBT, SBM, the Christ University Pune Lavasa. So in a nutshell, Q India is an Indian chapter of global non-profit organization Q World, which has been briefly introduced by Pavel, and the slides are very nice. And the core aim of Q India is to develop a robust, educative, collaborative, and informative community centered around quantum technologies. And not only quantum technologies, also the theoretical part. I mean, not just like the hardware part of the quantum, and also the programming part. So but as you know, it is Q India, so it is like we will be densely focusing on only the Indian part mostly. But it is not like we are not open for other parts or other regions, something like this, other countries. So I mean, so honestly speaking, that as I mean, many of us in Q India do not have a proper background in physics. So sometimes what happens is that when you do the transition to this field of quantum physics and quantum computing, so what happens is that it feels very overwhelming. So the Q India's main aim is to give the participants and give also the mentors a very nice environment to do the transition in a smooth way, as smooth as possible, and demystify the field of quantum physics and with quantum computing and with the programming with Qiskit, Pennylane, which we're going to introduce in this today's talk, right? So one step at a time, obviously. And to do so, what we do some activities in Q India, such as which is called Flip Classroom. And this is the first thing because this is a very interesting concept, came out in I think a long ago, but we implemented it. And it is like we have the participants who do the reading at their home, and the participants learn some concepts corresponding to some implementation or some theory, and we elaborate those theories in the classrooms, or maybe we also implement it using some well-known softwares or this kind of stuff. And Also, at the same time, we have these flipped classrooms in quantum information, quantum hardware, quantum algorithm. And also, we are thinking about starting new classrooms in many new fields like quantum machine learning, because it is still going on, the quantum machine learning. But there will be many other stuff such as like tensor networks, and also there are many other, maybe some quantum optics also. So apart from these activities, I would like to also introduce that we are conducting bi-weekly meetings. Bi-weekly means like one meeting each 14 days. So two meetings in 1 month. And these we call a very cute name. It is called Coffee O'Clock, and coffee starts with Q. So it is fully quantum. And in each session, we invite speakers from mostly in Q India, but it is not like, because we also had we also had the collaborators I worked in at the institute. Okay, so I didn't introduce myself, but I will do it because I thought that Q India introduction is very important. And so the speakers come and they give a presentation on some particular topic. So let us consider like somebody just came and give a talk on quantum communication. And in next half an hour, what we do, we just discuss about that particular topic. And that's the thing, like demystify the field, right? I mean, there is no mystery in the field. We just discuss the concepts and make it clear. Like for any students, I mean, if you're a master's in the particular field, or if you're a researcher, or also if you're a high school student, we don't know about anything about the field. I think that is what I wanted to say, but I would like to say that how long we have come in Q India. So in LinkedIn, we have our own channel, and we have like more than, I mean, we just crossed 1,000 followers in today morning. So this is very interesting. And this is a very nice number, like round up 1,000. And we have 534 Q India registrations, and 7 coffee sessions, as I told you. And also, you know about Q-Bronze, some of you, and if some of you don't know, then Q-Bronze is like a conference. I mean, it's a small conference based on the topics, based on the slides provided by Q-World. And we use them to give out the knowledge of quantum and quantum programming. And also we give the degrees corresponding to if you finish this particular sessions and conferences. So we awarded 128 diplomas. And also we have 4 flipped classrooms, as I told you, because I mentioned 3, and one of them is quantum machine learning. So yeah, so that's what I wanted to say. And we hope to grow more under the collaboration with Q Cousins, institutions like CEBT, and organizations like Quantum AI Foundation. We hope to grow exponentially by reducing the complexity of quantum exponentially at the same time. So thank you very much. That's what I wanted to say.
Okay, perfect. Thank you, Akash. All right. Are there any questions from our participants? Questions regarding Q-World, Q India, Christian University, or organization of the conference? I don't see any questions. So, Anshul, do you know if Professor Amlan is with us already?
Yeah.
Okay, so yeah, I think that maybe we can start the introductory session, sort of the session Professor Amlan even earlier. So Anshul, yeah, you can introduce our first lecturer. Anshul, you are muted now. Yes, we cannot hear you. Akash, can you hear Anshul?
Can you
no.
hear?
Yes,
Yeah,
we can hear you now. Yes. Mm-hmm.
Okay. So, I mean, it's a real pleasure to introduce Dr. Amlan Chakrabarti. In him, we have found a guide, a philosopher, and by profession, Professor Chakrabarti is a professor. He is head of Akash Chakrabarti School of IT, Calcutta University, and heads the higher innovation
council for the West Bengal government. And Sir has a very distinguished academic credentials. When you look at it, he has done his post-doctoral research from Princeton University. Then he has done his PhD from ISI Kolkata, which is Indian Statistical Institute. And Sir is a very distinguished researcher, and he is a member of IEEE India, very senior member, and holds the editorial position in almost every journal that you can associate with quantum computing or computer science. So you take name of Springer, you take name of elsewhere. Sir is on the editorial board of many of these journals. So it's a real pleasure to invite him for his talk, which we are going to start now. Sir, the stage is all yours.
Okay, thank you, Anshul, and thanks to this excellent initiative, okay, done by the Christ University and Q India and Q World. That means I am really fascinated because when I started my research at the Statistical Institute in 2005, right, people didn't encourage me much except my supervisor, Professor Shushmita Shulkole, and some of my professors at ISI and University of Calcutta. But now I really enjoy this moment because I find that a lot of young researchers, okay, across the country, across the world, okay, is joining this particular fascinating domain of computing research. And apart from that, when we find that the startups, the big corporates, right, all are in this particular domain, right? It really feels great that what we started, right, in one step or two step, okay, maybe 15 years ago, right, in India. That means I might be one of the researchers in India who has submitted a thesis in quantum computing, right, at 2009. So it's really fascinating for me, and I will try to try to keep motivating all the researchers in this quantum computing, and try to get engaged in the whatever possible way I can support the initiatives in quantum computing in India and across the world. I will love to do that. Now let's move on to my presentation, right? I think all are waiting for that. So my presentation will be, as I know that this is an initiative in the domain of quantum machine learning, and again, when we say quantum machine learning, it has also expanded, right, in an enormous amount, right, in the last 4 or 5 years. A lot of things have come up in this quantum machine learning, and people are trying a lot many different things. Okay, so without getting into the very any specific particular part of quantum machine learning, what I try to propose in this particular presentation is the motivation of quantum intelligence, right? Which is the powerful background, right, behind what we do in quantum computing, and then we look forward to quantum machine learning, right? So I feel that my presentation is visible to all of you.
Yes,
yes.
Okay,
Yes,
okay,
sir, it's visible.
Okay, great, thanks, fantastic. So before I start my lecture, I should give my humble regards to my professors who has inspired me over the days during my PhD, Professor Shushmita Shulkole from Indian Statistical Institute. Okay, she's recently also got recommended or recognized as a fellow of Indian National Science Academy, and obviously Professor Neeraj Jha, who is also one of the pioneers in this particular domain of electrical engineering from Princeton University. Also this work wouldn't have been possible without my very motivated and very energetic and very intelligent, okay, bunch of students, okay, who are PhD students. I couldn't add my interns, right, who are also from different institutes across the country. And due to this, some of the recent achievements what our lab has done, okay, it is basically their hard work, okay. So So we'll come to those activities of the latter part of my presentation. Now let's get into what is quantum, okay? So as we look into this particular scenario, this scenario tells the progression of our computing paradigm, right? We started from a computing paradigm which was mostly electromechanical, where we can do hardly some few arithmetical problem solutions, solving arithmetical problems. Then we moved on to the superscale computing, which was the era of transistors, era of silicon, right? Obviously, it didn't start at a single day, right? It took a start from the discovery of transistors in the Bell Labs. And then at the present scenario, we see the transistor miniaturization, and we are seeing that a high packing density of transistors are leading to a lot of very increased computing power, right, in the miniature devices too, right? It's not only computers are now computers. The computers have been transformed, okay, to things, right? And now we know that Internet of Things, or we know that things compute. And then we move on to this paradigm, which is called quantum computing, right? And this is a very exciting paradigm. So why this paradigm came? When we started the research in 2004, 2005, right, there were two motivations, right? And those two motivations are still there. Motivation one, okay, actually three motivations, I will come to that. Yeah, three motivations. Motivation one was that actually, that means the way I started my PhD thesis, because I was basically a VLSI design engineer. My background was a VLSI design engineer in ORCAD, now which is named as Cadence. So when we started the EDA design, and when I came to my supervisor, Professor Shishmita, okay, she said that, hey, why don't we look into something which is beyond the current VLSI, right? And then why this looking was there? Because the circuit sizes was getting miniaturized. So circuit size miniaturized means now we know that the transistor sizing is around 8 nanometer, which is almost, we are touching the atomic dimensions. So when we are squeezing when there's a natural trend of squeezing the size of transistors, right, there are two ways we can do. We can still continue our classical postulates, and we can still think that, okay, we are going into atomic dimensions, but we are still going classical electrodynamics. But the other story is that when we go into the atomic dimensions, why not we exploit the features which are available at that dimensions, or at those dimensions, right? And those features are quantum features. Okay, those physics are quantum physics. So when we are going into that dimension, right, we can obviously think a trend which gets shifted, okay, from the macro computing states, okay, to the nano computing states or quantum computing states. That was a shift one, okay. Shift two was that if you are trying to, quantum physics is always exciting, right? People try to simulate quantum physics, right? But simulating quantum physics in classical computer was not a good thing to do, because it will have a saturation soon, right? You cannot compute at that particular dimension what quantum physics requires, okay, right? And this was a proposal for Richard Feynman. Richard Feynman said that, okay, if you are trying to do quantum physics, right? If you are trying to simulate quantum physics, what you need to do, you need to find a computer, right, which works in a quantum mechanical principle, right? And that was again another push, which is known as quantum computers, right? The third push, okay, for which we mostly the research what we do in the computing domain, whether there are exciting algorithms, whether there are exciting computing speed up we can achieve in that particular domain, right? So that quantum computers becomes an exciting domain, okay, of computing research, right? And that also evolved, right? At that point of time, we had only a few algorithms like Richard Joyce's algorithm, Grover's algorithm, Deutsch algorithm, Shor's algorithm. We had the polynomial algorithm, polynomial factoring algorithm. So there are few algorithms, right? But still, that was enough motivating. And now, if you look into the bunch of algorithms which has been defined in the quantum domain, it's really enormous. It's really a good number. So look into the quantum zoo. There is a very good repository, okay, which is called Quantum Zoo, which lists all the quantum algorithms, right, and tries to give a little bit summary of what are the advantages of this. So regarding the algorithms, we have super polynomial or a polynomial speed up. And in very rare cases, we have an exponential speed up, okay, compared to the classical algorithms, right? Classical, okay, the algorithms which runs on the classical computers, okay. Having said that, it is not a, what I can say, it's not a golden truth, right? It means that it's not that every algorithm will have a speed up at the quantum domain, right? And that's the research of quantum algorithms, that you try to pick up the algorithms, right? You try to formulate the algorithms which can show a speed up in the machines which works in a quantum mechanical ways, right? And those are the directions with which the research initially started, right? And let's see that what is this, and what I actually said is in terms of the speed, but that is being now manifested really. When we started research, okay, it was just a proof which was done conceptually, right? And there were a lot of anti proofs were also there from the very pioneering groups. But slowly and steadily, quantum technology emerged, right? And obviously, D-Wave, IBM, they actually contributed immensely in that, right? Microsoft, and they now we can really see the physical quantum computer, right? And we know that this particular quantum computer, in many of the cases, right? In many of the cases, if we can properly massage the algorithm and we can properly transform it to a quantum equivalent, right? Then it will have a polynomial or a super polynomial speed up, right? And that what gives you a quantum supremacy, which is a very good title, which is coined by Google now. So what's the basic principle, or how we can have this leverage? What is the real part of quantum computing, right? The real part of quantum computing computing like it works as a wave, right? If it works as a wave means it has interference, right? I'm not getting into the quantum physics, as Akash rightly said, that it again comes with a different. If I go into the quantum physics, right, I cannot go to the quantum computing in the same lecture. But just I want to tell you that if you look into the simple diffraction experiment, right, all of you go to the diffraction experiment, which is very well defined. The experiment says that you have an electron, right, and there are two slits, very, very narrow slits, which is that means some dimension which matches the dimension of the electron, right? And if you see the other side of that, right, so normally what you will see, if electron is a particle, if electron state is a particle, right, it will either go to slit 1 or it will go to slit 2, right? So you will have impressions only in particular direction, either in direction of slit 1 or in direction of slit 2. But what we get in the experiment is that we really get a particular distribution, okay, distribution of energy, right? It actually goes from slit 1 to slit 2, which means that an electron simultaneously exists, right? Both in slit 1 and slit 2, right? It passes simultaneously with both in slit 1 and slit 2. And that is only possible when it is a wave, when it is a particle, right? And this is a de Broglie's theory of wave particle duality, and that actually takes that we can constructively generate the quantum wave, and we can destructively generate the quantum wave also. So this is called the interference, right? And this interference is the major issue due to which we have the decoherence. Okay, why the quantum states have decoherence? Because it has a wave property, right? And due to the wave property, it can decohere, right? It can have a negative interference. So this is one of the issues. This we can use for our benefit also, right? We will show how this can be used as a benefit. Two other things are there, which is called superposition and entanglement, right? So superposition is something that to generate a linear composition of states, right? One state is generated as that means a quantum state is generated as a linear superposition of basis states. Right, I'll also come to that with some examples in that of my discussion. And the third part is the entanglement, right? Where it tells that, hey, I have two entangled particles and I did not know both of them, right? They are so close friends of one another, right? If we separate them out also, they maintain their coherence, right? And this, how they maintain their coherence is again a difficult proposition, right? But they maintain their coherence, and this helps us in communication, which means that if I know what is the state of friend one, right? That is, I need to measure only one state. I need to measure only the state of friend one or friend two, because measuring one state will automatically give the measurement outcome what is probable in the other state. So these are the typical phenomena, right? Which happens in the quantum domain of matter, in the quantum states of matter, right? And that gives us a different scope of computational operations, right? And this scope of computational operations actually help us to think the algorithm in a different way and to construct the algorithm in a different way, so that I can churn out this particular this usefulness of the quantum platform, and I can show the quantum supremacy. Okay, having said that, right, there is that means when quantum algorithms were not so much popular, right? There are some researchers, okay, which just try to imitate the classical algorithm and convert to a quantum with some sort of with some way, right? And that is not a good practice, right? That is not a good practice. So the good practice for a quantum algorithm developer is that try to look into the algorithm, try to look into the quantum operations and quantum principles, what are there, right? And try to completely explain the algorithm in terms of those operations. Don't try to just do a sort of equivalent transformation. Okay, that means classical to quantum in some form, right? It doesn't help so much. So let's move on. So these are the premises on which the quantum computing, the fascinating world of quantum computing stands. Okay, so this is what is a qubit, right? You know that a qubit is something called a quantum bit, right? A bit is the smallest possible memory what we can have in a classical computer, right? Similarly, qubit is the smallest possible computing state what we can have in a quantum computer. Now, what are the values a qubit can attain, right? Like a bit, a qubit can also attain the value 0 and 1. Though the value 0 and 1, the interpretation of 0 and 1 is in quantum states, right? It relates to the quantum states. It can be a spin up or spin down, right? It can be a polarization. Find a particular polarization state of a photon and a particular orthogonal polarization state of a photon. So this can be decoded as 0 and 1, or it can be electron present in a dot or electron not present in a dot, can be a 0 and 1 state in the that means in the quantum state. So the way the qubit will be defined is again a perspective of the technology. Right, when we worked at Princeton, we found out there are very good technologies available. Okay, we actually listed 5 technologies. Okay, like quantum dot, neutral atom, linear photonics, nonlinear photonics, and ion trap, right, and superconducting qubits. So these are different technologies. When you level into different technologies, right, it will have a different interpretation of a qubit, right? What is a qubit and what is a qubit state? So unlike classical computer, where we try to say that when a transistor output is 1, right, it is transistor output is high, right? It is storing our state 1, and transistor output is close to the ground voltage. Then it is storing 0. It's a uniform across the transistor domain. It is not the same in the quantum domain, right? So quantum domain technology is very important. Based on the technology, your qubit cost. Based on the technology, either your qubit scaling up of qubits. Based on the technology, in the noise that are associated with the qubits will all be different, right? So technology is so important in the quantum computing. Now this particular picture gives you a particular scenario that what is the advantage or what is the difference we have in a quantum qubit, okay, or a quantum bit compared to a classical bit, right? If you see the states, okay, so obviously we can have the state 0 and 1, which is just instead of representing them as 0 and 1, we use a particular gate notation. This is derived from the quantum mechanics, right? If you have just a preliminary understanding or reading of quantum mechanics, you will understand that these are the notations by which the quantum states are determined. So as 1 and 0 in the qubit are quantum states, they are also represented as the gate notation. So they are 0 and 1. We can have a string of qubits, perfect, right? So a string of qubits is represented in the we show a string of 0, 1, 0, 1, which represents an equivalent to a binary value 5. But the difference is that I can also have a qubit which is in a superposition state. So his spin up and spin down, which I considered as spin up is 0 and spin down is 1. Sorry, spin up is 1 and spin down is, you can have different conventions, okay? So spin up is 1 and spin down is 0. In this particular convention, we also can have another direction of the spin. In that direction of the spin, which is shown here, right, you can define it as a superposition of 0 and 1. So what do we have? We have the first 3 qubits as 0, 1, 0, and the next qubit is a superposition of 0 and 1. So what happens is it's actually this particular state is a superposition of 4 and 5, because this is 0, 1, 0, 1, or 0, 1, 0, 0 in superposition. So that's the beauty of the quantum, or that's the difference of the quantum states compared to the classical states or classical bits. So this is the scenario of what we have in the quantum domain. So the notion of a quantum state is basically defined by by convention, which is called a Bloch sphere, right? And these are the Bloch sphere. Okay? These are the Bloch sphere, right? Right? You have a so normally the z-axis of the Bloch sphere, up is defined as 0. So up is defined as 1, down is defined as 0, or vice versa, whatever way you try to define, right? Two orthogonal, two orthogonal in the z-axis, right? They are called, one is called 0 vector, one is called 1 vector. And these are the basis states. 0 and 1 are the basis states of a single qubit, right? What is a basis state? A basis state means if you have a vector space, in a vector space, any particular vector can be represented as a linear combination, of the basis states. So any qubit state can be represented as a combination of 0 and 1 with the amplitude. So combination means that it will have an amplitude for 1 and it will have an amplitude for 0. And these amplitudes are conventionally complex amplitudes. So it is a complex vector field. So the total, in the qubit space, right? You can go on expanding the qubit space to multi-qubit space too. But if I try to focus on the very simplest qubit space also, a qubit space is a vector space which has complex amplitudes, right? So this is a scenario, and what are the other possible qubit states? Other possible qubit states are something like on the surface of the Bloch sphere. This is very interesting, right? On the surface of the Bloch sphere, any state you define, it is also a qubit state. But this particular state will not be pure 0 or pure 1, right? This particular state will have a component along the 0 direction and a component across the 1 direction. So all these states on the surface of the Bloch sphere is a superposed state, right? And this is a very interesting phenomenon, of quantum computing, right? And this actually gives you a good opportunity to span a larger space using a very small amount of resource. But I will come to that. Right, and the other part is the entanglement, right? Entanglement means you are maintaining the coherence between the two quantum states, which are initially entangled, and then they are moved far apart, but still the coherence is maintained, right? It was actually said by Einstein as a spooky action at distance, which means that there is some skeptic communication is going on, or some skeptic where is existing between these two states so that they are maintaining a sort of coherence, right? And this has been established through experiment that it really happens. It's not only by the quantum mechanical principle by which from the theoretical understanding, right? It has been proved repeatedly by experiment that this happens, right? This happens if you can maintain the quantum, the quantum oblivion, right? And that helps in the communication and also trying to transport the quantum information from one point to another point. So let's try to look into this particular quantum entanglement, which is very interesting phenomenon, right? Right. And also I introduced certain terms in physics, which I can come because this is these are the notations which you need to understand, right? Which is very, very important to understand what is real quantum, what is really happening in the quantum domain, right? And how you are abstracting that, and you are defining this as a QPU, quantum processing unit. So I could term that from the quantum physics to QPU. This will be a very interesting title of the talk, but I'm not presenting this at this point of time, okay? But this is a transformation. What is actually happening is the quantum physics. What we're actually abstracting is called QPU, quantum processing unit. So how this happens? So the quantum physics, right? It is well laid down that a state psi, which is a time-dependent state, right, evolves with time. And that evolution, which is something called del T of psi t. Psi is the quantum state function, which is a function of time. This is defined by the Hamiltonian, okay, of that particular quantum system. So Hamiltonian, which is defined as H, is nothing but the evolution of the quantum system with time, right? And that is the notion. So when we are trying to tell that I am operating on the quantum state, and I'm trying to change the quantum state, okay, from state A to state B and state B to state C, what we're trying to generate the Hamiltonian operation, okay, or we're trying to construct the Hamiltonian operation. And that's what is computing here. Just try to again understand me, okay? So the computing here is just we are trying to reconstruct the Hamiltonian in our own way. And can that Hamiltonian influence enough my quantum state so that I can start with the initial quantum state and I can go to the resultant quantum state where I can do a measurement. Okay, so this is the notion which gets carried from the physics, which is underlying the quantum system, and the abstractions in the computing domain which we work upon, right? So let's look into this. What is a Schrödinger's cat? So Schrödinger's cat is something that the cat is half live and half dead, right? You don't know what is the state, right? You randomly open the box, you will find whether it is alive or it is a dead, right? So the mystery is that right, if you open the box and you get every time it's alive, or if you get open time it's open and you get every time it's a dead, right? It's not a problem, right? It's a normal world. It's not a quantum world. If the quantum world happens, if we open up 50% times you get the cat is live, and 50% time you get the cat is a cat is dead, right? So how you explain this phenomenon? This phenomenon can be explained that, hey, my quantum state, this is a quantum state, right? And quantum state can exist in superposition, right? So if I tell that the cat alive is 1 and cat dead is 0, so the quantum state what exists here is basically a superposition of 0 and 1, right? And that's what is exactly defined in a very animated form, of this particular notion of quantum states, right? Right, and this is example of superposition. This is what is entanglement, right? So entanglement is actually called a EPR term, right? And this, there are several possibles, right? I have only tried to explain that what happens for a one EPR pair, right? For a 2-qubit quantum system, right? You can have several of those. So if you look into this particular state, this is a typical state. Why is this a typical state? It's a typical state because if you look into here, right? 0. So 0 A. So A means it's a qubit A. B means it's a qubit B, right? So it means that the 0 comes from qubit A, and so the first qubit comes from qubit A, right? And the second qubit and the second value comes from qubit B, right? And this is a 2-qubit state, but these 2 qubit states cannot be separated into 2 qubits, 2 independent qubits, right? You cannot factor this particular state. And hence this is an entanglement state. You cannot take that, okay, this is qubit A and this is qubit B. What's the advantage of this? So suppose this particular state exists. So 0A, 0B, and 1A, 1B, this particular state exists. Okay, what happens? Right, when you measure this particular state, as we know, this is a superposition state also, superposition and entangled state, right? Right. After you measure, as you see that that a cat alive and cat dead, once you measure it, it will either alive or either dead. So what it means that if we try to let me take an handle. Yeah, okay. If we try to measure this state, either we will measure this. Okay. Perfect. Okay. So either you will get this state, or you will get this state. Now the beauty of these two states is that, right? If you measure only the first qubit, okay, you know that if the first qubit is 0, then the second qubit is also 0. And if you measure the first qubit as 1, the second qubit is also 1. Right? So so what do you need to do? You don't need to measure qubits. See, okay, again I'm repeating, right? Those very new to this particular domain of quantum computing, quantum information theory. So this is a superposition entangled state. When you measure this, either the state will collapse to this state or this state. When it collapses to this state, right, you don't need to measure the values of A and B individually, right? If it collapses to this state, right, you don't know actually what state is collapsed. But suppose it has collapsed to this state, right? And so when you measure one of the qubits, you will get a value 0. When you get so once you get a value 0, you know that the other qubit will also be 0. And similarly, if you were to measure the one qubit as 1, the other qubit will also be 1. Automatically, no, you don't need to measure. So this is the property what these two entangled states maintain, right? And this can be maintained for a long time, and when they're separated across, okay, right? Then there may be several this type of entangled states. You can also have entangled states with the 0, 1, and 1, 0, right? All the states can be there, okay? So the scenario here that it means that, okay, the two quantum bits, which forms this quantum system, they maintains a sort of invisible correlation. Okay, they communicate with each other and they try to retain their so if one gets a particular value of the state, the other also gets the same value of the state based on the entanglement state created earlier. Okay, and that's the beauty of entanglement. So these are the basics of this quantum mechanics and where you take it to the quantum computing, right? So this particular picture gives you the scenario, again due to limitation of time, not getting into this. So the operations of the quantum system. Again, you remember that these operations are a little bit different from the operations where we do it in the classical hardware. In the classical hardware, we tell that here there is a gate, right? Input gets into the gate, and the gate operates on that and generates an output, and this output gets into the second gate. So what it means that this is the flow of the signals in the space. So gate A is located in a particular spatial coordinate, and then the output of gate A goes into the gate B, which is again another spatial coordinate. So this particular blocks, okay, in the classical computing are basically spatial processing. The signals are processed by gates one after another, okay, in a spatial dimension, right? In the case of quantum, okay, you just need to remember that what you are doing H psi t. So the psi gets changed with time, right? And each of these operations are nothing but describing the Hamiltonian. So it is not that the psi is moving in space. Psi is only changing with time. So which means that you start with a quantum register, which is a set of qubits, right? You operate it with this particular quantum operator. Okay, fine. You generate a value which becomes psi t to psi dash t, and then you again operate with another operation. Okay, in the next interval of time, so it becomes psi double dash t, and this way the operations on the same quantum register goes on, and the evolution is on the time scale, right? And when we try to tell this, what are the Hamiltonians? How we generate the Hamiltonians, right? This is the construction which you need to do with the quantum gates. There are several quantum gates. Okay, I can take again one complete lecture of 3 hours on this, but I'm getting into that. There are a lot of representations. Each of the gates have a sort of representation in terms of unitary matrix, unitary transformation. It is a representation in terms of symbols, right? It is a representation in terms of the operators. Okay, the operators. So you have the single qubit gates, you have two qubit gates, you have a 3 qubit gates, okay, like Toffoli, and then you can go on and on multi-qubit gates. But having said so, again, technology comes in a great way, right? These gates are logical gates, right? Remember. So when you try to map them in a particular technology, you need to find what are the exact primitive quantum operations by which you can using which you can decompose all these gates. Mostly the single qubit gates are generally supported by the technology. But when you go with the 2 qubits or 3 qubit gates, they need to be decomposed into the quantum operations supported by the technology. And that is the enormous amount of work what the quantum CAD designers do, or quantum synthesis. There's a lot of research work has been done in the quantum synthesis, and that is meant by quantum synthesis. Suppose you have a Hamiltonian, right? You want to transform it to a technology. How you do it, right? Hamiltonian, okay, in terms of your high-level gate, right? How you transform to technology. That's a synthesis. But we also did. Our group also has done some very good works in this particular synthesis domain, right? We defined the quantum compiler, the first quantum compiler FTQLS when we worked at Princeton, right? And these are the very good works exist, right? At the present, and also researchers are still working in this domain. Okay, this is a very interesting domain of activity. Okay. Now let's come down to what is this particular quantum supremacy, right? The baseline of this. There are a lot of things we can say about quantum supremacy, but what's the baseline of quantum supremacy? The baseline of quantum supremacy is scaling up in computation. I will just give you a one-line answer, right? Why you think quantum computer is so important? I think quantum computer is so important because you can do computing at a much higher scale. Now, how does it come? Scales means you are adding resources. You have to add resource, and then you can do an enhanced computation. But, right, there is no free lunch, right? You cannot tell that, hey, I will not spend any resource, but I will step up in my computation. You cannot do it. But the idea is that how much resource you give and how much computation benefit you get. If you compare this to the classical and quantum, you will see the difference, and that will really excite you. Okay? So what's the difference? The difference is that in a particular classical computer, if you are moving from 16-bit computing to 32-bit computing, what resources you need to add? You need to add 16 bits more in your registers. You need to add 16-bit more in your pipeline. You need to define the operations at your arithmetic logic unit, which are 16 bits more. So here the resource requirement and scaling up is linear, right? If you need to add 16, if you need to increase the computing from 8 to 16, right? You need to add again 8 bits everywhere. So it's a linear. You add 8 bits, you get a resource enhancements of 8 bits. But what happens in a quantum computer? In a quantum computer, you get an exponential. Okay, so if you have to move from 8 qubit quantum computing to 16 qubit quantum computing, how many qubits you need to add? You need to add only 1 more qubit, because here the computing scale is exponential. So So 3 qubit will give you, okay, will give you 8 states. Okay, 8 states of computing. 4 qubit will give you 16 states of computing. So you see that the number of computing states, okay, what you have, okay, is exponentially grows with adding up of resources. And so there is a promise that quantum computer can do computing at a higher scale with a lesser amount of resource. Okay, with an increase in with a less increase in resource compared to what we do in classical computing. But having said that, there are also a lot of other things which needs to be done in quantum computer due to the present present scalability issues. Okay, so if you compare just hand to hand, okay, comparison can be a little bit different. But what I mean to say is that the promise of quantum computing, if you can lead to the technology, the promise of quantum computing is enormous. Okay. Perfect. So, so once we go on from a qubit, right, it will go to a circuit, because qubit is just that was a quantum operation. A quantum gate is one particular operation, but we can go on adding up operations, right? So you can add up operations in each qubit S, right? Or you can combine qubit S and you can do 2 qubit operations. Right, you can do 3 qubit operations also, right? No problem. So these operations, okay, on the qubit, right, as a whole sum will be defined as a quantum circuit, right? And there are different ways you can analyze this circuit. What is actually happening? You can theoretically, or you can simulate this circuit operation. But at the end of the operation, what we actually do, you try to measure the outcome, right? And that's very important. When we try to measure the outcome, right, you need to make the quantum state so that it is well suited for measurement, and that's also another part of quantum computing. So unlike classical computing, the computation complexity is mainly in the classical computing to achieve the operations, right? You start with the data, right, and you do operations, right, and the number of operations you need to do defines your complexity of your algorithm, okay, to achieve your result. Vis-a-vis what you do in quantum computing is that in a quantum computing, right, you generate all the possible states, which also incorporates the result state. But the problem is that if you just do the measurement there, right, your result state cannot be taken out from all the other existing states, because all are equal probable. Your major cost of computation is to enhance the probability of the result state compared to the other states in the distribution, in the quantum distribution. And the quantum algorithmic complexity is mostly due to that. Okay, how you try to move from an initial distribution to a distribution where you can measure and you can get the probable outcome of this quantum operations. Right, so measurement, so targeting the measurement, you actually define the quantum operations. Okay, and when you start with your initial quantum state, and you move on with your quantum operations with a motivation that slowly and steadily it will be increasing the probability of the result state. And once the probability result state is certainly higher, okay, than a particular, that means compared to the other states, now if you do the measurement, your quantum system will collapse in that particular state which has a higher probability. And that's what's the quantum game. Right? I tell to my student that this is the quantum game we have to do. Okay? So I'm not getting into details of this. You can just get into the basics book and you can go through, right? But I will just skip a little bit of slide because, so how much time I have, Anshul? 5 minutes or 10 minutes?
Sir, you have 10 minutes. I mean, 10, 15 minutes.
Okay,
Then
good.
we'll go with the Q&A session for 5 minutes.
So I am just moving on to a little bit on this because this is so before going to this is also one of the very important notions of quantum computing, right? That was I was also puzzled with this particular assumption, okay, in the early stage of my research, right? How this happens. So the first is that all the computations, right, in this particular in the quantum domain are reversible. The quantum computing means it's a reversible computing, but again there is a caveat. It's not that all reversible are quantum. So reversible computing by on its own can stand as a particular computing domain. But all the quantum operations, right, are reversible because they're unitary transforms. If as they're unitary transforms, which are represented by U in a generic notation, we will always find the U dagger. And when you multiply U with U dagger, it becomes I. So which means that you have done an operation in a quantum state. You can always find an inverse of that, okay, conjugate of, conjugate transpose of that, which you apply, you again come back to the initial state. And you can always do that, whether you do that or don't do that, that's your that means your algorithmic pathway, but you can always do that. Second very important thing, which is an important factor in the quantum secrecy also. You cannot copy an unknown quantum state. Okay, you can tell me that, okay, like I said, there is a gate which flips it. So, okay, which flips the outcome. So if I know that, okay, like a CNOT gate, okay, operation of a CNOT gate is that is the control qubit and target qubit. If the control qubit is 1, target qubit is flipped. So you can tell that, sir, if I have to copy 1 to the target qubit, what I do, right? I set the target qubit initially to 0, right? And then I apply the control 1, and then target becomes 1. So sir, I have copied 1 to 1. What's the difference? Difference is that here your quantum state is known. You know that your target qubit is 1, right? If you know the target, you know the control qubit is 1. As you know the control qubit is 1, you can set an ancillary qubit 0, and you can flip the ancillary qubit, and you can take the value 1 also in the ancillary qubit. But there is no way, if you don't know that what is the value of your control qubit, right? If you don't know the value of a control qubit, there is no way by which you can copy the control to the target. Right? So there is a very, very, very simple understanding, but sometimes many of the research papers I see that means also I find the preliminary works, I found that this particular notion is absent, but this is a very important notion in the quantum domain. And this is one of the path for quantum secrecy, okay? So I'm moving a little bit fast due to the time, okay? So let's, so this is a scenario of quantum system. This has been taken from IBM Qiskit, one example, right? I'm not getting into details of this. This is the way it looks around. Again, just a notation. These Qs are all your qubits. C is the classical measurement. So what you get after measuring this you actually store here at the classical. This is the classical classical bit, the classical storage. Okay, these are quantum storage. This is a classical storage. This is a notation, just to our different notation. Okay, these are all your quantum gates, so quantum operations. This is a measurement, right? So after you've done on your quantum operations, you measure each of quantum qubits, right, and try to take the value and store it in a classical bit, so that you can visualize the result of your computation. Now, when you do that, at what point you measure, that depends on your algorithm. What are the gates you use? That depends on your algorithm. But this is the entire quantum game. You start with a quantum distribution, okay, that convert the Hamiltonian to some quantum operations, right, and try to do a measurement when you find suitable, right? As I say that when this is entirely logical, when you are in the simulation window, but when you transfer it to the real technology, where the real quantum engine works, or QPU works, quantum processing unit works, there is a series of transformations. which are called low-level compilers. Okay, or you can also tell synthesis. Okay, synthesis from your high-level to low-level synthesis. And this also takes several steps. Okay, this is actually from logical qubits to physical qubits, and then optimizing, and then matching the other requirements of the technology concerned. Okay, I'm not detailing all this, but these are all discussions, okay, which can be done in a very extensive way. But you have to go through all this to understand this fascinating domain of quantum computing and how to exploit this, right? Now I look into the quantum leaps. So what I have discussed in the prior is that the initial setup, what are the knowledge domains you need to look into. That means those who are coming at the first level, okay, quantum is a very exciting field and I want to contribute in this domain. Hey, you can of course do it, but my suggestion is that get into something, get into the quantum stuff, try to learn these basics, and then come up with your novel ideas in the quantum domain. Okay, so novel ideas in the quantum domain is basically a lot of issues up there, okay? So building the quantum computer, exploiting the quantum computer, okay, with different algorithms and try to find the quantum supremacy, okay? Also look into the errors, right? And look into the technologies. Okay, this is a holistic scenario, right? Having said so, you cannot be a one person. Now the quantum is, okay, has expanded so much, right? You cannot be a master of every component of quantum computing, right? So you have to identify that which particular quantum computing you are very well capable of, right? And which part you need to collaborate with others and need to form a team, right? And need to go ahead, right? If you look into the status of quantum computing, okay, it was slow, but it's picked up, right? It picked up very heavily, okay, after 2010, right? And it is really accelerating, right? In the last 3-4 years, there are many things which are happening, right? And as you know that India is also taking the quantum technology as one of the major technology roadmap, right? They are built up in the consortiums, okay, like QUST, right? And they have also defined a national mission of quantum technology. So these are very fascinating things, apart from the pioneers like Google, Microsoft, IBM, Rigetti, okay, Atos, right? Okay, Honeywell. So whom you name, right? Most of the big giants and big corporates are now into this particular technology of computing. There are plethora of domains, okay? Software domain, technology domain, enabling technology domain, okay, and a lot more. There are also some the fundings which are available, right, to support this quantum research. So this is what is a quantum intelligence, right? This is a very simple example, right? Why I like Grover Sachs. I am reading. I am working with Grover Sachs for the last 15 years, and still I am a fan of Grover Sachs. Why? Because still Grover Sachs is using quantum machine learning, and you need to only learn the parameters of the Grover Sachs by machine learning. That's one of the way you need to do. So those who are new into this, I just want to again excite them by this particular scenario of Grover Sachs. So Grover Sachs is an algorithm by which you try to search an unsorted database or unstructured database. Okay, that means you don't know where it is. That it is okay. That means the database is completely unstructured. So what you need to do, right? In a search algorithm, you need to call an oracle. So oracle, okay. So oracle contains the search query, right? Say, okay. So the element, so you have a value k, right? What do? You take each element of your database, right, and you pass to the oracle, and oracle will compare it with your search element and will tell whether the search is yes or search is no. Yes means you have found this, no means you didn't found this, like find this, okay? So in a classical, right, if you have a list of n elements, right, which are not sorted, right, you require, in the worst case, you need to search each of the elements, which means you need to such n elements. You need to call this oracle n times. Right? Because each element you need to push to the oracle, and the oracle will test whether this particular element matches the search criteria. And in the worst case, you will get the element at the end, or you will not get it at all. Right? So you need to call the oracle n-1 or n times, and then you can tell whether it is there or not. Okay? In the worst case. Now, what happens in the quantum? So in the quantum, right, you can encode, right? You can this is called quantum encode, which is also a very interesting thing, right? You can encode all your elements, okay, in a quantum state, right? And you can generate all the elements. Suppose you have 16 elements in your quantum. That means, for example, this example is 8 elements. So there are 8 elements in your, okay, that means in your bouquet, right? And you have to find that which element matches your search criteria. So what do you do in quantum, right? You encode each element and you generate a superposition, right? Right? And this superposition will actually consist of all the elements in superposed form. Because if you see, you have all the 8 elements, 0, 0, 0, 1, 1, 1. And at the start, you can tell that, hey, they're all equivalent because all of your elements can be your search item. Okay, all of your elements is equiprobable. Sorry, all of your elements is equiprobable. Okay, to match your search criteria. Right. This is the assumption, and this assumption is very good in the quantum domain. Right. You first to generate your equiprobable superposition. Though in my initial research, I worked with some of the students and to generate a bias superposition. That is also very interesting, but we couldn't find much algorithmic exploitation on that, right? But bias superposition can also be done. Right? It's not that you always generate the equal superposition. But for this example, let us assume that this is equal superposition. Right? You pass it to your oracle. Right? Oracle is a function f. So oracle will simultaneously evaluate with all the superposed states. Right? This is very interesting. This is called quantum parallelism. Right? And this will superpose and this will come up, right? So what we will have only one state which is responding yes and all other no. And that's the state you hold after the oracle. So oracle need not to be called n times. Oracle is only called one time, and that oracle takes the entire superposition states and generates the results also in a superposition. Okay, for example, if I go to the next slide, okay, this is the result of superposition. So oracle will, okay, yeah, this is the result. This one computer. So in the classical computer, you have to go one by one. In the quantum computer, you generate result, which is superposition of yes and no. One will be yes. Very simple Grover search algorithm, only one criteria, though we can have multiple match state also in the Grover. But that I'm not discussing here, okay? So one state will have yes and rest all is no, right? And then the beauty of quantum amplitude amplification comes up. So amplitude amplification, what it does, it just takes all the states. This particular oracle, what it does only one thing. This defining this yes on a quantum state means it marks the quantum state. And marking the quantum state is normally done by a phase inversion. So this ES will be interpreted as the state which has an inverse phase compared to the all others. And now the quantum amplitude amplification works up. So what it does, it actually takes the mean across all the states. And the mean across all the states will be very closer to all the states because all the states are in the same value. And now if we subtract this mean to all of the states, you will see all of the states are reduced to a high level like this. Whereas this state which was phase was flipped, is amplified. And this you need to do sometimes, right? And Grover has proved that you need to do this do 10 times, where n is the length of your search list. So instead of n, what was the worst case complexity or worst case iterations you require, number of iterations you require, in the worst case, in Grover, you require root n. So it is quadratic speed up. Okay. This is the entire scenario in the other way. This can be also interpreted by geometrical interpretation, right? And you can go on and on this. Okay. So if you look at
Professor Amlan.
Yes.
So we also have some time for questions, right?
Yes.
So can you wrap it up in a couple of minutes?
Yes. So I will just take 2 minutes. So I will not continue further. So this is the quantum space, right? And you can get into all the good resources which are available. But I will only point out one thing, that quantum machine learning, which is the focus in this particular discussion. So in quantum machine learning, what we try to do, we know the machine learning has a lot of hyperparameters. And ultimately, how a machine learns. Okay, this is a very important question, right? That means I tell my students that how do you know how a machine learns? So how do I know that how my student learns? Okay, my student learns when I see that the student does good in his or her examination. So there is an examination which the student has to qualify, and based on that I know the student learned. So now I know that, okay, if the student gets 50%, he has learned. Maybe another faculty will tell, no, if the student only gets 80%, he or she has learned. Another faculty can come up with, okay, no, if the student is 90%, he or she has learned. So it means that the learning depends on the performance. Okay, that means if you do a good performance, you have learned well. If you didn't do a good performance, your learning was not good. And the performance also varies from the domain. So if this is a very hard exam, I know that if the student scores 50%, I will tell it's okay. But if a very easy exam, if a student scores 90%, then only I will tell it's okay. So it's a domain specific also. So the way we try to do is that, how is the performance of my model? That's the key of the performance. So we try to look into the performance of the model, and we try to iterate on that, and we try to try to modulate the parameters so the performance is better and better. And then we tell that it has learned well and well, right? So to tune this is an optimization problem which can be very well defined in the search space, right? In the search space, you need to find the best possible parametric values, right? And need to fit it to your model so that your model is perfect. And as I said, the Grover search, similarly, you can define Grover search, you can use Grover search. Similarly, there are other search algorithms which can be very well used to tune these particular parameters of a machine learning model and make its performance good. Though there are other strategies also, right? I've only given one strategy based on the discussions what I have done, okay? So here I end. I just set the quantum machine learning context here. There are beautiful applications. There are some recent advancements done by our group, which is an MNJS algorithm, which is a fast true quantum and colony optimization demonstration on the entirely quantum algorithms. Previously, we had quantum algorithms which are hybrid, but this is the first of its kind algorithm which was done in the entirely all the steps. That is your path. Okay, that means your generation of the path, doing the pheromone deposition, doing the pheromone annihilation, searching the best path, all were done in this particular, in the quantum settings, right? That was very important, and that's why our algorithm was became so popular. This is a entire flow. The paper is already there in the IET. It has got recently accepted in the IET, and these are our results, which is a good contribution. I think one of the good contributions from Indian researchers in the artificial intelligence domain is in the quantum platform. Okay, right? And the next is obviously another thing which we are proposing is a QDLC. This is also an upcoming work we are doing, right? How we can leverage the entire quantum stack, right, in the development platform. How we can leverage the quantum stack as a business platform, business development platform, right? That's the proposal of quantum DLC. This is also an archive paper at present. We are also finalizing this paper for a submission, and we hope that it gets through, right? This is a recent announcement of this particular award what we got from IBM, and I will just close here. these are the achievements what we have done in the quantum domain, right? We have a lot of quantum research activities going on in our department, in our school, and we have a lot of international collaborations, and we have a lot of corporates, research groups are working with us. To name a few, IBM, TCS, HCL, and few are also there in the pipeline. We have good PhD students. Many of are absorbed by industries already, and we are looking forward to more students and more interns and more collaborations in this particular domain. Okay, so that's all from my side. If you want to contact, you just connect me through my email, and yeah, that means I will be very happy to connect and collaborate and to help the researchers in the quantum domain. And I hope that my lecture will help you to understand the real nuts and bolts of quantum computing. Okay? Yeah. Thank you.
Yeah. Thank you very much, Professor Amlan. It was a very nice presentation, and it was very elaborated. Yes. I wish we could give you more time to present more about your work. Yes. But maybe we will talk. Yeah. On the Discord channel, maybe participants will have questions. But yes, you can ask Professor any question you want. But there is a question I can see. It is a general question, like so Devashree is asking that there will be any courses in quantum computing in University of Calcutta available?
Yeah, so we have started the courses for our students. We will be starting these courses, maybe short courses, from our department in collaboration with some other organizations, maybe QRD Lab, which is an incubated, from our university. We are planning these courses, and I hope that next year we can start the courses. Presently we are taking the courses to all our undergraduate, our master students on quantum computing, and the response is very good. Right? A lot of interns are there, so those who wants to work, they will automatically get to the courses as interns, right? And then we always have a selection process for the interns, but you can always apply for internship and you can connect to the courses. Yes,
that's amazing. Thanks for the information. And if you have any questions regarding the slides, you can just ask. But if the questions are not directly related to the slides, then you can just post them on the channel, and Professor is going to answer them as per your queries.
Yeah, so any other questions amplified, you can also mail me the questions. Okay, it's Anshul knows me, Anshul connects me very often. So if there is any question, you can put it to the organizers. I will be very happy to answer them also that means
Professor Amlan, we have a lot of questions coming on Discord, so I will be mailing it to you, and hopefully we'll be posting up the replies quickly.
Perfect. Hope all you have enjoyed my lecture.
Yeah. Thanks so much.
Thank you, sir.
Thank you.
Great, fantastic. Thank you very much. All right, I think yes. So if you have any questions, you can also post your questions on the dedicated Discord channel towards quantum intelligence. But now let's move on, and it's time to invite our second speaker, Manush Gupta. So Manish, Dr. Manish Kumar Gupta, currently works on quantum machine learning in Poland with Dr. Piotr Gawron in AstroCent. So Manish, welcome. Thanks for accepting our invitation. And today Manish will give a talk titled Quantum Machine Learning Using Pennylane. So Manish, if you are ready, we can start, and the Zoom is yours.
Thanks, Paul. So let me share my screen.
Yeah, we can see your slides now.
Okay, great. Let me just put it in full screen mode, so it's visible to everyone.
Yes, I can see it at least.
Okay, great. So let's start the talk. Thanks, Paul, for a nice introduction. So I'm Manish Kumar Gupta, and I work at AstroCent in Nicholas Kopernikos Astronomical Center, Polish Academy of Sciences, with my advisor, Peter Gawron. So first, I would like to thank Peter for helping me in preparing the slides. So now let's jump into the main topic, which is quantum machine learning using Pennylane. So the agenda of this talk is as follows. So first I would be describing a little bit on machine learning and the flow of the machine learning, basically the algorithm of machine learning. And then I will talk about quantum computation and postulates of quantum mechanics. And then we'll try to understand how this quantum computation fits in this setup of machine learning. And after understanding this, what we are going to do is that talk about quantum machine learning using Pennylane, where I'm going to explain a little bit about hybrid form of computation, talk about gradient optimizers, and then with some examples, we'll conclude. So let's jump into it. So what exactly is machine learning or deep learning? So deep learning is a subfield of machine learning based methods using artificial neural networks and with representational learning. So what exactly it means is that these artificial neurons are inspired by the neurons in the brain. And the layer of these artificial neurons are able to capture the data and these neurons forms the layers. And using this setup of layers of neurons, you are able to produce, you are able to train the model and produce the output, which is from the same distribution as input training set. The machine learning model has a particular structure. The algorithm looks like this. So it has 4 steps. You define a model, and then you define a cost function, and then you try to compute you minimize the cost function using a gradient descent algorithm. And this, after you have trained the network using the input data, you try to predict using the trained model. So the first part of this algorithm is you have to define a model. So the model is defined with a function f, which takes 2 parameters, the input data set x, which is used for training, and the free parameter theta. And what you do is you multiply the input data with a free parameter w, a set of free parameter w, and then you add another set of free parameters b, which is generally called bias. And then you apply a decision function, which is sigma here. So after, when you train the model, you get a trained function f of x and theta. Now you define a cost function, which is basically tries to calculate the error. So f of x and theta gives you the error in prediction. So this cost function is basically the difference between f of x of theta and the actual prediction. So when you train the network, you get a f of x of theta, and when you give the input, it will generate the corresponding output. And you take the difference, how far the prediction is from the actual output, expected output. And you add this, and this defines your cost function. The point is that the error in the prediction has to be minimized. And this cost function captures this error. Now, when you are given a function, how you're going to minimize it? So we use our old technique of calculus using gradients. So you first compute the gradient with respect to the parameters, which is theta here. And then you update the parameter, the free parameters using this gradient descent. So, I mean, you update the parameter theta at time t plus 1 equals to theta at time t, and then you subtract the eta times the gradient. So you are trying to move in the direction of steepest slope. So you are going a downhill to try to find the minimum of this hill, where eta is your learning rate. And this process is repeated until a convergence is reached. So you want to minimize the error, and you define that you want to have this much error. And once that is reached, your model is trained. Once the model is trained, what you do is you apply the training set and see what exactly this model is predicting. Now, this is the general flow of a classical machine learning algorithm, okay, deep learning algorithm. And now we have to understand how we can apply quantum computing with this. So now the current machine learning algorithms are, the current machine learning algorithm is very powerful, and there are many softwares for it, software libraries for it, like TensorFlow, PyTorch, and Autograd. And the reason why it has been progressing so well is because of the hardware availability and special kind of GPUs which are available now. So at some point of time, with increasing amount of data, this could be a problem. And now we have quantum hardware in market, and it has come up with a promise that it can solve hardware problems. So what can we do about it? So now we have a hard problem in hand of optimization, which is basically machine learning, and how can we apply quantum hardware to machine learning? So before we jump into how we can apply quantum hardware to machine learning, we have to understand quantum computation. So this is a general setup of a variational algorithm where you have a classical computer and you have a quantum computer, and this classical computer wants to use this device to do some computation. So what it is going to do is it is going to send some control information to this quantum computer regarding the state preparation, regarding parameterized unitaries, and the type of measurement it has to do on the quantum computer. And then the quantum computer applies these parameters and runs the simulation on the hardware, runs the circuit on the hardware. And then you apply the measurement to get the classical result, because classical computer understands bits, not quantum bits. So you have to get something which is classical, and measurement does that. And it returns back to the classical computer. So if you have an optimization and you want to take advantage of a quantum computer, you have to optimize some particular routine and offload it from classical computer to a quantum computer. And the cycle repeats until your goal is achieved. Now, this computation can be seen as an experiment on a quantum device, where there are 3 stages of this process. First is state preparation, then second state is evolution, and third state is measurement. So the first stage of this experiment is preparation, where you are going to create a state with a given state parameters. So it is basically configuring the qubit state, and then you evolve this qubit state using some unitary evolution using this operator, U operator, and this is called evolution. And then after the state has evolved, you try to make measurement on the qubits. And after measurement, what you get is the classical result, which falls in the classical domain, and you send it back to the classical computer. Now, to understand these 3 stages and the associated units of it, so we jump onto the postulates of quantum mechanics, and we'll try to understand what exactly a state of a quantum system is. So the state of a quantum system is a complex unit vector in an n-dimensional Euclidean vector space, Cn. And this complex space is spanned by basis vectors, which we call computational basis vectors. So it is represented by kets, where 0, this is the ket representation, and it can also be represented in the form of matrix. So it is basically a column matrix, and there are n-1 basis vectors. So it is represented also by a column vector. Now, the ket this form, I mean, this representation is called ket vector, and ket vector, any state vector can be expanded in terms of these basis vectors. So these are the basis vector, and it is a linear combination of these basis vector where x0 up to xn minus 1 are the coefficients of these basis vectors. And it can be written in the matrix forms as x0 up to xn minus 1, these coefficients as a column vector. Now, the dual vector of the ket vector is called bra vector. The notation is like this. And it is basically when you take a complex conjugate of the ket vector, what you get is your bra vector. And it is represented as a row matrix. Now, this state space is equipped with an inner product, which is called bracket. So you take multiply the ket vector with the bra vector, and this gives you a scalar number, which is called inner product. And there is another notation which is called outer product, so which is called ket bra, where you multiply the ket with the bra. Now, a general state of an n-level quantum system is normalized linear combination of basis vectors. So suppose psi vector psi is written as a linear combination of these basis vector from 0 to n minus 1. So the basic statement here is that this vector has to be normalized. What it means is that these complex coefficients alpha 0 to alpha n minus 1, the square of those numbers has to add up to 1, and this is called normalization condition. So suppose you have two vectors. I mean, it is important to know that when you have two vectors, they represent the same physical state if it varies by a phase factor. So the eta or I theta is called your phase. And when you have two vectors, which is different, only differ by a small phase factor, they represent same physical state. Now, the state vector of a qubit can be represented on a unit block sphere, or on a unit sphere, which is also called block sphere. So the two polar points are the eigenvectors of a poly Z matrix, which is 0 and 1. And then on the x-axis, you have your diagonal and anti-diagonal vectors, basis vectors, and on y and minus y, you have right circular and left circular polarizations, which can be represented in terms of the basis vector, computational basis vector 0 plus I1. Similarly, for diagonal and anti-diagonal, it will be 0 plus 1 with normalization of 1 by root 2. So now we are going to come up to time evolution of a quantum system. So given a state, the state is going to evolve, and how it is going to evolve. So evolution of a quantum system is governed by Schrödinger equation, which is represented as d psi by dt equals to IH times psi. So basically, it's a rate of change of the wave function equals to minus I times the Hamiltonian of the system times the state vector. So where H equals to H dagger is called the Hamiltonian of the system. It's an operator, it's an observable, which corresponds to the energy of the system. Now, suppose you want to evolve in state from time t0 to t1. What you do is you apply the unitary from t0 to t1 on the starting state, which is at time t0, and the final state after evolution becomes psi t. And ut0 to t1 is called unitary operator, which drives system from t0 to t1. The property of a unitary operator is that u times u dagger equals to u dagger times u is identity. Now, if the Hamiltonian H is constant between time t0 to t1, you can represent that unitary as e to the minus I times the time t1 time difference t1 minus t0 times the Hamiltonian of the system. Now, suppose Hamiltonian of the system is not constant between the time t0 to t1. What you have to do is you have to apply this unitary over a very small time scale where the time is constant, the Hamiltonian is constant over that particular time interval. Now, when you apply these unitary gates, what happens is the state evolves. So if you want to see it on a block sphere, you can see that state vector can evolve from one state to another on application of unitary. So in this particular case, what you are trying to do is rotating a vector about the y-axis. So you can see this is the y-axis. And when you apply unitary operator, you can actually do a rotation around this y-axis. So it can move from this point to this point or this point to this point, depending upon the theta. Similarly, this block sphere figure represents the rotation of unitary vector on the equator around z-axis. So the rotation axis is your z-axis, and the vector is being rotated around this z-axis. So this represents your rotation of the state vector. Now, we have come to a point where it is important to mention that quantum measurement is an important part of this circuit. So when you measure something, what you get is a real number, which is classical. So you define a set of projection operators, P, which is represented by capital P, which is set of small pi's. And corresponding to each projection operator, you have a measurement outcome, which is represented by AIs. One of the properties of this projection operator is that it sums up to one identity. So when you sum these projection operator, what you get is an identity. When you square this projection operator, you get back the projection operator. Now, suppose you want to measure the probability of outcome AI. What you have to do is you have to sandwich this projection operator PI between the ket and the bras, and it will give you the probability that what is the probability of getting an outcome AI corresponding to this projection operator PI. And when after the measurement, the state of the system is changed, and the new state after the measurement is represented by this equation, where the state after measurement psi of AI is equals to projection PI times the psi, and then you normalize this new state with this value, square root of this value, which is basically sandwiched between size of the PIs. To give an example, suppose you have a state vector which is on a block sphere represented by this black arrow, and the representation is square root of 0.07 times this basis vector 0 plus square root of 0.3 I times the basis vector 1. And now suppose you want to measure it in 0 and 1 basis. So when you measure it in 0 basis, which is represented by P0, what you get is a probability of the state being found with 0.07 in this direction. And when you measure with P1, which is the projection operator which projects it into +1, then what you get is the probability of getting in this direction to be 0.03. Now suppose another example. Now you have state vector, which is represented in the computational basis, same initial vector, which we used for the previous example. Now you want to measure in another basis. So you have the projection operators Q plus and Q minus. When you measure it in the plus direction, the probability of being in that direction is 0.958, and in the minus direction, which is basically your left circular, is 0.42. Now, you want to compose you want to combine two qubit systems. So what you do is you take the tensor product of two qubits. So suppose you have the first state vector psi, which is represented by your row column vector, psi naught and psi 1, and it's represented in basis form using psi naught with basis vector 0 and psi 1 basis vector 1, similarly for phi. And when you create a new system, which is joint state over C square tensor C square, the new state is represented by psi tensor phi, and it can be represented as a column vector, which is tensor product of two matrices. Now, after we understand the basics of, required elements of quantum mechanics, we are going to jump on quantum circuits and what exactly is quantum circuit. So we need to understand this. Why? Because this would be used in the next part of the talk, and it will be required for understanding the machine learning programming using Pennylane. So quantum circuit is a new paradigm of computation. So a quantum circuit is a computational routine consisting of coherent quantum operation on a quantum state. So basically what it means is that you have a quantum state represented by qubits, and what you do is you apply unitary operators to evolve the qubits. So in this pictorial representation, this Q0 represents the qubit system 0, and Q1 represents your first qubit. And these purple boxes, represents your unitary gates which act on the first qubit, and this purple set of gates acts on the second qubit. And this plus is a C0 gate which acts on these two qubits together. Now, this symbol, measurement or meter, is a representation of a measurement. When you apply the measurement on the first qubit, you get a classical result, which is stored in a classical register. So the power of quantum, where does the power of quantum computing comes from? So the power comes from the ability to interfere complex amplitudes in a very high dimensional vector space. And this gives the power to the quantum computing. Now, quantum circuit has three states, as I discussed. The state preparation, where you prepare some initial quantum state psi, generally in the 0, 0 state, and then you apply a unitary transformation, parameterized unitary transformation, U theta, using a sequence of quantum gates, and then finally you measure the evolved state using some observable O. Now we understand quantum circuits. Now let's jump into how we can do quantum machine learning using Pennylane. So you need to remember the first section of the talk where I was talking about machine learning and the general flow of the machine learning. And since we have a quantum hardware, okay, I see some red lines coming on my slides. I do not know from where, but it's not mine. So you should remember that the first section of the slides where I was talking about the general flow of machine learning, where you had 4 steps. You have to define model, find the cost function, and then you optimize over it. Okay, you optimize over it. In that you have to fit the quantum model of computation. Now you have a hard problem. So this is a hybrid model of computation. Excuse me, somebody is doing. Can somebody stop doing this? Oh, Pavel, are you there?
Yes, I've just cleaned the screen, so it wasn't me. I'm not sure who did it, but I just cleaned it, so it should be fine. Okay. So I guess that someone just probably did it by accident.
Okay, okay. Thanks, Paul. So quantum computing comes with a promise that it can solve hard problems, and quantum machine learning is one of the hard problems. So it's good to see how exactly you can apply the technique of quantum computation as well as machine learning to see how good it works. So we come up to the concept of hybrid computation, because the current quantum hardware has a lot of noise, and you still have very small number of qubits. So you can only run very small shallow depth circuits. And to take the advantage of quantum computing, what you do is you divide the algorithm into two parts, the classical part and the quantum part. And this hybrid form of quantum computation is represented by this graph, where you have two types of node, classical node and quantum node. Classical node is represented by a orange color box, and your quantum node is represented by a green color box. So when you have an algorithm, you have two parts, the classical part and the quantum part. And in the quantum part, you pass on that subroutine to a quantum hardware. So with on the quantum hardware, you have a device, a physical device, which is associated, which is called quantum device, and a variational circuit, which would be run on that particular quantum device, which is represented here by a state and a unitary and final measurement. And this would be a loop. So classical node will pass some parameters to this circuit, and it will run that circuit. You do measurement, you get the classical output, and you send it back to the classical node. And this process repeats until unless you optimize. I mean, suppose in case of machine learning, you are trying to optimize this cost function as we discussed earlier. And this algorithm is going to run as long as this optimization is not achieved. Now, one of the problems for using this quantum node is that you have to find gradient, because finding gradient is important for optimization. So you run the variational circuit twice using a parameter theta plus s and theta minus s, and by running the computational circuit twice, you can actually calculate the gradient of this quantum circuit. So now you have the cost function, which has subroutine running on a quantum computer. You can calculate the derivative of it. So now you can actually minimize the function. And after running the circuit, you have to measure something. So now we have an observable. So observable is a quantum measurement whose labels are real number. Mathematically, it is represented by Hermitian operator, where O dagger equals to O. And the expectation value of the operator is calculated by sandwiching the operator over the state vector. So you multiply, you take a sandwich, I mean, with the state vector psi and ket and bra. For example, suppose we observe the spin of system. So expectation value tells us that the average spin of the system in a given state. Now, we are going to see a more detailed view of the original picture, this picture of finding the gradient, how exactly you compute the gradient after running the circuit twice. So this form of calculation of gradient is called parameter shift rule. So before we jump into parameter shift rule, you can ask the question, how can we calculate? I mean, classically, we can calculate the gradient of a function, right? Using the regular gradient method, which we learned during calculus, where you take the function f of theta, you calculate f of theta minus f of x minus theta, and then divide it by 2 theta. But that method is approximate. So when you run this algorithm many times with the normal differential, then it is going to cause errors. So that's why we need to have an analytic form of gradient for this quantum circuit. So parameter shift rule gives you the exact gradient of a quantum circuit, which is represented here by f of theta equals to average of the observable over the evolved state, which is psi times the u of theta, where u of theta is given by e to the minus I theta, where G has two distinct eigenvalues minus R and R. Then for this particular function, your derivative is given by del of f with respect to theta. Partial derivative of f with respect to theta equals to R times the function theta plus S minus f of theta minus S. So you are going to use same circuit, but with two shifted parameters, theta plus S and theta minus S, where S equals to pi by 4 minus R. So that's how you get the name parameter shift rule, because you shift the parameters by some amount and rerun the circuit twice. For example, for X gate rotation, poly X rotation, you can calculate the function for a function which rotates the state vector. You can calculate the theta by taking the partial derivative with respect to theta, and then the derivative would be 1/2 f of theta plus pi by 2 minus f of theta minus pi by 2. Now, in gradient descent, when finding the minimum, you need some optimizers. So there are several optimizers. Generally, we use gradient descent, but there are several others, which are Nestrov momentum optimizer, Adam, and AdGrid, where eta is your step size and m is your momentum. So here, what you see is you calculate the next set of parameter based upon the previous parameter and the gradient. And same with this momentum optimizer, you have a momentum and you take the concept where you have a ball falling from the hill and it will have momentum, and you want to make sure that if it is not stuck in a local minima. So that is the advantage of having Nestrov momentum optimizer. Now, finally coming to the Pennylane. So what exactly is Pennylane? So Pennylane is a software framework which allows you to use your standard machine learning libraries, which is PyTorch, TensorFlow, or NumPy, okay, and then allows you to run the machine learning code on either simulator provided by IBM Qiskit or Strawberry Fields, which is optical device, or on a Rigetti Forest or a Q-Sharp or Google Cirric quantum hardware, or maybe on some simulator. So you have your old machine learning libraries, the classical machine learning libraries, and this Pennylane provides a framework to run this code on a quantum hardware. So let's take our first example. So here what I'm going to take is you have initial state. You are going to do a rotation about x-axis by a parameter phi1, and you are going to rotate it around y-axis by a parameter phi2, and then you do a measurement in the sigma z basis. And suppose you want to write this variation algorithm and you want to minimize what exactly you are going to get. So what you're going to get is you are going to start from a vector 0, and then you do rotation, and you have to find phi and phi2 such that you get a minimum of this function, because your observable sigma phi represents your cost function, and that would be -1, we know. And how would you implement this? So what you're going to do is you're going to import the Pennylane QML package, and then you are going to call gradient descent optimizer. After importing these two, you have to create a device where this circuit is going to run. This right now I'm going to use default device. You can use another devices, like devices from Google or Strawberry Fields or any other simulator. And this wire represents how many qubits you are going to use. And with each node, you have a corresponding circuit that is going to run on this device. So you first define the circuit. So you create the function circuit with the parameters, and then you apply the gates QML times Rx, your first gate, which takes the parameter var of 0 and applies to the qubit 0. Similarly, you do apply the second rotation Ry and apply to the qubit 0. And then you do the measurement in the poly Z basis, and you return that value. And now you have defined the circuit. Using this statement, you attach this circuit to the device. So this circuit is going to run on this qubit device. Now you create an optimizer. Here we create a gradient descent optimizer, and then you run this variational circuit to minimize. So you start with initial parameters, some random parameters you can choose here. For example, we are choosing 0.5 and 0.2, and then run this variational circuit for a certain number of times. And this optimizer generates the new set of parameters for the given circuit using the initial parameters. So this new parameter would be again fed back, so that after 30 steps, you will see some minimized value of the cost function. So if you want to see on a block sphere, you started with some state, because when you set the var to be 0.5 and 2, you started with some initial state. And after running 3 different optimizers, your gradient descent optimizer, your net stroke momentum optimizer, or Adam optimizer, you see the path followed by the state vector after the optimization. So you see a different path that was taken by state vector during the optimization process for 3 different optimization strategies. Now, that was a dummy example. Now let's talk about a real example. So we take an artificial data set, which is Moon data set from sklearn library. We create a data set which is basically 2 semicircle of data, which represent your 2 classes. Now, before we use this data set, we have to basically normalize it. So this is the normalization you're going to do. So x original minus the minimum of the original. This represents your data sample, and you take the minimum and then divide it by the scale. So maximum of the maximum value in that data minus minimum value of that data, so that all the samples lie between 0 to 1. Now, since we have to apply encode this on a qubit using rotation, we are going to scale it to between 0 and pi. So this is the scaling. Now, the next step is to encode the data. So now, first what we did is we created a data set, a Moon data set. Then second step, we normalized it and put it in a range between 0 to pi, so that we can apply it as a, rotation. We can apply the rotation. And then finally, we are going to encode these features on a qubit state using this UE, unitary gate. So suppose you have xn features into data set. So what you're going to do is you take the initial state, which is initialized in 0, and you apply this rotation unitaries to do an encoding. So in this particular example, you have your first feature is encoded on a first qubit, second feature is encoded on a second qubit, up to n features on n qubit. Where rotation is given, rotation around x is given by e to the minus I phi times poly x divided by 2, which can be expanded in terms of matrix as cos phi by 2 minus I sin phi by 2 minus I sin phi by 2 and cos phi by 2, where this rotation falls between 0 to pi. Now, once we have encoded the features into the qubits, now we need some sort of variational gate. So in this particular example, we are going to take this variational gate UV, which entangles the information and is parameterized by angles, which we are going to learn after training. So the parameters we want to learn from the data. and L denotes the number of layers. So these are your layers of, quantum layers. This is the first layer, this is your second layer. And in each layer you have your rotation, which depends upon 3 parameters, alpha, beta, and gamma. And then you have another gate, which is called C0 gate. It's control not gate. So it is going to act on the first qubit and second qubit and third qubit and fourth qubit and fourth qubit and first qubit. And you are going to repeat. So this forms your layers of the deep learning neural network. Now we need a decision function. So because you have to do some measurements. So what you're going to do is you write the function f as average of some observable over the evolved state. So this, if you remember this, your initial state was 0. You applied an encoding using an unitary UE. Then you applied the variational circuit, UV, and then you measure some observable on the evolved state. So in this particular case, what you are going to do, if you expand this, what you can see is that this is your observable, and then you see the initial ket, your encoding unitary, and then your variational circuit unitary. You evolve the state. So you're basically, this is psi at time t, and this is bra at psi time t, and you take the average. And in this particular example, the O is, we measured the first qubit in the poly Z basis and do an identity operation on rest of the qubits. Basically, we ignore it. So this will measure the first qubit and give you a classical result. So poly Z matrix is represented by rows 1, 0 and 0, -1, which has eigenvalues 1 with eigenvectors 0 and -1 and 1. And then finally, you need a classification function which classifies your predicted data. So it acts on this f of x of theta, which is trained, and you apply this sine function. Now we have to actually do the training. So you take the data, you divide it into train set and test set, and then you initialize this parameter for the W, which varies between 0 to pi, and then you write the cost function. So here your cost function is your y, which is the given y, the given y from the data set, and this is your predicted y. So when you apply the x train, you get a prediction and you calculate the error. So y train minus f of x train comma theta, which is your free parameter, and then you divide by the batch size. So you would be running this this cost calculation over a batch of size eta t, and to find the average, you divide it by eta t. Now we have come to an actual example implementation. So first you have to do certain imports. So you are going to use iter-tools import, where you have to create an iterator which gives you the data samples. Then you use the sklearn library, which is very commonly used by machine learning people. And then you use shuffle for shuffling of the data. Then you have to normalize the data. So you use min-max scale, and then you again, you have to divide the data between train and test set. So you use this function. Then finally, you need some sort of matrix or to calculate the accuracy, how the prediction is going. So you need matrix. And then you have to import QML from Pennylane, then NumPy from Pennylane implementation of NumPy. And then you have to do encoding of the data, which is rotation. So we are going to call angle embedding. And for entangling the layers, we are going to call strongly entangling layer. And finally, you need to initialize this entangling layer with some initial parameter. So this function will give you a set of initial parameters from a uniform distribution. Now, you create a seed. You create a seed because you want the results to be reproducible. Then you create a data set using moons. You create a set of data of 100 points and noise parameter of 0.1. And you also provide a random seed so that you can reproduce the data set. So it is going to give you 2 sets of data, which is in the form of semicircles. And then you shuffle this data because you want to randomize it. You do not want a particular order, you want to randomize it. And again, you provide it with a seed. Now you're going to normalize the data using min-max scale so that the feature range falls between 0 to pi. Now you're going to split the data between the train set and the test set. So your X train and Y train represent your first training set, and X test and Y test represents your test set. And this is your whole data set, X and Y. And now test site specifies how much of samples you want in the test set. Now to encode these features, you need certain number of qubits. So this x.shape tells you how many qubits you want. So we know from the data that you have two classes from the moon data set. So n qubits would be 2 in this particular case. And as we had seen in the previous example, you have to create a device. So we are going to take the default qubit device, and then we are going to specify how many qubits we want, so which is represented here in Pennylane by wires. Now you have to create a quantum circuit as shown previously pictorially. So you create a circuit with given weights and you do angle encoding. So basically you are going to rotate the qubits based upon the features, and then you are going to do entanglement. So you're going to create layers, strongly entangling layers, and then you specify number of wires. And then finally you are going to do a measurement on the first qubit, which is represented by 0, a poly measurement on the first qubit. And then once you have your circuit ready, you are going to attach this circuit to the device on which you are going to run, which is in this case is a default qubit device using this QML QNode device statement, which is a decorator form. Now we have the circuit, we have the device, we have to create a cost function. So cost function takes the theta and the input data and calculate the expectation, and it creates the predicted. So it is going to run circuit with theta from x in x, I mean all the elements in x, and it is going to calculate the predicted value and take the mean. So you have predicted value, you have expectation because you have already passed. So this is basically y which you expect, and this is the prediction after training the model, and you calculate the loss and you return. So I mean, as we discussed previously, you have a loss function which calculates the difference between the actual expected value and the predicted value. And finally, you have your classification function. Now, since for this example, we are going to specify, we have three layers. Now you convert to start the learning procedure, you have to change the classes because I mean, you know that for polymatrices, the eigenvalues range from -1 to 1. So you have to change the Y train in this range. So you change wherever you see a 0 to -1, and whenever you see a 1, you keep it as 1. We take the batch size as 5, and then you calculate the number of batches by taking the total number of samples present, and you divide it by the batch size, which is in this particular case is 5. So you will get the total number of batches it has to be run. and you select number of epochs, how many times you have to run the algorithm. So you can, you can select any number, but we have chosen it to be 5. Now you have to initialize the entangling layer. So you have to use this function to create a set of parameters, initial parameters, which basically generates using a random number, a uniform from a uniform distribution. Now, the next step is to create a variational classifier. So in this particular case, we are going to use Nesterov momentum optimizer. And this is your optimizer. And then you are going to split the input X into batches. And then you are going to run over all the batches using this chain, where batch cost is calculated using a lambda function, which takes in the cost function as specified and where your X train is your, the batch, and then corresponding Y value. And once you calculate the cost, you have the batch cost, you pass it to the optimizer. It will take in the initial theta and the batch cost function, and then calculate the next step in the gradient descent, which will generate next set of theta, and it is going to loop to optimize. And this is the end of the learning loop. Now we have to calculate how successful the training was. So what you do is, with the final theta, you are going to run the circuit on the test set, and it is going to generate you the scores. And then finally, the scores are between -1 and 1, but the original Y prediction was from 0 to 1. So you had to apply this sign function, which is classification function, on the score, which converts -1 to 0 and 1 to 1. And that gives you the actual prediction. And you calculate the accuracy by, subtracting and taking what is the percentage of getting the exact results. So these are the two matrices. Now, we come to almost end of the talk, where we are going to see how this learning is taking place. So in the first step, with randomly initialized parameter, the classification accuracy was 0.40. On x-axis, you have feature 1. On y-axis, you have feature 2. And your red dots represent one cluster of data, one set of data. Your blue dots represent another cluster of data from the moon data set. And you can see using this contours that the classification accuracy is poor. Now, in the second step of the classification accuracy changes to 0.40, and still you can see from the contours the classification is not happening properly. In the third step, the classification accuracy increased to 0.41. Now in step 4, again it is increasing, and you can see that the blue region is coming in capturing the blue dots. Now step 5, the accuracy increases to 0.54. That's step 6, accuracy increases to 0.59. You can see that this blue region is capturing the blue part, and that's why the accuracy is increasing, and the red region captures the red part, red dots. Now in step 8, the accuracy still increases to 0.63. And then in step 9, 0.58, you can see that classification is happening. The blue region it captures the blue dots, and the red region captures the red dot. Step 10, 0.65. In step 15, it is 0.79, and you can see it is increasing to 0.79. And finally, in step 20, the blue region is capturing the blue red dots, and the red region is capturing the red dots. So now finally we have come to the end of this talk, and what we have, we have to conclude. So what we have learned today is what are quantum states and operations, how a quantum variational algorithm works, and what is quantum neural network. and how to program a quantum machine learning. And there are several things which is, much more than what is there in the list. So we have not learned about barren plateaus, which is basically when the gradient is a very small number, what you're going to do and how you're going to do minimization. Then how well QNNs can express machine learning algorithms, and then various architectures of QNNs. So we have not seen these things, and there are several other things which we haven't. These are some of the important references which if you may want to go through to learn more about it.
Okay.
And this is the comics written by my advisor Peter Gavran. It is in Polish, so this is in Polish. So if you are Polish, you know Polish, you can probably download the first version or buy a new one from the market, the second version. Thank you so much for your attention.
Hey,
yeah,
great.
Thank you very much. This was a very nice talk, and thank you for the tutorial also on Pennylane. So there is an obvious question people are asking, that apart from the slides, are the codes are available in repository or?
No, I can put the codes on the repository, because this was a very simple example, right? So it was not, it is not very useful, but it is just for understanding how exactly this thing works. Because if you take a very complex example, sometimes it's very difficult to understand what exactly is going on. So
yes, exactly.
Yeah, so we can put that. We can probably put that on GitHub.
Yes, and people are also asking about that. The codes are running in Python. So yes, how do you run it on real quantum devices?
So if you see this statement, okay, so this two statement, right, from line 35 to 43 is very important. Okay, to understand that, I have to take you back to the picture where I started. This hybrid computation. So you define a Q node. This is your quantum node, and related to this quantum node, you have the circuit which you are going to run, and you attach a device corresponding to it. Okay. So if you understand this structure, you have a classical node, you have a quantum node, and for the quantum node, you have a device and then a circuit. And you have to tell this whole algorithm that this device is going to run a particular device, and this is the circuit. And this is represented by these set of statements. So using line number 36, you choose a device. What would be your device? Will it be a simulator? Will it be some circ device or IBM device? You have to specify this option here.
Right. Okay? So we can call any
exactly.
We can run in any real device. Just in the quotation, we need to change the statement.
Yes. So you'll have to look in the documentation. It has a particular name for every device. You just change the device, and then you have to specify some more options corresponding to that device, and then you are good to go.
Yes, thank you. And there is another question, is that modeling quantum machine learning is required to measure errors, or we just consider like an ideal case that there are no errors and we run the algorithm?
No, so every time you do any kind of measurement on the circuit, right, this would have some errors. The measurement statistics would not be very accurate. So to increase the accuracy, you have to specify here how many times you want to run the circuit for, to decrease the accuracy, increase the accuracy, right? Because you know that if you run an experiment n number of times, you can increase the accuracy by dividing the result by n, right? So this is specified here as one of the parameters, which is called shots. So if you specify 1,000 shots, or if you don't specify, it is just numerically calculated on a simulator and it will be exact. But on an actual device, you'll have to specify how many shots, and the more number of shots you put, the accuracy is going to increase. Okay. And you know the current hardware is noisy, so you'll have to have more number of shots. unless your device is completely crazy. Okay.
Right.
Yeah. So Manish, this is Himanshu. May I ask a follow-up question on that?
Yeah, please go ahead.
Yeah, so specifically in deep learning or machine learning, we have a lot of hyperparameters that needs to be tuned in order to increase the accuracy, precision, F1 score, so according to the confusion matrix. So considering the costs involved in the quantum hardware, how do we assess that how to optimize the hyperparameters and the feedback loop procedure that we typically have for deep learning, how we might optimize it for quantum machine learning specifically?
I mean, the process would remain same because you are basically offloading part of the computation, the optimization process to the quantum hardware, right? So, I mean, as per my understanding, everything would remain same. You would not have to do anything because those hyperparameters basically change the values of batch size and things like that, right? Which falls in the classical domain, not in the quantum domain, right?
Okay, and then how do we assess that we will be getting maybe a polynomial or exponential speed up for a particular quantum machine learning algorithm?
I mean, it is very difficult to say. That is the current topic of research currently, that how useful this I mean, running machine learning algorithm on a quantum device is useful or not. I mean, this is the current topic of research. We still do not know, is it good to use a quantum computer for machine learning or not? Okay, it is still ongoing topic of research. So I do not have an answer yet.
Okay, thanks. Thanks a lot.
Yeah, thank you.
Thank you for the answers. And if you have any other questions, you can put it on the channel, respective props channel, and Professor is going to answer those questions. So yeah, thank you once again for the talk.
Thank you.
Yes.
Thank you, Akash.
Okay.
Pavel, please, yeah.
Yes. Okay.
Thanks, Pavel.
So yes. As Akash said, I can see that there are some new questions on our chat. So please post your question on our Discord server, and Manish, if you have time, if you can also just take some time to answer the remaining question, then that would be perfect, of course.
Surely.
But now we have to move on because we have already a small delay. So the next speaker is Oskar Słowik. Oskar is a PhD student in mathematical physics at the Center for Theoretical Physics of the Polish Academy of Sciences and Qiskit advocate at IBM. And today he will tell us about variational quantum algorithms. So Oskar, if you are ready, Zoom is yours and you can try to share your slides.
Yes, I'm ready. Did not start the video. I don't know what's wrong.
Okay, no worries.
Can you see my screen? Hello?
Yes, we can see it.
Okay, great. Okay, so everything works. I can start. So thank you, Pavel, for introduction. So my talk will be about variational quantum algorithms, and outline is as follows. So first, I will give some motivation. Then I will move to the, let's say, the definition of variational quantum algorithms, some applications, and what is the variational method. Next, I will describe briefly variational circuits and differentiation of them, but already Manish described some of this stuff, so I will try to be brief. Next, I will move to variational quantum eigensolver, which is an example of a variational quantum algorithm. And the second example will be quantum approximate optimization algorithm. And finally, I will try to outline some limitations and challenges related to the topic and summarize. So in general, we have, we know that quantum algorithms in principle can do very interesting stuff like factoring large numbers, simulating quantum systems, and solving linear systems of equations, or things like that. And some of these tasks can be done with exponential speedup, meaning that there is a guarantee, theoretical guarantee, that there is no classical algorithm which can do it better than at least exponentially worse. But many of these quantum algorithms, for example, Shor factoring or things like that, they require fault tolerance. So, so let's say a total correction of all errors. And such a thing is not available in the nearest future. And that's the reason why researchers are trying to do something to, for example, are interested in variational quantum algorithms because such algorithms do not require such, let's say, low noise errors or full quantum tolerance, fault tolerance. And they can be, so they can be run on what we currently have, which is called noisy intermediate scale quantum. So such circuits have, let's say, moderate amount of qubits, say between 50 and 100. And they are noisy from the name. So only small depths of circuits are possible because the noise accumulates. But we already know that they achieved quantum supremacy in tasks related with, let's say, for example, we have some examples by Google, the well-known experiments using Sycamore quantum processor showed evidence that indeed these noisy intermediate scale quantum devices, even they can generate very complicated probability distributions, which cannot be sampled by classical algorithms. So now, yes, so what are quantum computers good at? So we already know they can efficiently sample from some complex probability distributions, underlying probability distribution generated by quantum circuits, and perform some linear algebraic operations in very high dimensional vector space. So in particular, if you want to model some quantum systems, then quantum computer is a natural thing to use because we can quantum systems dimensions scale exponentially with the number of constituents, as you already know. So this is very hard to do other way, at least from the dimensionality problems. So quantum computer is a natural thing to use in such a case, and to perform, for example, prepare quantum states or ansatz and things like that. On the other hand, we have classical computers, which are very well developed. They are very good at data storage, feature extraction. We have whole branch of so-called classical machine learning. You are all, I'm sure, familiar with what's classical machine learning. So in the hybrid model, so this introduction is about hybrid models. We will go to variational things later. But hybrid model, in principle, in the hybrid model, we would like to connect these capabilities, so classical and quantum computers. So because our quantum computers are very bad at the current, so we would like to allow as much of the model to reside on the classical hardware. And our models in the hybrid approach are a hybrid between classical computing and quantum computing blocks. As you already know, these quantum circuits can be differentiated, and this enables us to have automatic end-to-end differentiation of the whole thing. So this hybrid quantum classical model is a learning heuristic in which both the classical and quantum processors contribute to the indicators of the learning performance. That's the and the idea has been already presented by the previous speakers, so I won't dwell into that. Here is an example of such a hybrid model. So it operates on quantum data sets. So you can have quantum data set or classical data set, but here is an example of quantum data set, which is firstly, let's say, processed by some quantum model, which has some parameters. So their operations depend on the parameters. And then we have, after quantum model, we always have some measurement operation, because the quantum states are not accessible. We need to measure to have any information what's going on. And then it's post-processed by some classical model, for example, a neural network. And finally, there is some optimizer, which optimizes both quantum model and classical model. So it changes the parameters, uses this end-to-end differentiation of the whole thing. And you can use some gradient methods, as already has been said, to train the whole thing. That's the hybrid approach. And this is like a hello world example, that you have quantum data, which are points on the block sphere, and you want to do a classification of this data into the two data sets, which are denoted by colors. So for example, first you can have just one qubit gate with one parameter theta, and Ry theta is a rotation about I-axis by angle theta. Yes, so by varying this theta, you can rotate the whole thing, and then you have measurement in the z basis, which is the projection. So you can imagine that if you change this angle, the data will be better or less separated. And then afterwards, you have, let's say, two simple weights. You calculate, you do a softmax, and you have some probabilities, and this is like a toy model of a binary classifier for quantum data. But another example is hybrid quantum classical neural network, where you have quantum neural networks and deep neural networks connected into this such a hybrid structure. And you also can do backpropagation in quantum neural networks. So the whole thing is end-to-end differentiable, and it can be trained. From the perspective of the classical optimizer, this is something it can train, and that's all it needs to know. If you can calculate the gradients then and do backpropagation, then everything can be trained. But in this talk, we will focus on variational quantum classical algorithms. So we will have some quantum subroutine, and the classical part will be only for training this quantum subroutine. So we'll have some state preparation, some quantum subroutine, which depends on some classical data, circuit parameters, which are fed up into it using classical processing. Then you do measurement, you have measurement statistics, and then classical processing. In the classical processing, you do some post-processing of this data, and you have a classical optimizer, which will update the parameters theta for the quantum subroutine, and everything goes in a loop. And so examples I will describe today is variational quantum Eiger solver and quantum approximate optimization algorithm. So those can be used to obtain low energy solutions to minimize some cost functions. Another interesting thing is already mentioned quantum neural networks, but also quantum convolutional neural networks, which are quantum analogs of convolutional neural networks. So these things can be used for extraction of non-local features, for example, image processing. And finally, there is something which is called quantum generative models, which can be used to generate quantum distributions from the data. Regarding applications of variational quantum algorithms, there are many. And today we will focus on finding ground states, so the applications in quantum chemistry, and specifically in quantum chemistry. So they're like a classical variational quantum eigensolver, and also in a combinatorial optimization, specifically max cut problem. But there are many different ways you can use. For example, you can use the variational quantum Eigen solver not only to find ground states, but also as in the compilation. And also, for example, to solve systems of equations and things like that. So it's not like one algorithm has only one application, it can have many applications, or some variants of it can have. Yes. So what is the variational method in quantum mechanics? So consider a space of your quantum states, which is and a Hamiltonian. So Hamiltonian is an energy operator. So it tells you what are the energies of your states. So the states with well-defined energy I call the eigenstates of the Hamiltonian. So they are the eigenvalue, they are eigenvectors of the Hamiltonian with some specific value. Now, the goal, let's say here is to, let's say our goal is to find approximations of ground states and, well, let's forget about the cited states, about of the ground state. So each element from each quantum state, which is allowed, so which is in the Hilbert space of our system, can be decomposed into some combination, linear combination of these guys, which have well-defined energy. And if you calculate the expectation value of the Hamiltonian, which is this bra h cat, this is just the sum of squares of coefficients times the value of energy for the eigenstate with this coefficient. So you see this, it's at least the, so E0 is the smallest possible energy of your system, which is called the ground state. So it's at least the ground state times the normalization of your state. And variational principle tells you that for any ansatz, which is like some test quantum state, psi, if you calculate this expectation value of this Hamiltonian, so the expectation value of energy normalized, because in principle this psi may not be normalized, then it's at least equal to the ground state, so something we want to approximate. And it's equal to ground state if and only if this state is a ground state. So we can try to vary this psi, and every value we will get, we will know that our ground state energy, what we want to approximate, is smaller or equal than that. Yes, so varying psi, we can find upper bounds. And so we can, for example, use, but you know, going through all Hilbert space, all space of a quantum state is not feasible because it has a really bad exponential scaling with number of particles or another stuff. So you can just need to restrict to some subspace. So you will choose so-called the structure of your ansatz. So for example, you have some continuous parameters, and you will just vary these parameters, and according to some rule, you will generate continuous family of states you will test. You want to find a global minimum over this. If your ansatz is well found, so it has an overlap with the ground state, then you should be able to find a good solution. Well, yes. So that's another thing: how to find such ansatz, and also how to deal with local minima. So there are methods for it. So-called Ritz method or Hartley-Fock method can be used to address problems related with that. For example, to ensure that there is only one minimum and things like that. Okay, so now you know what the qubit is, and I just need something which is called Pauli gates. So Pauli gates are one of the let's say flavors of quantum gates, which are just rotations about x, y, and z axis in the block sphere about the angle which is pi. In fact, if you take tensor products of such Pauli gates, if you take, they will, so such a thing, for example, if you have two qubits and you take x tensor product y and x tensor product x and x tensor product z and all other combinations, this will form you a linear basis of all possible Hamiltonians you can have. So this is called a Pauli basis. Yes, and by taking tensor product, it means that the given basis, the given operator acts on a specific qubit. And as you know, in the circuit model, we have some initial quantum state, we have some unitary, and we have measurement. So after each measurement, we get some bit string, some classical information. So if we want to find the underlying probability distribution, so the probability which is connected to the state psi, we do not have access to the quantum state, yes? But we can approximate this underlying probability distribution related with the state by repeatedly measuring the counts for each bit string. We will check what are the counts, and we will get some histogram. So this histogram which will approximate the probability distribution. And now, what is the variational circuit? So a variational circuit is just a quantum circuit which has gates which depend on some parameters, say continuously. So here is some example. I mean, I do not specify how these gates depend on given parameter by some formula, but I specify which gate depends on what parameter. Yes. And after this variational circuit, you want to convert it to classical information. You do some measurement, and this measurement may not be in Z basis. Yes, okay. All in all, you can have just measurement in the Z basis, but you can realize measurements in all different bases by just applying additional rotations, which will change effectively the basis. So this way you can approximate for any Pauli string, you can approximate its value. So this way you can find the estimator for any energy operator or any observable, in fact, because you can find the expectation values for each bit for each Pauli string, which is the basis. Okay, so differential quantum circuits has been addressed, so I will just go quickly through it. So yes, so parameter shift has also been addressed. Let's go to variational quantum eigensolver. So sorry. So in variational quantum eigensolver, we have some parameterized quantum circuit which prepares quantum states, our ansatzes, our test functions, yes. Then we have expectation value estimation. So we need some, in particular, possibly we need some rotations to change the basis of our measurement to be able to approximate our expectation value of our energy. And then if you have the energy, yes, so we know we would like to minimize over the energy, so we can differentiate this whole circuit, calculate the gradient, use some gradient descent or whatever you would like to calculate new sets of thetas and feed it up to the energy to the parameterized quantum circuit so that our ansatz will change and everything will repeat again and again until we will be happy, let's say until we will reach convergence. I mean, the point, I mean, the question, it might not be, okay, so here's a problem. So you need to be able to efficiently find this expectation value, which may not be possible, but if Hamiltonian is sparse enough, then for sure it can be efficiently calculated. And also there are some tricks I will show you later how to do it in general. So now, how to encode our problem, real life problem, to this setting. So also how to choose ansatz, how to choose optimizer, and things like that. So we will focus on molecular simulations. So we have some particle, let's say it's H2 molecule or lithium LiH or whatever, or H2. And so we have some data about this molecule. Its geometry, so interatomic distances, charges, and multiplicities, spin multiplicities. We can write out the electronic Hamiltonian, which consists of one body and two body terms, and also the nuclear repulsion energy, ENN, and use some ansatz, for example, Hartree-Fock method, fix some basis for molecular orbital functions and use classical computer. So at this moment, we don't have any quantum computer used. We use classical computer to calculate these coefficients in the Hamiltonian, HPQ and GPQRS, using the information about calculating so-called 1 and 2 body integrals. So they depend on the geometry, on the structure of the molecule. But next, we need to feed it. We want our problem to be encoded to a quantum computer. So quantum computer uses qubits. It does not use electrons. It does computation on qubits or spin half particles. Mathematically, that's the same. So there are various kinds of mappings you can use to encode your electronic problem into qubit problem. For example, Jordan-Wigner, Brady-Kitaev, and parity mapping. So here is an example. So these A's and A daggers are creation and annihilation operators. So they form electron in some orbital denoted by its index. So for example, A2 annihilates, so destroys electron at orbital 2, molecular orbital 2. So you have some bunch of molecular orbitals, as you know, in the molecule, and that's it. And here is how this ATO should be mapped using Jordan-Wigner. So as you see, it's mapped to some sum of Pauli strings, to something which acts on qubits. So after this mapping, you will get qubits and Hamiltonian written in the language of qubits. So qubit Hamiltonian. Yeah, so this is how this mapping looks like pictorially, but let's, I think as we don't have time to discuss it in detail. So now how to choose this ansatz, how to choose your variational circuit. So the first way is to just use two local circuit with nodes, well, without, let's say, a structure. So it's heuristic to local something. You have some rotations, you have some C nodes. You not specify. You should specify what C nodes and what is the, like, say, interconnections of these C nodes inside this U C node block. And you can use, and this is like, let's say, some heuristic for choosing your ansatz. So preparing the state as the ansatz. But there are other ansatzes which are physically motivated. So, for example, they are based on coupled clusters. So, for example, you can have, for example, consider just excitations. So you have these red guys, and you consider excitations of these electrons. So you can, for example, consider excitations where only, well, the whole pair is excited, or only one guy is excited, or any combinations of that. And this gives you some different ansatzes, different structures of the circuit, and that's it. So, what in general in variational quantum circuits, what are the measures of the quality of the ansatz? So first of all, it should be as expressible as possible and has great entangling capability, which means it should be able to construct highly entangled states in general, that's the rule, and also highly expressible, So it means that you should be able to construct as many states as possible, yes? But of course, it does not, it's not like if these measures of quality are bigger, then it means that your circuit is better, because, for example, a more expressible circuit may have more depth or have more entangling gates. So there are some costs with each, related with each circuit of the implementation, which are circuit depth, number of parameters, number of entangling gates, and connectivity. Connectivity means that usually the topology in the of interconnections of 2-qubit gates in quantum computer is restricted. I mean, let's say always, it's safe to say. So you need to do some additional transpilation process to map your let's say abstract quantum circuit into the circuit which can be actually implemented on a device. So if you have large connectivity then of your ansatz, then there will be some large overhead related with that. So how can you get a good answers? You can use the knowledge about the problem, about its structure, about some perhaps classical solutions known, or things like that. You can use the knowledge about the hardware to just, push it to the limit. But you can also use an algorithm. So there are so-called adaptive methods of finding answers, adaptive QE, PACT, and things like that, where you are just specifying a list of operators, and this algorithm will try each operator in simple terms. Let's put it in simple terms. We could try each operator and check which one is the best according to some rule. And also you should utilize some symmetries. If the Hamiltonian has symmetries, you can use it to reduce number of qubits or things like that. You can freeze some orbitals or remove them because, for example, it seems reasonable to freeze core orbitals because electrons in the core should not contribute much to the total energy and things like that. So you have some tricks. And finally, okay, yes. So you can use them to reduce number of qubits, make your circuits simpler and things like that. Now, in terms of the optimizer, it also is about all variational quantum algorithms. The optimizer should require as few measurements as possible because quantum measurements are costly because you need quantum computer to do it. It should work well with noise because cost evaluation, so the approximation, approximation of this expectation value of the Hamiltonian, which is called the cost function, because you want to minimize over it, is a probabilistic process, as I tried to describe. So the optimizer will never get like totally ideal, even if it will use parameter shift rule. It is some probabilistic noise related with something. And also the problem about the noise that it might affect the training landscape. So the shape of your cost function. I will discuss it later, I guess. This NIBP and artifacts, probably. So, so an overview of this VQE algorithm is as follows. You have a molecule, you do a computation of these 1 and 2 body integrals to get Hartree-Fock. You map your problem to from fermions to qubits. Then you use some reductions, and then you have an optimizer. You optimize parameters of your ansatz, of your variational quantum circuit related to this ansatz, and you would like this to converge to some model. So applications can be not only to find a ground state or ground energies, but also find potential energy surfaces and to study molecular dynamics. So here is an example, like for very simple molecule, H2. So this is the energy of this molecule as a function of interatomic distance. Or actually, this energy cannot be distinguished from the exact energy, at least on this graph. At least on this plot. And also a fun fact is that this variational quantum algorithm, variational quantum eigensolver, was a topic of the recent IBM Quantum Challenge. I mean, not the IBM Africa Quantum Challenge, but the previous one, where the participants, where the task was to find the ground. It was the final task, where the participants had to find the ground state of LIH molecule up to some specified accuracy, and the score was number of CNOT gates, which were entangling gates, in the variational circuit. I mean, if you use different gates, for example, swap, they can always be converted into CNOT. So so that was the score. So of course, the lower number of CNOTs, the better. And the best possible score was 3 and was not expected by the authors. So they were surprised that participants were able to take it down to 3. Also, some participants got 1, but they were cheating. I mean, they were calculating the energy by a simulator and then, just try to cook up something which will just give spit out the correct state. So the smallest possible value was 3. So that's a fun thing about that. Now let's move to the second type of algorithm, which is quantum approximate optimization. So the QAOA is used for combinatorial optimization. So for example, an example of such a problem is that you consider bit strings, or all strings with n bits. So you have a cost function, and you want to find, say, minimum. Or if it's cost function, it's minimum. Of course, you can make it maximum. That doesn't. You can just add minus or whatever. Usually, this cost function is the sum of some clauses or some let's say some sub-functions. So the first step is to encode your problem using a Hamiltonian. So you want to find a Hamiltonian such that the eigenvalue, each of your problem instance will have as an eigenvalue the cost function value for this bit string. So for example, to understand it concretely, consider a max-cut problem. So a max-cut problem is a graph problem where you have some vertices and edges. So here is a weighted, let's say a weighted problem. So you have also weights corresponding to each edge. And your goal is to find a cut. So let's say you pick some edges and you say the cut goes through these, such that the value corresponding to this cut will be maximal possible. So the value of the cut will be the sum of these weights it goes through. So it's equivalent with to coloring. So you can just color vertices using, let's say, blue and yellow, and then you will say that if edge is connects guys with different colors, then it means a cut goes through this edge. So your score is the sum over of edges, the weight of the edge, 1 minus value of this edge. So the bit string has zeros and ones, and for example, 0 can be blue and 1 can be yellow or something like that. Yes. So if they are the same, then this 1 minus xy xj is always 0. So it does not contribute because there is no cut does not go through this edge, and if they are different, then it contributes the weight. So I hope it's clear. And now, if you have this classical cost function, you can use a Hamiltonian wij 1 minus Pauli z on ith qubit times Pauli z Pauli z on j cubit. I mean, it's not times; it has a tensor product which has two Paulis, one Pauli at ith spot and second Pauli at j spot. So why Pauli z? Because Pauli z has eigenvalues. Pauli z has eigenvalues, eigenvectors 0 and 1 with values 1 and minus 1. So that's basically how you can encode it. And in quantum scenario, you will need each qubit for each vertex. Yes, so this these arrows, for example, can, I think authors meant to indicate a spin because qubit is mathematically equivalent to a spin half particle. But let's say this arrow indicates a quantum state if it's 0 or 1. Yes. So now let's move further. So towards the algorithm. So the QAOA is motivated by so-called adiabatic theorem or adiabatic quantum computing in general. So in the adiabatic approach, you start from a ground state of so-called driver Hamiltonian. So the point is that the driver Hamiltonian is some Hamiltonian for which you can easily, what is the ground state, and you can easily prepare this ground state. So it can be anything. Here it's a plus state is an eigen state of x Pauli x gate, and this driver is just minus sum of these all Paulis acting on each qubit, one at each time. And then the whole thing in adiabatic theorem, it tells you that if you vary so you take a Hamiltonian, and your driver Hamiltonian, and you slowly deform it from the driver Hamiltonian to problem Hamiltonian. Yes, and you want to find the ground state of the problem Hamiltonian, because this is where is the solution to your problem. So you can slowly deform one Hamiltonian, the easy Hamiltonian, to the, let's say, more complicated Hamiltonian. I mean, it's not about the Hamiltonians. The point is that you can prepare the ground state of this first Hamiltonian, and you do not know the ground state of the second Hamiltonian. So you can just imagine that over time you slowly deform one Hamiltonian to another. And the adiabatic theorem tells you that if you will do it slowly enough, and slowly means it's 1 over delta squared, then your final state will be the ground state of HP. So it remains a ground state of this Hamiltonian through all of this process. And this delta is called the gap of the Hamiltonian, which is the difference between the lowest energy, the ground state, and the first excited state. Okay, so here this S is just, let's say, normalized time. So 0 is at t0 and 1 is at small t equals large t. Okay, so I think I don't have time to discuss it, but the point is that you can use so-called trotterization, which is a technique which enables you to divide your evolution from time 0 to time big T by some small steps, over which this Hamiltonian we are varying is approximately constant. And then you can apply some another theorem, and you will end up with this approximation above the point with peak. And you define in QAOA operator QP beta gamma, which resembles really this approximation of the let's say of using the continuous path, but it has some three parameters, beta and gamma. So you have a beta is just a tuple of p angles, and gamma is tuple of p angles as well. And you take a product of these operators. So first you have some evolution given by the driver Hamiltonian, specified by angle beta. Then you have a chunk which is given by the problem Hamiltonian, and you do it alternatively. Driver, problem, and the length of this evolution, the time of the evolution for each step, is specified by these three parameters. So here is how, what's the idea? So then you will get some, let's say, this orange is what you will get by a QAOA approximation, and this dashed is what you will get if you use adiabatic change of the Hamiltonian. So very slowly you will change one Hamiltonian to another one. So how QAOA works? So we start with the initial state, which is the ground state of the driver. So it's plus state on all qubits, and we apply our operator. So we need to specify this P. So this P is some parameter, which is just number of applications of this alternative applications of this driver and problem. Yes. And beta and gamma, as I said, they encode for each step, they encode for how long you will use evolution given by driver and for how long you will use evolution given by the problem. And now a variational part is that you can optimize over these three parameters, these times, let's say. So this beta gamma, ket beta gamma will be just the state you will get after applying this whole operator. So you will p times apply alternatively this driver evolution and problem evolution with time specified by this beta and gamma. And then you will have approximation ratio, which will be your score, your energy, the best possible energy you got, over the C max, which is some, let's say, theoretical value of your. And the nice thing about it is, due to adiabatic theorem, as p goes to infinity, you need to obtain optimal solutions. So ratio need to go to infinity. But of course, we do not want P to be large, because the larger the P, the greater the length of the depth of the circuit and a number of parameters. But it is some kind of a guarantee that asymptotically we need to get an optimal solution. So let me summarize what are these steps. You define a cost function which encodes your problem. So all in all, you want to find a quantum state for which the expectation value of HP is as let's say as large as possible. And the driver, or sometimes called mixer Hamiltonian, which is just a Hamiltonian for which ground state you can find. It's easy. You construct layers of these evolutions. So sorry, there should not be two betas, but there should be beta and gamma. Pick your P. So you will concatenate these layers according to the angles. Prepare the initial state, apply your operator, and classically optimize over these guys. So how to optimize? You need to know what is the value of your energy, but you can just measure your state beta gamma, ket beta gamma. You can measure it. You can do this. This HP Hamiltonian is just some sum of Pauli guys. I mean, I won't discuss the complexity of this procedure, but in principle, you can this big FP can be found from measuring, and you just do the use some gradient methods to parameterize. And finally, if you say you're all done with the optimization, then you measure your quantum state to get approximate solution of your problem, because this will be some quantum state which gives the best possible expectation value of your cost function. So there are some things which known about QAOA. So it's not like it's like can do everything or things like that. So I wanted to outline some limitations or problems right now at this part of the talk. You should be aware that these methods have limitations, and actually we do not really know much about what can they do and what they cannot do. But something is known. So what is known, for example? It's known that QAO cannot be efficiently, it's just a sample of what is known, yes, because we don't have time to discuss everything, but just to give you an idea. We, for example, know that this QAOA cannot be efficiently simulated by any classical computer, even when P equals 1. So you do just two operators. Another thing is that this performance can only improve, it's monotonous with this rate, let's say, with increasing P. So it's in contrary to some another algorithms like quantum algorithm with increasing time. There are, of course, problems for large P. The circuit is that deep, so it can be noise can overwhelm the signals. That's a classic thing. Another thing is that the performance of this algorithm on most problems is just a heuristic thing. We do not have any theoretical guarantees for the achievable rate. And also there are some recent works which show that some local classical algorithms that achieve or outperform the R, so the score, approximation ratio, of QAOA up to certain depth on max cut over some types of graphs. There are some types of graph, high get, things like that. And also another thing is that local classical algorithm which outperforms P equal 1 QAOA on max cut is known. The funny thing is that QAOA cannot outperform some classical algorithm, so-called Germans-Williamson algorithm for max cut for any value of P, which is kind of sad. And the last thing is that you can, maybe there's a question some people are asking. So for example, let's stick to this optimization on graphs. Can a local quantum algorithm So a local quantum algorithm is a constant depth algorithm that in each step only operates on neighboring vertices, obtain better result than those achievable by polynomial time classical algorithms, at least in some cases. And the answer is we don't know. So now let's move into another challenge. Another challenge is trainability. So the whole thing won't work if we cannot optimize over these parameters. But to get a gradient, you need to do some amount of sampling, or some amount of experiments, because you need to find the estimator for this gradient. And if the gradient is very small, you need to do a lot of experiments. You need to do at least 1 over of this gradient, and noise, and even statistical noise. Another thing is that if you take your grades at random, so you do random quantum circuit, then the gradient is very small, except for some small region. So the probability is arbitrarily close to 0 for a random point. And it turns out it grows exponentially with the number of qubits and number of parameters. So you won't have too much qubits and parameters. Of course, this algorithm cannot work if gradients vanish. And the Barren plateau is a situation where your gradients vanish exponentially fast with the problem size. So number of parameters, number of qubits. And if you have such a plateau, then it's a huge problem, because so here is a figure. So you are increasing number of parameters from, I don't know, remember, let's say from 6 to 20. And the blue one is for 6, the landscape of your cost function for 6. And the, let's say, orange is for 20. So you see it's becoming more and more, let's say, flat at the top. So if you will start far from the optimal solution, which is this point inside the point 0, with value 0, then if you will start somewhere far from this point, you will have flat landscape. You will have a plateau of your cost function. So your gradients will vanish, and you will have really difficult time to find a correct direction in which you need to go inside this hole, because everything is flat. So that's basically the idea. There are many papers about Barren plateau. It's like a hot research topic now. Problem is also that Barren plateaus can be induced by noise. So what are the ways to deal with noise-free Barren plateaus? So let's skip this noise-induced Barren plateaus. So you can initialize your parameters close enough to the infimum, but you do not know where. So that's not a great advice. Another approach is layer by layer training, where you see this Q array has layers. VQE also has layers of this variation circuit. So the idea is that to train one layer at a time and then go to another layers. And this way you will have less parameters, and hopefully you will have smaller, larger gradients. But this can also lead to some problems with so-called layer saturation, where it turns out it's not equivalent to train layer by layer and train everything everything at once. And you might have problem with reaching the solution or things like that. So it's not the best thing. And also, I mean, it's whole. I guess my impression is that it's constantly investigated. It's not known what is the final status for all of this. So this is like, let's say, some recent results. Also, another idea is to just reduce parameters. So just be frugal with your ansatz. Do not use too many parameters. Do not use too many qubits. Just use it for a given problem. Use the problem structure, things like that, and then maybe you will be good. You will be good. Of course, sometimes if you know a problem, then you know, for example, where more or less where should you start with your algorithm. But that's another topic. Now let's move to the efficiency. So as you know, we need to be able to calculate the cost function, which is just some of Pauli's things. If you have a Boolean plateau, then it leads to problems because we need to do many samples. So that's bad efficiency. But even without Boolean plateaus, the expectation value of these estimations needed to calculate this cost function may not be efficient. In particular, it's known in quantum chemistry, where number of different strings grows as 4 to the power of number of qubits. And there are some ways to, to go around it, like divide Pauli strings into qubit-wise commuting parts, because if you divide your H into parts which are commuting, then you can simultaneously measure. Optimize your sampling. So do not measure each Pauli string the same number of times, but measure it proportional to the square root of variance times the absolute value of the coefficient. It turns out it's the best, it gives the best results. And there are some more complicated ideas. I want just to give you, maybe for further reading, just give you some buzzwords. Is classical shadows, neural network tomography, and things like that. Now, in terms of the accuracy, the problem with hardware noise is that first it can slow down the training process. For example, it can just give you band plateaus and you're stuck, but not necessarily using bias mechanism. It can bias the landscape so that the noisy global optimum is no longer noise-free global optimum. So you have your ideal function. It has this minimum you want to reach, but due to the noise, your landscape changes and you land in some global minimum, but it's not the minimum. It does not match the minimum of your problem. And another thing is that it can affect the final value of the optimal cost. Of course, we can try to use quantum error mitigations to mitigate as small errors as possible. And another thing is noise resilience. So it turns out, and it's a good thing, that there is some inherent resilience to coherent noise. So it means that if you implement U theta plus some small error instead of U theta, then under some nice assumptions, your optimizer will be able to correct it, and you will be fine. Now, if your noise is incoherent, so for example, it's due to decoherence, random gate errors, or measurement errors, it is not known in general. But for example, it's known for VQE for quantum compiling that it has a very interesting thing which is called optimal parameter resilience, which means that global minima of the noisy cost function correspond to the global minima of the noise-free cost function, which is a good thing, but it's only for a subset of VQEs, which is only for quantum compiling. So I guess in general, as far as I know, it's not known. And here is a summary of this talk. So first, VQAs are a family of hybrid quantum classical algorithms utilizing variational quantum circuits and classical optimizers. I guess that's very clear from this talk. Another thing is that VQAs are considered as the most promising candidates for obtaining quantum advantage using MISQ. So quantum advantage is just, let's say, be able to do something practical better than classical algorithm. And VQAs also share a common structure outright to Antal. So a task is encoded into a parameterized cost function, evaluated via a quantum computer. And the classical optimizer trains the parameters. I mean, okay, the circuit was parameterized, but you, all in all, you do some measurements and post-processing to calculate this expectation value of cost functions. So equivalently, you can say that the cost function is parameterized, okay? And the topic is very fresh and there are many unanswered questions. And basically, we have no idea what we are doing. I mean, we don't have many guarantees and a lot of things are not clear. So there's plenty of work in this field. And I'm done. So I'll be happy to answer your questions at the moment.
Thanks, Oskar. It was a very nice presentation, of course. And yeah, variational quantum algorithms are very interesting indeed. There was a question asked by Abhishek in the last presentation, but I thought that it would be better to ask you in this presentation that, first of all, it is like you already explained that in quantum classical algorithms, we use the classical part to optimize the cost function, but why we do it? Like why we use the classical part in this particular subroutine? Is there any reason? Because we use the quantum part in parameterized circuit, like the parameterized circuit is quantum, but why we do optimization? It is like classical.
Could you repeat why we are using a classical cost function?
No, actually, why we're using the classical optimization to find the optimum value of the cost function? Is there any like maybe quantum way to do it, like fully quantum thing, you know, not classical quantum?
Well, I guess
because you wrote right in the third point that the classical optimizer trains the parameter.
So I mean, the way you are calculating gradients is in some sense quantum, right?
Yes.
Because it uses, you need to run quantum computer and some measurements to find these gradients. So
exactly, yes. Like it is a personal question of mine. Is there any, you know, like can we develop quantum optimizers? You know, like we use this Kobla method or Adam or maybe gradient-based method. What do you have any comment to say about this? Like quantum optimizer, you know.
Well, that's something I never thought about. And I'm
actually, this is just a random question. Yeah, just.
I guess you need to specify because if your problem is boils down to some classical function,
right?
And you just need to, and you have. I mean, in this setting, of course, it's useless because I mean, in this setting, just by definition, you're using classical optimizers. Of course, you can think of another settings where you would like to do something without this classical optimizer, but if your problem can be encoded in a classical function, then right. I don't see any reason to, and you can differentiate your quantum circuit via some operations, because this parameter shift rule uses quantum computer. Quantum computer does something, applies something, and measures, yes. Then I see no point in doing anything more. But maybe I'm short-sighted.
Okay, I mean that was enough. I mean, that was a nice explanation. Thanks.
So one quick question: QAOA or VQE, have we achieved quantum supremacy or quantum advantage already, Oskar?
I mean, it's hard to prove such things because, for example, QAOA, when it has been presented by Fari et al., it gave a solution which was better than any non-classical algorithm, yes? But in order to show that there is no such classical algorithm which can have better R, is usually very challenging to prove that you cannot. So it turned out that history shows they showed that QAOA does better than any known classical algorithm, but they didn't prove that there is no such algorithm, right? And up to my knowledge, it's still not known. In fact, after they presented the result, people came up with classical algorithm which had better results than QAOA. So it's often like you do something quantum better than any non-classical algorithm, and then people find out, for example, can be inspired by this algorithm, but not necessarily. And they find out classical stuff which does things better or polynomially equivalent. So as far as I know, it's not known. And even it's not known in the weaker version, let's say. So it was somewhere in my presentation. So it's a question. Can a local quantum algorithm do something better than classical algorithm, which is polynomial time? at least on some instances. So is there any, and the question is, we don't know. It's possible, I've seen a paper from this year, I guess, that it might be possible this polynomial local algorithms dominate pointwise the whole class of local quantum algorithms for these problems. It was, I think, graphical. I can send you a reference. I don't know at the moment what is I mean, it's a conjecture. I mean, it's not been proven, but they had some numerical evidence. So the short answer is no.
Okay, thanks a lot, Oskar.
Up to my knowledge.
Yeah, thanks for the answers. And do you think that you're going to share the slides or on the Discord channel?
Yes, sure.
Okay, so that will be fine, and you can share them. And if you have any questions, you can post them on the Discord channel. And yes, thank you once again, Oskar.
Thank you.
Okay, great, fantastic. Thanks, Oskar, once again. Thanks, Akash. So I think that now it's time for tutorials. So is Kavitha already with us? Yes, Kavitha is with us. So the first tutorial will be given by Kavitha Yogaraj, and it will be a tutorial about Qiskit QML. So Kavitha, if you are ready, I think we can start because we are just kind of the schedule a bit. So I think we lost, Kavitha is here. Okay, yes, great, fantastic. Great to see you, Kavitha. Okay, so maybe just a brief introduction. So Kavitha is his total work of experience of 10 years and currently is working as a quantum computational scientist at IBM. So yeah, as I said, she will give a tutorial about Qiskit QML. So Kavitha, if you're ready, the Zoom is yours and we can start. We cannot hear you now, I'm afraid. I think there might be some technical issues with your microphone. We still cannot hear you, unfortunately. Maybe you can try to just rejoin, or I don't know what's going on, because currently we cannot hear Kavitha.
Hi, Paul. Hi, Akash. Can you hear me now?
Yeah, perfect.
Okay, so rejoining helps. To save my bandwidth, I'm gonna turn off the video. And thanks for the nice introduction, Paul. And it was nice to hear everyone. All the speakers did such a great job. I'm going to share my desk here. Let me know when you can see the screen.
Yeah, we can see it. It's clear.
Okay, I'll go full mode. It's taking some time to get the presenter's view. Are you getting it?
No, actually.
Screen?
Yeah, now it's there, but it just exited.
Yeah, it is taking a lot of time to get it. So how is it okay? Good. Hi. So I am a computational scientist here at IBM. I work in IBM quantum consulting team. I became a Qiskit advocate 1.5 years ago. So this is how my journey is basically. So I became part of the community, and I'm trying to show like it's how I entered this job, because there are many LinkedIn posts that has been asking me like, how did you enter IBM Quantum, and then what is the roadmap? So I'm a software developer. Can I become can I do some developing in quantum computing? And there's a lot of students who wants to do collaborations on papers versus they want to learn on tutorials. So I would like to share my journey a bit before we go ahead with the tutorials. So this is how I actually first started with being a contributor in Qiskit community. So from there, I joined the student group and I started learning more on quantum computing, more on Qiskit. So with that, I started even attending a lot of quantum events. So the first event that I attended was Quantum Challenge 2019. So that is when I first attended the Quantum Challenge. And by then I did a couple tutorials and then did POC for an internal demo at IBM. So when I did that, I actually also got secured an internal job, transferred from what I was doing to quantum consulting. So that's how, by involving myself into Qiskit and learning about quantum computing and joining and making my presence in all the quantum events, that's how I actually became. I was not a Qiskit advocate then. I started preparing for Qiskit advocate exam. But at the same time, I transferred my internal IBM job to quantum computing. So this is my third year in IBM. And that was about 1.5 years ago when I moved to IBM quantum job. So now it's been 1.5 years. And as I moved here, I also applied for Qiskit advocate, and it was a test. And you know how to apply for Qiskit advocate now. So I did not become an intern, but this is a way forward. So I just diverted myself here. So this is a way forward for people who are students who wants to come into IBM Quantum, try to do internship. So when we join the student group, you can actually host guest speakers in your campus, and so do some funding on the quantum computing club as well, and build a network of like-minded people. And you can progress inside the community even further, like doing more contributions as such for Qiskit tutor, maybe Qiskit tutorial suggestion, or I also wrote a Qiskit HHL tutorial. So those combinations and contributions are a lot of open source contributions are welcome, right? So you can do this. After that, you can actually learn about quantum computing and learn about Qiskit. A lot of resources are there, and qiskit.org is where we actually a lot of free resources are available for us to learn, including the tutorials also. And then quantum events, once we join into Qiskit Slack, we have a lot of resources again there to join, and there's a big community who's actually uplifting everyone. Advocates are the strongest and most skilled Qiskit users among or researchers also, and many people that have presented here today are also Qiskit advocates. So you can also become a quantum intern at IBM by applying for quantum internships. So this is something that I wanted to share about how to enter IBM Quantum, whether it is quantum consulting or quantum research or Qiskit related activities in IBM. So this is the roadmap that we have seen from IBM, Jay Gambate, so who's the fellow of IBM and who's leading quantum here. We are in 2021, so we are hoping we get an eagle with 127 qubit system. I would like to talk about 4 layers here. So when we speak about I want to come to IBM Quantum and how to fetch a job in Quantum. Like there are 4 layers of jobs where you want to see yourself. Either you want to be a model developer or algorithm developer or kernel developers or the system developers of the whole IBM Quantum itself. Like these qubit machines, quantum computing machines are actually getting developed by quantum systems. And developing quantum circuits, coming up with that idea, and then implementing Qiskit runtime, coming up, those are all kernel developers. And after that kernel, then there is algorithm, like let's say quantum SVM algorithm or a quantum op flow algorithm or a neural network algorithm. So that development, and then application of that is into natural sciences or finance or optimization. So you just heard VQE with classical optimizers, and the question was quantum optimizers. So yeah, you can actually try to work in these areas and then come up with these ideas to implement. So basically there are, and model developers is where I work on application on the existing algorithm that's been discovered from algorithm developers. So model developers is at the top layer where I sit right today. And this is where I would be walking you guys to into the tutorial. So let's enter Qiskit ML tutorial. Before that, I would like to give a little details of what we're going to learn today. So we want to do quantum machine learning. And when we say quantum machine learning, people will ask, what is different from classical? So the data set is there in classical and data set here in quantum also. But a quantum machine learning algorithm cannot understand data like how a classical machine learning algorithm can understand. So we need to do encoding and then decoding of it. So encoding and decoding is there. So it sounds very simple, right? So we just add, let's say we just add at a hypothetical level, just 2 steps of encoding and decoding. Reading out the, decoding is basically reading out the measurements. So how does quantum think about encoding and decoding? It thinks it converts the encoding states into state preparation state and decoding it into measurements. And quantum machine algorithm itself has a bunch of unitary evolution of them. So here, in the right-hand side.
Kavitha, sorry for interrupting. Can you please go with the full screen? Because we cannot see the full screen because it's like we can see the slides and the pages, like the presentation mode. Yeah.
Okay. Got it?
It's not there yet. Maybe there is some issue going on.
Sharing is paused. Bring your shared window to the front. Oh, can you see this now?
It might be due to we have present viewer mode. We have.
Is it now visible? Because it looks like your screen is sharing. I'm getting your screen is sharing.
We have presenter mode on our screens.
You might have to share the presentation mode as well, I guess.
Okay. Give me a sec. I'm using 2 monitors and swapping across them.
It also might be due to because I don't know which screen were you sharing, or was it the only PowerPoint presentation? But maybe if it were PowerPoint presentation sharing only, it's better to share the screen, the specific screen.
So is it now visible? And let me go to presenter mode. How about now? I think I'm sharing screen.
Oh.
Yeah, it's perfect. Yeah.
Yes, it is
presentation.
I shared the whole desktop right now. So
great. Thank you.
Oh no, okay. So here we were where we were trying to see the encoding part has state preparation and reading out part has measurement. So until here, this sounds pretty cool, but then how this quantum device can classify stuff, right? So there is quantum device here, and square and circles and triangle is going into the quantum device, which we are calling it as quantum machine learning algorithm. And we want to get a prediction from the model. So I will not be touching the VQC or VQE part, as the previous speaker has covered this part. So let me say about kernel evaluation here. So the kernel actually takes the inner products of these two inputs, and it tries to predict that using quantum kernel method. And that is an implicit approach, what we are trying to do. So let's start with an example. Here we have X and here we have X data and then the feature map here. So the X is already a feature map which has been mapped, and here there is no way that we can actually differentiate between two classes, square class and the circle class. But the moment, which is, we can't separate it because it's impossible to separate by a linear decision boundary. So we will have to, the concentric circles which are just opposite to each other, or a concentric square, it's not easy. So the data point of two classes are arranged in such a way that in 2D plane, it cannot be separated, right? So now that let's take an example of feature map. I have taken this from Maria Schall's book, and then try to map it into different dimensions. The moment we map it into different dimensions, as you can see here, the data is at a higher dimension, and we can actually come up with a hyperplane that divides the data red in by squares, right? Right circles by squares. So that's what we are trying to do here in quantum kernel maps. So mapping, yeah, mapping this circles into different dimension than the circles, than the blue circles are. Red circles and the blue circles are getting mapped into different dimensions here. So the way we are doing is X is basically a function of phi, and then we are trying to actually come up with a, so you see here psi of xi and psi of xk. So this is where the kernel matrix starts happening here. So the calculations of inner product. So let's actually just define the kernel matrix called k of xi comma xk. And now the moment we actually maximize the distance between xi and xk, if the inner product is not equal to 1, that means they are different. If they are similar, then the inner product is equal to 1. So basically we are maximizing the distance with this kernel trick, and it differentiates the red circles by a blue circle. So this is what straightforward method calculation happens versus the kernel trick that we are trying to show here. So kernel matrix is the kernel trick that we are talking about. So kernel matrix, classically, what it does is polynomial kernel and a Gaussian kernel, it actually takes the exponential of it. So in polynomial kernel, it corresponds to feature vectors where all of the monomials of order D here and below are in each element would not be that very separated, because you can see here polynomial kernel, and what if the data here, so yellow or this red circle, if it's there here on the squares here, I mean, if red circles are there here, it's not a concentric circles, but it is circles are here also, then the polynomial function, polynomial kernel would not work in that case. So Gaussian kernels, right? Gaussian kernels, it is equal. It's actually a bit equivalent to infinite dimensions, but it contains only essential features. It will not extract all the features from the input feature sets. So that's the difference between Gaussian and then coming to quantum kernel now. So quantum kernel, it will help in classification of a boundary. It will help us in constructing without a conjecture too difficult to simulate classically. So which is not easy to it's not easy to simulate classically, and hence it can be only done it in quantum. And here is where we are trying to show there is a quantum advantage, which a classical machine learning algorithm which cannot separate two different classes. Let's talk about binary classification here. We can also do multi-class classification with quantum machine learning. But talking about binary classification here, if two classes cannot be, if two input data cannot be, binary classification cannot be done very accurately, then that is when quantum machine learning would be more advantageous. So if classical machine learning is already doing too good with 98% accuracy, then we can't expect quantum ML to actually do any better in that case. So what we're trying to say here is there is quantum advantage, and we are replacing the inner product of classical machine learning with the quantum state. And that quantum state creates a classification boundary in such a way that classical classification cannot do it. So with this, let's actually go to QSVM execution. I'm going to bring up my notebook. Let me know when you guys can see the screen.
Yeah, we can see a Git repository, right?
Yeah.
Okay.
So I'm going to walk you guys through quantum machine learning. So go to Qiskit.org here. So as this is a tutorial, are people gonna do with me the tutorial? Or you guys actually have enabled yourself to do it in IBM Quantum Labs, or you're having your own laptop set up with Qiskit and Conda environment? How is it going to happen now? Akash?
Pavel, do you have anything to say about this? So I think the participants are going to arrange themselves, because there I think I can see a yes. So they are arranging their own systems, and maybe you can go through yourself. Yeah.
Okay, then let's actually begin with the tutorial now. So if you go to Qiskit here, there's a lot of machine learning tutorials here. And today I'll be walking you guys through one of them, that is quantum kernel machine learning. So you can actually go download this tutorial Python notebook. Should I send this link here in the chat?
Yes, you can send the link. Yeah, it will be nice.
Okay. Okay, I have sent it. So if you can download into your quantum labs, let's go ahead. So let's actually talk about what is quantum kernel machine learning. Now that I spoke about and showed the difference between when the data is mapped in 2D versus polynomial dimensions versus higher dimensional space, right? So here when we come to quantum kernel machine learning, we need to understand what a machine learning is. It takes data patterns and study and tries to do the task, whether it is classification or clustering. For many data sets, the data point are better understood in higher dimensional space as we went through the PPT also. So to put the data into higher dimensional space, we need to do some features mapping. So that's called feature map. So here we come up with a kernel function of n-dimensional inputs. Let's consider X and J is basically a data point. With n dimension, n being the number of features. And we map n dimension to m dimension space here xi, f of xi comma f of xj denotes the dot product. So we will actually come up with a kernel matrix function, which is kij is equal to k of xi and k of xj. So with this, we are coming up with a quantum feature map, which is called psi of x. This x is basically a classical feature vector, which we are trying to map using using the quantum Hilbert space. And now after mapping, the f of xi xk is now mapped to psi of xi and xk, such that we have quantum kernel, which is in a higher dimensional space. And the paper we are referring to is, I'm sure everybody knows this paper, most of you guys. It's the supervised learning paper, which was published in 2018 in quantum physics. And it's been done by, mainly done by Otek and Antonio. Antonio came with this idea, and he also actually implemented with the proofs. And Kristen has done a lot of YouTube videos on quantum kernels also. So if you can actually go ahead and read it, it will be great mathematical description of each of it. Also, it's been done there. So now let's calculate a kernel matrix using a quantum feature map. And we will also use scikit-learn here. The reason being, quantum kernel machine learning, here we are actually only providing quantum kernel matrix, a pre-computed quantum kernel matrix. We will learn it, we will take that pre-computed kernel matrix and run it in a SVM algorithm of scikit-learn. Okay. So the tutorials are here, coming back. So now we will import matplotlib just for the sake of plotting and showing the results, right? And NumPy is for, we are actually using the data here and converting the data points into NumPy arrays here. And we are importing SVC, support vector classifier, from support vector machines algorithm module. And then spectral clustering is what we're going to use for clustering, but let's talk about clustering a little later. And we are just importing some more metrics. And here is where the Qiskit stuff comes, right? So basic air or air is a package that we are using from Qiskit for simulation purposes. And we are using ZZ feature map. ZZ feature map, we'll talk about it. It's basically a feature map trying to map data into higher dimensional. And quantum instance is for building a quantum instance with a backend. The backend here is basically basic air simulation. And then we have a couple algorithms. One is QSVC and the other is quantum kernel from kernel algorithm, and some data set here. So this data set could be a Kegel's data set or any data set that you want to run it on, but some data massaging needs to happen. So let's come to classification. So here in this paper, what they say is they've also used ad hoc data set, and they've actually proved quantum advantage here in this paper. Hence, we are referring to that paper again. And we are using support vector machine from scikit-learn. So you're all well aware of this, I hope.
So could you please like say a few words about the support vector machine? Maybe they are not like the definition or something.
Oh yeah, sure. So what is support vector machine? It's basically a bunch of algorithms is there in support vector machine, which will make predictions of a data that's been given. And that data could be classification data to classify data. Okay, and let me go through the examples here. So support vector classifier, let's talk about it. So here the data is in blue play. There's 3 classes here. And using a linear kernel, RBF, radial bias kernel. So they're using different types of kernel, and they're trying to actually differentiate classes, differentiate the input data set into multiple classes here, right? It's a blue class, orange class, and a gray class. So the gray data points of gray circle should only come in gray data point, gray class, right? But orange class is also in here, which means that the data is not being very well classified. So what does this support vector, it actually, the advantage of the support vector machines has their right away status, effective in higher dimensional spaces. When we come to linear kernels and polynomial kernels, we actually looked at it right here in our PPT. We looked at it that in linear decision boundary, it is impossible to separate the data in X. X is a linear decision boundary, which is impossible there. So now let's come to polynomial boundary. Yes, it's now possible to differentiate, but what if we have another circle class in the square box here, near the square box somewhere? So then it also becomes not linearly or polynomially differentiable, or the decision boundary of it is not possible. So they also say here in support vector machines that higher dimensional spaces, it actually works better. And this support vector machines actually work with supervised learning. When it comes to clustering, SVM, it's a supervising learning method, and hence it can be used in classification, regression, and outlier detection or anomaly detection as well. Here, it uses kernel functions. So you can now think why we are using SVM for quantum kernels. The versatility of SVM is you can give a kernel function, and that kernel function can be pre-computed kernel function, or it can be a callable kernel function. So when you give a kernel function which is already pre-computed or already callable, then SVM can actually work on those kernel functions. This is the main advantage of SVM basically. So can I move from SVM?
Yeah, that was a very nice introduction. Thanks. Please move.
Yeah. So now that we know a bit about SVM, we are using SVC, which is specifically classification algorithm. SVR is for regression. We can also do SVR also on regression also on this quantum kernel tutorial. You can go extend it. We are using ad hoc data given by Qiskit. Given by Qiskit, we are taking from quantum machine learning algorithms directly. So here I'm in the GitHub right now. If you go to data sets, there are a bunch of data sets that I wanted to show. Breast cancer data set, ad hoc data set are the two data sets that we can actually, that I have run experiments with. But this is code here. So we are working with ad hoc data set. Okay. So in this ad hoc data set, we are actually saying, well, let's only take train size of only 2 dimensions data, which means only 2 features we are trying to take. And then ad hoc dimension, we are giving it as 2. And then we are telling that we want ad hoc data of 20 size. And then I'm gonna tell why we have 40 size here. I'm going to get the data. Anybody has issues in importing stuff? Akash, I'm not seeing the chat. You can actually speak to me as you see any questionnaires on running this tutorial.
Yes, I haven't seen any questions, so maybe you can go ahead. Yeah. Okay,
good. So we are calling this ad hoc data, passing a training size of 20 and test size of just 5. And one hot encoding, we don't want one hot encoding. One hot encoding will actually create create two labels, 2 destination classes. So we don't want, and include the sample also, we are trying to tell. So after we are getting the train features. So we are dividing the data into train, test, and train labels and test labels. So let's see how our training data looks like. Training data is a NumPy array with just 2 features here, 1 row and one column and another column. And the length is basically 40. We just looked at it. I asked the training size to be 20 and I got 40 length. So I'm trying to rerun it again. Let me play around a bit with ad hoc dimension if I'm using just. We need to test this, why we are getting the size has 40 when we are asking for 20. However, moving forward, so I'm just trying to check the types of arrays here that we have got. I mean, it's an NumPy array, but I just am trying to show here. Let's keep some time running. Okay, train size is 40 and then test size is 40. And then all of the train features and test features, all of them are NumPy arrays. Let's see how the test label looks like. So it's a binary classification, 0 and 1. Yeah. So we will try to map the data into just a plane here on a plot and try to show the data set, how it looks like. So data is here on blue class and on a red class. So red points are supposed to be red, dark points are supposed to be a test data. Red halo points, halo circles are basically a train data. Same as with the halo points are train, and then the test points are solid in terms of squares as well. So it is pretty straightforward data to get good accuracy, because we don't see a data point saying that red versus blue, right? Or it's not mixed up. So we have pretty much good data set. So this is about the data set. Any questions on the data set before we move on to quantum part?
Yeah, maybe I would like to know that what is the data set actually representing? It is just random data set, or
it's ad hoc data set is completely random.
Okay, I see.
So even in the Qiskit machine learning, you can go read about it. When it comes to breast cancer data set, it's about predicting the breast cancer. So that's what this data set is about. But ad hoc data set is completely ad hoc, and then you can see that this data set is much better distinguished, basically.
Exactly, yes.
Mm-hmm.
Okay, please go ahead. Yeah.
Yeah, so there is a multiplication happening here in the label train. It actually multiplies it into 2 before we get it. That's why we are getting 40 instead of 20. We are getting 40. We were asking here to give a training size of 20, but it is giving us 40. We need to check inside this what is happening. I think there's a multiplication of train size and the test size, and then it is dividing and it is sending the data out. Anyway, so coming back here, test labels are all zeros and ones, and we actually just map the data for classification. Let's talk about feature maps, right? So what are feature maps? We spoke about in the PowerPoint presentation, we spoke about the data needs to be mapped. So now that we have data, which is good enough, we need to do that encoding. To do that encoding, in machine learning, what does the encoding mean? It is trying to represent the input data into richer representation. And then so that the estimator can understand that very well. What does that estimator? Estimator is basically any kernels which is using it. So now we are calling an estimator as a quantum kernel estimator. From now on, when we are dealing with quantum kernel machine learning, the kernel of a SVC algorithm, as we saw here in support vector classifiers, right? Linear kernel is an estimator. Here, linear SVC, it becomes a linear SVC. And the RBF kernel is basically another estimator, which becomes a polynomial estimator, basically, right? So here, when it comes to quantum, this is a quantum kernel estimator. To get better classification, we are using SVM because SVM said that it works better in higher dimensional spaces, right? So feature maps are typically not a linear maps, it is non-linear maps trying to map the data into higher dimensional data. So trying to map the data into higher dimensional data. So example, when you have a 2D image versus a 3D image, then it is much better in looking, isn't it? So the data now gets mapped to higher dimensional space by having a separate hyperplane. So that is basically feature map data encoding. Think about feature map has data encoding part, which is now easy to distinguish. So why we are using feature maps here to, we connect feature maps into kernel function, so that this kernel, when using this particular feature map, kernels get the data which is encoded into a new feature space. Once the data is encoded into new feature space, then the kernels can play with the psi of xi and xj. So if two items are similar, xi and xj, if they both are similar, the inner product is close to 1. The one of the prime example of SVM is basically estimator framework that we were just talking about, kernel estimator. So kernel estimator is basically implicit feature mapping that we saw here in this internet. We saw this. This is an implicit approach with quantum kernels, right? So SVM is suiting better for it, for the implicit approach, and it also because it works with higher dimensional data, and it also said in the SVM website, right? It also said that it can work with a callable kernel function. So that is the reason why these are the main 3 points why we are using SVM for it. And then coming to kernel function, we have seen a kernel trick that k of psi of xi and xj is now a kernel trick which helps the base vectors get transformed to a feature space, which explicitly is now transformed to a different feature vector altogether. So the data is now at a different space, basically, and that is what is called as a kernel trick. Now building a kernel itself is a kernel trick there. So quantum feature maps are basically the main components of QML algorithms here. Even quantum kernel estimation also is one of the main component this is another algorithm. So there could be variety of estimators, and one of them is QSVM quantum kernel, variational quantum kernels, or quantum neural networks also. So when we say quantum classification, it's just not quantum kernel classification. So I just added this point that it can be VQC, variational quantum circuits, or quantum neural networks also. So we can, just like how we can do neural network classifiers, normal neural network classifiers like classical ones to classify data, and also deep neural networks also can work on classification of data. Even SVC can work on classification of data. So just like that, we have many different forms in quantum, variational quantum algorithms, quantum neural networks, or kernel-based estimators like QSVM with quantum kernels, right? So there was a quantum advantage that was proposed by Monte paper in 2021. I think I have that open somewhere. Is this that? No, so I don't have that open, sorry. So in that paper, it's actually mentioned that a problem that is impracticable to solve in classical methods are the same problem that can help get a quantum advantage. So if we can, in that examples, if we can actually divide the data here classically, then let's not do it in quantum. If the data is not able to be divided in classical, that is when Manto is suggesting to go with quantum, and then you can get a quantum advantage, because that particular data set had a problem of not able to differentiate between classical data into quantum data. So classical data into different classes, right? So that classical data has been taken, which was not able to be solved, and then map it into higher dimensional spaces using quantum states, quantum kernel methods here, and then do it. A step in this direction is to find such a quantum feature map for given input data that is not easy to compute in classical form. That is when we need higher model. That's when we need higher performance. That's when we need higher dimensional data space. That's when we want the input data to be represented into higher dimensional space. And the data patterns now are complex in nature, which cannot be represented in a linear dimension or in a polynomial dimensions, that is when you need quantum kernel methods to explore data into higher dimensional space, because the input data itself is very complex. So that's what this paper talks about. Otek and then Antonio's paper talks about that when the data is mapped into higher dimensional spaces, that's when we can take the advantage of the class methods here. So that's what this paper talks about. I wanted to just show a mapping of the data here in this. Okay. So in this notebook, what I'm trying to present is try to show the data that is mapped using ZZ feature map, which also extends Z feature map, which is basically ZZ feature map can work with 2-qubit entangled states. Z feature map can work with 1 qubit also. So when we say 2-qubit entangled states, that means ZZ rotation has been applied on our gate, and then ZZFM, it becomes a conjecture to be that cannot be simulated in classical. But ZFM, which is basically Z feature map, can be simulated in classical, because we are just using 1-qubit machine, 1 qubits there, and then it is possible to represent it in classical. But ZZFM is a feature map where the data, input data gets mapped to a higher dimensional space, cannot be represented in classical. So that's why I'm trying to show with ZZFM, which cannot be represented classically. So furthermore, the entangle operation, it does not create a product state also. ZZ feature map does not create a product state, but rather it creates a kernel state which cannot be represented, quantum state which cannot be represented in classical machine. So here with quantum kernels are also very well explained in one of the article of IBM, and you can also go read about it in Qiskit quantum kernels also. Now I'm going to use ZZ feature map, and feature dimension is one of the parameters that we need to associate it with the number of dimensions. And here ad hoc dimensions we had given 2. Right, ad hoc dimensions we had given 2, which means it's 2 array, 2 columns. So we are saying it's just 2 columns, 2 features. Repetitions are 2. So we want to repeat this test with ZZ feature map 2 times. And entanglement, we can do linear entanglement or full entanglement. So I'm just doing linear entanglement. So entanglement helps us in overfitting or underfitting, try to tune QML into overfitting or underfitting, which is a classical ML's way of understanding. And quantum instance gives us a backend to run our algorithm in. So here we are using a Quasum simulator. We can also use a state vector simulator. So because I'm using Quasum simulator, I'm giving 1024 number of shots. And the seed is basically one, I think some number I have given. Yeah, 1, 2, 3, 4, 5, some number actually. So transpiler seed is trying to shrink the circuits into basic states, right? So then I create a kernel using quantum kernel class, trying to give a feature map, which we just created with ZZ feature map. So ZZ feature map encodes the given data into higher dimensional space. We just got that. And then we are giving a quantum instance for a quantum kernel to run using a simulator. This simulator can be even a quantum device. So you can even call a quantum device and then send it here for a quantum instance. And we have ad hoc kernel. Now this ad hoc kernel is nothing but a quantum kernel. We can call this as an estimator. So we will now use scikit-learn's SVC algorithm. And SVC said we can define a custom kernel actually. So what does it mean? You can define your own kernels by either giving a kernel function in Python or pre-computed matrix. So a kernel function means you can give a callable kernel or already pre-computed kernel matrix. Okay, so here we are going to do 2 of these exercises. So here we have ad hoc kernel, which is here, and we are trying to do a evaluate on that. And I'm going to go to this quantum kernel class of GitHub. So this quantum kernel is a class here, and here it is taking a feature map, which is basically ZZ feature map or any quantum circuit. Here we, but before going to that, let's actually show you guys a feature map, how it looks like. So let's say I'm first building a ad hoc feature map. I built that. We can actually draw that feature map. So this is how the feature map looks like. We are just using 2 qubits here, right? Because 2 dimensions, each dimension represents 1 qubit here. So the data is, data needs, as many dimensions are there, has that many qubits we need basically. So this is the quantum circuit we get. So now the data is encoded into higher dimensional space using quantum states here. So now let's go back to the quantum kernel class. It needs the quantum circuit, the feature map, and batch size. This is only for running the experiment in quantum devices. It needs quantum instance, which actually considers quantum backend also. So with that, we are actually trying to get a quantum kernel. I want to go to one function, which is evaluate. So this is a function that I'm interested in showing mainly here. So evaluate is a function that what we are calling on top of quantum kernel that we get from this quantum kernel class, right? So this particular evaluate function takes 2 vectors, x vector and a y vector. X vector is basically the x data, what you send. Y vector is basically the y labels, what you are sending. So it could be 1-dimensional or 2-dimensional array. So it is only working with arrays here. So you have to convert your data sets, a pandas data frame into a 2-dimensional arrays when you're working with. And it returns a matrix basically. So evaluate method returns a matrix here. So this is the main point. What we want to send here, a kernel is actually receiving ad hoc kernel.evaluate, which is receiving a kernel matrix. According to this, it is said that either by giving a kernel has a Python function or by pre-computing the matrix. So here we are passing the kernel matrix to this kernel. And now that train features and train labels, features are X data, labels are Y basically, right? So you saw how those X and Y look like. Labels are nothing but zeros and ones, and features are nothing but 2 columns that you saw. You're fitting an algorithm. Once you fit, what happens is SVC calls a kernel, and this ad hoc kernel will get this data. So you're not able to see that here because we are not passing stuff like this, ad hoc kernel, and then pass X comma Y. So we are not passing like this because it's an implicit call. So the moment you're calling evaluate function, on an SVC algorithm, the moment svc.fit happens, it's actually getting the data X and Y, which is here X and the labels Y. So we will just try to see this. I don't know. Okay, I need to run this. This ad hoc SVC, if you see, it is a type of SVC basically. SVC is a scikit-learn package, right? Scikit-learn algorithm, which is now bound to run on quantum kernel evaluate method, right? So this is coming from Qiskit machine learning. So it is now completely clear that we are using the quantum kernel, and SVC is not throwing us any error, and it can work with QM. Now it can work with quantum kernel here, right? So now we can call SVC uses a quantum kernel estimator. So now that it uses a quantum kernel estimator, we are also fitting that. We are also scoring that. We are fitting on the training data. We are scoring on the test data. And you already saw that this is such a good data. So there's no mismapping happened here at all. So this red square box blue square box was supposed to be in blue, and all the training data, which is in halo square, is also in the blue box itself. And you're getting almost 100%. You're getting almost 100% result. It takes a bit of time to get results from quantum kernel, and especially we are using Quasum simulator. It takes even more time. If it is state vector simulator, it takes lesser time because it's an exact simulator, right? Quasum actually has it's a noisy simulator. So now, this is
I actually got like the callable kernel classification test code 1 year. That's exactly the same thing. So what does it mean actually?
Repeat your question.
Yeah, like the test score. What is this test score? I mean, how it is evaluated?
This score method is basically coming out from SVC method, because we are extrapolating SVC class here. So let's actually go to SVC with custom kernel. See, this guy, this example, not this guy, has a kernel which is just a Python function with just an inner product of NumPy inner product of 2 data points here, right? So this is a callable kernel. So this kernel SVC, this is also coming from SVM, support vector machines only, right? So this kernel is also calling this Python function, which is a callable kernel. So just think that this particular function, let me open a text. So just think that this is not a my kernel, but this is a evaluate method. Evaluate method of from quantum kernel class. So I'm just putting it as qk.evaluate, just so that or maybe just evaluate and it is in a qk class, right? QK class. So just putting it, I'm just not doing so very well here. So think about it's a definition in a class quantum kernel. But what we are using here is an SVC. SVC is also another class, right? SVC is also another class which actually has a definition of fit and a definition of score.
Okay, so maybe I will look for that, and maybe you can go ahead.
So definition of score. So you can actually go look at it. Yeah, I mean right away, right here itself, right? So there's a lot of functions. So these are just attributes. So there is a function called score. Yeah. So this score actually can take X and Y value and return the accuracy score of your test data. So this is a function that is there in SVC directly. So we are actually looking at SVC now. We are not looking at quantum methods. The moment we pass this ad hoc kernel, quantum is done here. So the quantum kernel is being evaluated and it's been sent. So the moment fit method comes, it again is using kernel. So it is again using quantum kernel in between that. So, so coming to this one. So every time a fit method is called, fit calls quantum kernel. Quantum kernel calls evaluate method. Right? Evaluate method. And then when you call a score calls again quantum kernel. And that quantum kernel actually calls the evaluate method again. So when we just passed a kernel with a quantum kernel evaluate, the job of it is basically is not done right away. When it is fitting, it will be using a quantum kernel. When it is scoring, it will be using a quantum kernel. And this callable kernel function test, the one that you asked, it is just printing purposes, right? This is my accuracy score. That's it. Simply, this is my accuracy score. Oh, I should have just run this part. Anyway, here we have just shown the example of how the callable function works, right? We can also pre-compute. I'm going to show an example of how to do a pre-computation before and then use the same fitting and scoring methodology. There are cases where you can't actually do an evaluation when, let's say, you have a web service and you're actually using quantum there, and then it took quite a bit of time, right? 2 minutes just for 40 records that we had. And reality is not having 40 records. We will be having more records, in which case you can't really get done your job there. So you can actually pre-compute the matrix and keep it like this. So here we are evaluating X vectors and then the Y vectors. So, and then after evaluation, we have ad hoc matrix, train and test data. And we are actually using SVC and we are telling the kernel is already pre-computed. This is basically a parameter. When it is pre-computed, we are just passing a matrix, train matrix with a train label, test matrix with a test label here. And then after we actually score the SVC algorithm with a SVC score method with the matrix, kernel matrix, which is already pre-computed, that is when we can also print how is our matrix algorithm using some matrix matplotlib plotting methods. And we just have 0 to 10 records. And we had 40 records for test data, train data, and then only 10 records for test data. So the data here is mapped into matrix, but here we can't get an insight right away how the data is being mapped and how the differentiation happens. So this is just another same thing.
So Kavitha, for binary class classification, this quantum kernel definitely is giving better advantage, but will it do the same for multi-class classification as well?
I didn't get it, Akash. Repeat it. You're asking.
I am asking that the paper that you shared, where so it talks about binary class classification and quantum advantage using quantum kernel for a binary class classification problem, right? Which is this tutorial also demonstrating. So will it work for multi-class classification as well? Let's say I have to cluster, I have to classify in, let's say, 5, 10 different.
Yes. So there is a Qiskit tutorial on all pairs. You can use it for a K-way classification actually. So you can do QSVM with a multi-class classification, and it is also there in the machine learning tutorials.
But does it use quantum kernel again as a?
It uses quantum kernels itself, but it uses all pairs to actually. It's a multi-class extension from a normal scikit-learn, right? So it uses all pairs, and it's been implemented in Qiskit also to do multi-class classification. But however, in this tutorial, they have done PCA to reduce the dimensions. And you can see that multi-class extension has been used, and we are using ZZ feature map still with a linear entanglement. And then QSVM has been used with all pair extension. So this is the example of what you just asked. We have 3 different class A, B, and C, and the prediction is also such that multi-class classification can also work with this.
Okay, Kavitha. Yeah, but quantum advantage is something which is proven for this multi-class classification as well.
Only if the data cannot be classified into by classical machine learning.
Sorry for interruption. Maybe we can move the questions at the end. It will be better because we are on a flow. So.
Yeah, sure.
Yeah. Please.
So, so here we are actually just trying to show a GIF of the classification overall. So we are now ending with the classification. Before entering clustering, I can actually take classification questions. We have another 30-40 minutes to cover clustering.
Okay, that's great. I mean, please ask questions. This is fine. So yeah, if there are no questions, maybe we can continue, and maybe somebody will come up with questions and ask you on this question.
Yeah, sure, definitely. So guys, we can actually do ZZ feature map encoding, or we can do ZFM also. We can do poly feature maps. So we can explore with different feature maps and experiment for ourselves and use different data sets also. And one of those applications would be for fraud detection or for binary classification or multi-class classification, right? You can take this example and then try to simulate with any other data. It's just that your data needs to be converted into NumPy array. So there we are with classification. Now let's enter clustering part.
Hello, ma'am.
Yes.
Ma'am, I have one question. For data encoding, if we will go for angle encoding method, then like for 2-dimensional data, what we can expect in the output? It will be just amplitude or some kind of probability measure?
So what does angle encoding gives us, right? So there are many possible ways that we can encode the data in, right? Angle encoding is also one possible way. So we can expect we see the raw amplitude. So with angle encoding, we will be not doing tensor. We would be just doing the tensor product encoding, which requires n qubits, and it also represents into n-dimensional data. But it is cheaper and it is not that complex, right? So I don't think we would get benefit by doing angle encoding.
But it will be the angle with like rotation of that data point, whatever, like in case of qubit, one single qubit, we are getting 3 axes, right? So within the Hilbert space, however you are rotating your data point, that angle will be measured, or as a cosine angle and sine angle, your features, integer value will be placed. That is what my question is. Like, for example, my vector dimension will be like 2-dimension vector is there, and with value 5 and 4, right? Horizontal 5 and 4. So how I will encode this particular thing? What will be the result of that? Like in the back end, the process or computations, those are happening. We are not aware of this, no? So I just wanted to know that I'm aware with the theory, but what as an angle will be input? That is what my question is.
So the angle of your input data will what be taken. Let's say the angle encoding is done on rotation X and rotation Y axis. So, and then the rotation actually happens on your input data, right? Let's say input data is X, Y, we considered your input data is A. So rotation along A, A for X axis and Y axis is what will happen in angle encoding.
So that rotated angle only will be the measure, right?
Rotated angle, the angle measured of a particular input data is the measure that is considered in angle encoding. Yes.
Yeah. Thank you so much, ma'am.
So we can define to use which rotation we want, whether x-axis rotation or y-axis rotation also.
That we are giving through this, no, with these standard forms. But like if we want to show our contribution in this all things, then already everything is available. Then that is the question whenever we are going for QML algorithms, that how we can show our contribution. So if we will go for big data, it is very, very difficult to plot the data with all these methods. So if I will train on this particular model around 2 lakhs of records, then it will take so much of time. Then how we can justify this particular model is efficient than classical model?
So first of all, we will not be able to work with a lot of data. So the maximum that I have tested is with 5,000 records and about 22 features.
Yeah, so, otherwise kernel will get stopped if we will be passing more number of records. I tested that also, but it will not pick up the data. It will stop working.
Correct. Because the higher dimensional space, when it is mapping, so what we need for that is a better quantum volume. We have 128 has a quantum volume today, and we want a better quantum volume and then more qubit system. So today we have a 65 qubit machine, IBM Q Manhattan, but quantum volume of it is, I think it is 32. I need to check actually. So, but IBM Q Kolkata and Mumbai, they're all 128 volume, but the number of qubits is 27 qubits machine, that is.
No, but if limited features in terms of if 20 to 30 number of features also I will consider, then also kernel will stop working. Like 64 qubit is a big space, right? In that, if I will be utilizing on around 10 qubit of like 10 qubit size, I will take, and on that, with the help of amplitude encoding, if we will try to encode our data, then also it will fail. So what is the solution for it?
So solution is more power to quantum machines today. So see, we are taking a baby step in quantum, right? I mean, we are able to solve whatever from classical ML to we are coming to quantum ML, and we are trying to prove things can be done in quantum, and there's more advantageous here. Things could not be solved in classical is what we are trying to solve in quantum. So we are not trying to say even classical ML can actually simulate 2 billion rows also, right? It's not difficult in classical. You can do big data and then try to simulate all of it in parallel models and do it.
Ma'am, there is one gap in case of classical SVM and SVM. That biggest gap is nothing but classical SVM will fail again on big data set. Most of the points are getting misclassified. So that the priority of choosing this technology will be, we can go ahead with superposition method and we can pass our data in that superposition mechanism. But here also I tried, but I'm not getting results for that. Big data like SVM on big data set. That is the problem.
So you have tried SVM on big data set?
Yes, I tried, but their kernel is getting failed. If data set is unbalanced, like I have been taken one data set of credit card fault. In that data set is very much unbalanced. So that in that case it will work, but for training case and all, it will not take much of the data. Kernel is getting hanged. This
what is the size of your data set, Mukta?
It was around 3 lakhs. 3 lakhs records were there.
No. So please make your big data a lot of parallel models, and then don't work more than 5,000 rows at a time.
Okay.
So 3 lakhs, I mean, there's no way that we can actually have any result.
Then I partition the data, and in 1,000, 2,000 partition it is going.
So that 1,000, 2,000 is easy. 5,000 also it will work.
Yeah, but that too again also taking so much of time.
So you are suggesting model parallelism for implementing the machine learning algorithms?
The thing is, if you want to simulate, let's say just talk about 100,000 records, which is 1 lakh, right? So if you want to just simulate 100,000 records, today QML cannot take a lot of records. So I'm talking records in a sense rows, right? So when it becomes big data is when it is too many rows. So in big data, what we do is basically streamline data into many models, many same models, right? So you train it and then start simulating with many models of the same type. So that's what I'm trying to say here. And because we can't simulate more than 5,000 rows in our QML in quantum kernel methods. So what we can do, 20 models simulating the same different 5,000 records, and then build 20 such models and then ensemble them. And then you have a final model basically with ensembling all of those 100,000 records.
How to integrate them all?
Okay, in classical ML, you can actually Google for ensembling classical models. That we can do a lot of models can be ensembled into one model finally. So the method that I have used successfully is build 20 such models for 100,000 records. Each 100,000 records, each model taking 5,000 records, then ensemble them together, and then you have a final model which actually can now work on 100,000 records, right?
Okay.
So pictorially, I mean, its ensembling model is basically taking 100,000 records, dividing it into 80,000 training and 20,000 testing, and then 80,000 on 20 or 18 models, something like that.
Then where is the scope for exponential speed up, ma'am? How we can prove the speed up of algorithm?
So the speed up of algorithm comes in. So we are not saying that quantum algorithms are faster than classical. Only in cases where classical cannot solve, that is where quantum is high. It can perform better. That's what we are saying in those papers also, right?
But then if it is a feature vector of, let's say, millions of dimensions, then that is exactly where the quantum kernel might be having a better advantage as compared to classical, right? So
millions of dimensions means millions of features you're talking about.
Millions of features, yeah, feature vectors, yeah, correct, yes.
Feature space.
Feature space,
feature space. Feature vector we can take, it is depends upon like how many total number of columns we are having into the data set. As many as we can take, but then further processing also is expected from like how we can optimize that circuit.
Right.
I'm trying for that, but it is not happening.
So what are you trying to optimize here? The quantum circuit that you get it is from different types of feature maps when you're using QKE method.
Yes.
If you're using quantum kernels with or without torch connector, then you're working with neural network classifier class from QML package.
Correct. Like now I got the solution from you that we can partition our data, then we have to integrate it. But most of the papers are saying we are getting speed up with the help of these machines.
So detailedly read the paper and they say exactly how and why they are getting the speed up. there is a recent paper from what was her name?
Amira's paper and all, I have studied everything, but everything in their paper also common. Like Maria Schultz's paper and all are having same philosophy.
Yeah. So there was from Jennifer, there was a paper from Jennifer on covariant kernels. So covariant kernels, they say covariant kernels actually does better. And then there was another paper on provable accuracy, quantum accuracy. And the way they said it's a provable quantum accuracy is because they differentiated from a quantum model and the standard deviation error from a classical model and the standard deviation error from a quantum model. And they're working on a state vector simulator. And with that error, classical had a standard deviation error of three or more integer points more than quantum. So now with that just 3 or 4 points, they said, what is this? They said probable superior accuracy.
But ma'am, with like if you will optimize it, then gradient descent is one method we can use. But how long we can go for gradient descent? There is there any other method for optimization other than gradient descent? Like we are calculating.
Sorry for interruption. I mean, I was just saying like maybe have some other questions maybe they wanted to ask.
Okay, sir.
Or, yeah, I'm really sorry for interruption, but you know, maybe you can reach her personally, Kavitha, about these problems.
Yes.
You know.
So hi, Akash, Anuj here.
Yeah.
So just want to add like what Kavitha was mentioning. I think in nutshell, to my understanding, and if I go with the quantum global summer school and whatever discussions are happening, still the one thing which need to be understood, the QML modules which are there or whatever we are actually working, okay, they are still in the nascent stage. Okay, so you can consider they cannot be, if we are using them for the industrial apps, for the like some complicated data set which are being actually explored in the like classical machine learning. So answer is no. Okay, so you can start making an understanding how it can be done. But if you are experimenting, trying to experiment with a large data set, because this is a, see, as of now, the restriction is the number of the qubits. As Kavitha was mentioning, that feature data set, like features space which you are exploring. And if you do that, if it is like, for example, 256 actually features you want to explore, then you can't do it. Okay, so you have to go with a very restricted number of features. It can just try to, first of all, understand what are the, quantum is, in which particular area it is actually helping you. Okay. So if you understand that, then you can actually go for a larger data set. But as of now, it is difficult directly, as is like whatever the examples are there in the Qiskit textbook, it is not that straightforward.
Correct.
Okay, thanks, Anuj. Thanks for the
info. Yeah. Thanks, Anuj. So, yeah, it's not straightforward. And if you want to work on it, we have to build up different, more models and then ensemble them and then work with them. One approach, or other approach is basically, you can't really, there's a proverb, right? In India, they say like when you are testing a rice, you don't have to test all of the rice in your container. You just have to test one or two. So if you have 100,000 records, work on it for 5,000 records and say that what is the accuracy from quantum accuracy versus classical accuracy. If you think it did better, then use k-fold cross-validation. And then even cross-validation can actually work with callable kernels. So work with k-fold cross-validation as well, and try to see if you can actually see any better improvements in accuracy, and keep changing your repetitions, entanglement, and also different types of feature maps. With that, if you find any such data set where you are seeing quantum machine learning, quantum advantage, then you got it. You're there. Don't try to solve a problem which is classically already solved. That's exactly what Jay Gambarte's paper is also talking about.
So Kavitha, just one follow-up on that. So does that mean that we are identifying these specific problem statements where we can get a quantum advantage and getting ready for a larger qubit system? Once it is available, we might get a quantum supremacy. Is it a right statement?
If you get more than 1 million qubits, let's say, okay, 1 million qubits, then we can actually simulate 1 million features. Today, we can simulate already 2 or 3 million features with our classical machine learning, right? So if you are comparing how many number of features you're comparing against classical versus quantum, you would never say that quantum is so much better, because I'm not able to simulate 100 million features that I'm able to simulate classically. But the dimension of thinking is different here, that okay, my classical machine learning, whatever type of algorithm I used XGBoost classifier, which is supposed to be good. I used SVM, I used CNN. So whatever I'm using, I'm still getting 45% accuracy. It's such a lousy data, let's say. So with that data, come to quantum. If it's still a bad data, then you wouldn't be actually having good accuracy here. But if higher dimensional space mapping has been done, and then quantum can show that it is actually able to do it, even with 3 features, we are trying to show quantum advantage over there, right? So something intractable in classical is what you can solve it in quantum. We are not comparing classical against quantum. Then we are in a pitfall that we will never actually see quantum advantages. So even with million qubit systems, when it comes there, when we come there.
Interesting.
Yeah, that's very nicely put. Yeah, thanks.
Okay, thanks for the questions and thanks for the explanation. It was very nice. And Kavitha, I just noticed that in the Jupyter notebook by the Qiskit, they don't have these explanations. So is it possible for you to share your notebook?
What extensions?
Like the explanations you give, like the theoretical explanations, on the
Oh, I just added as I prepared this afternoon some things on ZZ feature map. Oh, all these things are there already in the Qiskit packages actually. Sorry, in the, where is this? In Qiskit, in Qiskit.org actually. So anywhere you go here and look for ZZ feature map. So
okay,
yeah.
So that's great. That's great.
So the ZZ feature map is here, and this is done for 3-qubit 3-qubit.
Under the Qiskit tutorial, quantum machine learning documentation, which I think Kavitha was just now showing. So it is the tutorial of quantum machine learning in the Qiskit.org. All those.
Yeah. That's what they're saying. By the way, I didn't catch your name, but that's what they're saying, that the explanations of what I have given on the feature maps and the ZZ feature map and other things is not there, but these are there already, and some of it are my understanding on different papers, basically.
I see. Okay, so I mean, if you think some like maybe you can share it, the slides you have presented.
Oh yeah, sure.
Yeah. So thanks. Maybe we will take a break for before the next present tutorial, and
okay.
So thanks, Kavitha, for the nice presentation.
Thanks a lot. Yeah.
Okay, so since we finished a bit earlier than we planned, then let's do a break indeed. And the next tutorial given by Antal Szava from Xanadu will start in about 20 minutes. So let's just do a break, 20 minutes break. Thanks. Okay, so hello everyone. After a break, now we'll have the last session for today for the conference. Antal Szava from Xanadu will tell us even more about Pennylane. So Ava, if you're ready, the Zoom is yours. And yeah, in the meanwhile, if there are some questions on our chat, then please ask and we'll follow. Okay, good luck.
For sure, yeah. Thank you so much, Pavel. And let me just quickly share my screen. So if also you should be seeing my screen at the moment. If that's not the case, just feel free to shout or write in the comment section. So once again, thank you so much, Pavel. And thank you for the organizers, including Q India and Q Poland and Q World, for picking the Xanadu and Pennylane team to give a tutorial session today. So my name is Antal. I'm a quantum software developer at Xanadu, and I'm also the lead developer for the open source engagement sub-team within the Pennylane team. So today, I would just like us to have a small introduction about quantum differentiable programming using Pennylane. And after that, we will just get into a tutorial session going through a couple of notebooks that we've prepared. I've sent through 4 notebooks. For each of them, you also received the solutions. Once we commence the tutorial session, you can just follow along the live coding that we will do together, but also you could just have a look at the solutions right away if that's something you would like to do. So kicking off with the presentation, let's have a look at using Pennylane for quantum differentiable programming. So you might actually ask yourself what Pennylane is, although I've seen that there was also a presentation previously today using Pennylane. Yes. But just to kick things off, Pennylane is an open source Python library for differentiable quantum programming of near-term devices. Well, this sentence is packed with lots of keywords here, and a couple of them are actually highlighted. So Pennylane is open source. The entire source code can be found on GitHub. You can just go there and browse through what we have in the software library Pennylane. It is also a library for differentiable quantum programming. We will actually see these 2 key things here. So differentiability and quantum programming side by side in a bit. It is also a library that has been created for near-term devices. At the moment, we still have noisy quantum devices, and most of the use cases that you can use Pennylane for. Yep. Okay. So most of the use cases that you can use Pennylane for are actually for these noisy quantum devices. So what exactly is differentiable programming? Differentiable programming is a paradigm that comes from machine learning and deep learning. And the main idea is that once you are writing your program, you also are providing some sort of a gradient to the functions that you are writing. So assuming that you write your own functions and you just tie them together into a full-fledged program, you are always providing these differentiable functions for your sub-functions as well. Once you have your entire program, you can just use one of the existing machine learning frameworks that support, for example, automatic differentiation. Such examples are TensorFlow, PyTorch, JAX, and also AutoGrad, which is a wrapped version of NumPy. You can use these frameworks to differentiate. Yes?
Just a quick question. Sorry for interruption. I'm not sure, but currently I cannot see your slides. I'm not sure if you are still presenting the slides. Maybe it's a technical issue on my side, but...
Yeah, actually, I can see the slides.
Oh, you can see? Okay, so
Me too. I cannot see the slides. Yeah.
All right, so probably something wrong on my side. So yeah, anyway, sorry for interruption. Please go on.
That's okay. That's okay. I can see it. Okay, so that's good. Is it then a problem only for a couple of people, or could it be
it's fine. I can see it again.
Yes, I can also see now. Thanks a lot.
Sure. Yeah, no worries. Okay, yeah, that's it's better to acknowledge if the slides are not visible at this moment. So yeah, but I'm happy if they are. But yeah, sure. So just going back to what really differentiable programming is. As mentioned, if we have a program that is differentiable in nature because we have provided our gradient functions, then we can use just machine learning frameworks to differentiate over such programs. Going on, another thing I've mentioned was the concept of quantum programming. And quantum programming will also involve quantum computing and quantum circuits. So what exactly a quantum circuit is, we can just have a quick example and have a look at how a quantum circuit could look like. In the right-hand side, we have a quantum circuit, which consists of three main parts. We have 3 qubits, each of them denoted by these lines in the quantum circuit. And there will be some sort of an initialization step for each of the qubits. So first, we prepare some sort of a state, a beginning state for the quantum circuit. And what we say actually is that this state can be denoted by a psi. And we use something that is called a bracket notation to denote this initial state. So this will be a ket psi, what we say. And for the 3 qubits, these are going to be 0 states on each of the qubits. So this is just going to be the 0 state that we initialize our quantum state in. The second step that we take, which is also apparent in this quantum circuit, is going to be some sort of is going to be applying some sort of a unitary transformation, a Y rotation gate on each of the qubits that we have here. To represent this entire unitary transformation, we can also just write a U that stands for the transformation itself, and it is going to be parameterized by some sort of a theta parameter. This theta parameter can be a vector of parameters. For example, in this case, it would be a vector because we have 3 different rotation gates. But it can be also a scalar value if we have a single rotation gate in our system. Once we have transformed our state with this U transformation, at the end of the circuit, we will just be measuring some of the qubits. In this case, we will be measuring the first qubit in the poly-z axis, and we will also be measuring the second qubit in the poly-z basis. So these measurements are great because we can basically just get the quantities related to certain observables that we would like to get measurement statistics for. So this is just a quick overview about quantum circuits, but using one of the postulates of quantum mechanics, we can also provide a formula for one of the statistics that is quite important when computing with quantum circuits. This is going to be the expectation value of some sort of an observable given a quantum circuit. So this expectation value is actually something that we can compute using the Born rule. The Born rule is a postulate of quantum mechanics that determines what the what the probabilities of measurement outcomes are based on some sort of an observable B. Having a look at the right-hand side of this formula, we see a couple of terms that might be familiar. So we have this ket psi, which was the state vector that we have prepared at the beginning of the circuit. We also have the unitary transformation U parameterized by some sort of a theta. And we also have the B observable that we've seen previously. This will just be the, in this case, when computing this expectation value, we can just use the matrix representation of the operator B. On the left-hand side, what we have is basically the adjoint of the unitary transformation and the adjoint of the state vector. This adjoint of the state vector is going to be the bra psi. If we look at the entirety of this expression, what we can actually see is that all of the operations between these vectors and matrices are going to be matrix vector multiplications or matrix multiplications. So these are things we can just simulate easily using machine learning frameworks whenever the systems that we have at hand are small enough so that they can be simulated with classical computers. It is also important to note that this expression can be parameterized by the theta value. Therefore, it will actually be a quantity that is continuously dependent on theta. So we've seen what differentiable programming is. We also had a look at what quantum circuits are. The key idea behind the quantum differentiable programming is that we can get the best of both worlds. So we can combine quantum computing with differentiable programming and define functions that involve quantum circuit evaluations. So assuming that we have some sort of a feature vector X, and we have some sort of a vector of trainable parameters theta, what we can do is to input them into some sort of a node, which we can refer to as a quantum node. And this quantum node will then perform some sort of a unitary transformation within the quantum circuit evaluation, which, and this unitary transformation will then be parameterized by the trainable parameters, this vector of thetas. At the end of the quantum node is going to be some sort of a measurement statistics that we would like to gather. And this will be something great when we would like to, for example, train quantum computers. As mentioned, we can just refer to this training procedure by having a look at a single function f that takes two parameters, a vector of features and a vector of trainable parameters. So the key idea here is that we can really train quantum computers just as we would like, for example, classical neural networks. Once we acknowledge that key fact, we can just start mixing up the training of quantum computers with classical models. So when it comes to near-term devices and near-term quantum algorithms, we actually refer to them as variational circuits. We will have a look at what variational algorithms and variational quantum algorithms are in a bit. But the key idea here is that we can have multiple of these quantum nodes together to provide a joint cost function and to create a quantum node in a bigger model. If we take these building blocks and combine them with some classical machine learning models, then we can actually create hybrid models where we have nodes that are quantum in nature. These are denoted with the green boxes. And we can also have nodes that are classical in nature, which are denoted with yellow boxes. One key thing here to note is that these green boxes, they can actually be executed on different quantum devices. So it might be that you have an ion-based quantum device here, but you might have a photonic-based quantum device somewhere else in your network. So the key takeaway here is that you can combine quantum and classical nodes in your hybrid model in order to just provide an end-to-end differentiable hybrid model at the end. I've started referring to the quantum components of a hybrid model as quantum nodes. But how exactly can we actually use these quantum nodes when we are simulating them with our classical machine learning frameworks? Well, The key thing here is that if you have a quantum node in the middle, you can just pass this quantum node data structures from machine learning frameworks, which are usually tensor objects. What you can then do is to extract the numerical data from these tensor objects, be it a TensorFlow tensor or a PyTorch tensor. Once you have extracted these numerical data, you can just pass them into the quantum node, which will then be, in most cases, the input gate parameters for the quantum circuit. The quantum node can then be either evaluated, or we can gather its gradient as well. We will soon be having a look at how to get the gradients of quantum circuits. And once we have our resulting quantity, we can just convert that numerical data back to the tensor object that we have used previously. So you might ask, okay, we can train quantum computers, but how good are they? How well can they be used for the use cases that we would like them to solve? Well, the answer is that most of the quantum processing units, these QPUs, they are still very noisy. So the entire advancements in quantum devices is in a research and development phase. There are advances when it comes to software development, and there are still hybrid models that are being tested, but it's still at a stage where we are using noisy devices. In order to be able to get the power of noisy devices, we have to use variational quantum algorithms. The key insight with variational quantum algorithms is that even though our quantum evaluations are noisy in nature, so we might not get the ideal results we would like to get, by repeating the same quantum evaluations many times, we can get quantities that are still useful. And this is a key insight for VQAs. Now let's have a look at what parts make up these variational quantum algorithms. So first, we would be choosing something that is referred to as a circuit ansatz. This circuit ansatz is nothing more than an educated guess, a good quantum circuit that is very special to the problem that we are looking at. Once we have this circuit ansatz, we can then just create some sort of a quantity that can be the expectation value of an observable, which we had a look at previously. And using this quantity, we can then go to the second step, which is to define a cost function. So once we have the expectation value of a certain observable that was gathered from a quantum circuit, we can just define certain cost functions in order to solve very specific problems, which can, for example, also mean using several of these expectation values to make up a cost function at the end. A couple of examples of cost functions that you can use for variational quantum algorithms include the variational quantum eigensolver, which can be used to approximate the ground state energy of molecules. But you can also just encode certain Hamiltonians using something that is referred to as the quantum optimization approximate algorithm, quantum approximate optimization algorithm, referred to as QAOA. Once you have some sort of a cost function defined, you can just finish up your training procedure by also defining a classical optimization method. In most cases, you already have your quantum component. You already have a cost function, which might have classical components as well. And at this point, you would most likely want to use gradient-based optimization methods in order to train your hybrid model and to get more ideal hyperparameters to your quantum and classical components as well. So I've mentioned that the last step will be to get the training procedure done. And the key factor here is that in order to get the training of hybrid models that also include quantum computers, you would like to extract the gradient of a quantum circuit. Now, up until now, I've been referring to the training of quantum computers, but we haven't really touched upon how to get the gradient of quantum circuits. This is a key insight, because if we would like to train quantum computers, and we would also like to get the power of quantum computers, we really need the gradient of quantum circuits with regards to some trainable parameters. The question is, how could we potentially get these gradients if even the simulation of quantum systems is classically intractable, and big quantum systems will be very hard to be simulated on classical computers? The answer is that there is something that is referred to as a parameter shift rule. This parameter shift rule defines a way of computing the gradient of a quantum circuit with regards to some trainable parameters by shifting parameters into the positive and the negative direction and evaluating the same quantum circuit using the shifted parameters. So having a look at the right-hand side of this slide, what we can see is that if we have some sort of an f theta quantum node, which is parameterized by the theta parameter, what we can then do is to shift this theta parameter into the negative direction with some s shift value, shift the same theta parameter into the positive direction with the same s shift value, evaluate the quantum node in these two positions, get the difference of these evaluated results, and multiply it with some constant value. And what the parameter shift rule says is that there are certain quantum operations which admit this formula, and when they are used in a quantum circuit, we actually get the gradient of that quantum circuit using this formula here. So I see that we got the question here. What does U theta consist of? That's a really good question. In this very specific example, U theta would be so U would be the unitary transformation that we have a look at. In this very specific example, it would mostly be a single rotation gate, for example. In that case, theta would be a scalar value. If you have multiple rotation gates in the same quantum circuit, then the unitary transformation would refer to all of these rotation gates, and theta would be a vector. In such cases, however, the parameter shift rule will be slightly more complicated, because you would also have to use the chain rule to get the gradient of the quantum function. So I also see that there's another question. I have a question. Please, what is the tool they use for drawing circuits and graphs in Pennylane and in these slides? They look simple and user-friendly. Oh, thank you so much. So I believe it might have just been one of our colleagues who has drawn these pictures. So there's not really a general way of drawing them. Yeah. So these were just created for the slides. Okay. So going back to the parameter shift rule, just as a quick recap, if we have quantum circuits with quantum operations that admit the parameter shift rule, then we can use a simple, we can use two evaluations or two times p evaluations, where p is the number of trainable parameters, in order to recreate the gradient of the quantum circuit. Hi, Tata from Toronto. Nice to have you here. Okay, so going on with the parameter shift rule, the intuition behind this rule is really similar to a simple example from trigonometry. So if we take the sine function and just regard it as some sort of an f theta function, what we can see is that its gradient is going to be the cosine function. But we can also just use one of the characteristics of the cosine function, which is that we can determine the cosine function by evaluating the same sine function with shifted parameters. So if we shift these theta values into the positive direction with pi over 4, shift the same theta values into the negative direction with pi over 4, evaluate the sine function at these two positions, get their difference, and then multiply it by a constant 1 over square root of 2, then we actually get the cosine function. And this is really the intuition behind the parameter shift rule as well. If we get some shifted values, as the quantum circuit inputs, evaluate the quantum circuit at those two positions, we can recreate the gradient by using some sort of a constant value as well. At this point, it is very, very important to note that the parameter shift rule is distinct from something that is called the finite differences rule when it comes to numerical differentiation. So we've seen that this is the formula for the parameter shift rule, and this formula is going to get the exact results for quantum gradients. So we get analytical results. In contrast to this, using the finite differences rule, what we get are only approximations. It is also worth noting that while in the finite differences rule, these shifts are very small in magnitude, with the parameter shift rule, these S values are usually pretty large. So as we've seen, one example could be pi/4. For finite differences, we usually have numerical instabilities, or there are cases where we can have numerical instabilities, and also the noisiness of the evaluations can affect these approximations that we get. So just as a recap, if we can use the parameter shift rule to get the gradient of quantum circuits, we are in a really good position because we can get analytical gradients. One thing to keep in mind is that with the parameter shift rule, we are increasing the number of quantum evaluations. So in that case, it is also worth noting how much of the resources we will be using when computing the analytic gradient of a more complicated quantum circuit. So just going back to the ideas we had previously, let's return to the gradient-based training model that we have been preparing here. We have the parameter shift rule, so we can compute the gradients of quantum circuits. In order to compute the gradient of a quantum circuit that has a single rotation gate, for example, what we can do is to evaluate the same quantum circuit with shifted parameters into the positive and into the negative directions. And this will allow us to recreate the gradient of the quantum circuit. Once we have the gradient of quantum circuits, we can simply just train our hybrid model that consists of quantum nodes in it as well, using gradient-based techniques such as gradient descent. At this point, I might just stop for a second. If there are any more questions, let me know. Otherwise, we can just go on. But yeah, I might just take a minute and see if you have any questions.
So, on which hardware these things will be executed as part of the Pennylane?
Yes, that's a good question. So we will actually touch upon this later, but Pennylane allows connecting to several types of hardware. So it can connect to, you can use Pennylane to connect to hardware from IonQ, from Rigetti. Using the Amazon bracket, you can connect to all of these hardware as well, but you can also connect to Xanadus hardware using strawberry fields. So the parameter shift rule is something that usually is applicable for qubit-based parameterized gates. There are certain parameter shift rules for continuous variable gates as well, but they are not as general in nature. And recently there was also a find that summarized that there is actually a general parameter shift rule for all the quantum gates that we know about. They are not as simple as just shifting the parameters. So I would just like to highlight the fact that in most of the cases, this easy parameter shift rule, so to say, works for well-known rotation gates. So for example, for X, Y, or Z rotation gates, or other gates that admit a specific criterion. So just to get back to your question, you can use it to train on hardware that Pennylane can connect to. But the parameter shift rule itself is more general. So if you have these, if you have gates in your quantum circuit that admit this rule, then you can use it to get the gradients.
Okay, and for quantum annealing, only D-Wave provides larger qubit systems, right? So for that type of hardware, can this technique be used?
Yeah, that's a good question. I must admit, I'm not entirely familiar with quantum annealing and their architecture, but I would think that their architecture is so much different that the parameter shift rule might not be relevant. But I wouldn't like to give anything. You know, I'm not sure. That's
okay. Thanks a lot.
So I have a question, like small question, like how the parameter shift rule gives us the advantage over other optimization methods. Like in the gradient descent, like we have other methods of defining this gradient, right?
sure. So the parameter shift rule gives us the advantage because if we don't have the parameter shift rule, we have no way of getting the gradients when we are training on real hardware.
Oh, okay, I mean,
so,
my question was maybe too much generalized, but specifically I was talking about targeting the barren platinum, you know, like the cost function becomes constant at some point. So this parameter shift rule may give us some advantage over that, or I mean, I'm not sure the question makes sense or not, but yeah.
So maybe it's worth just noting that the parameter shift rule just allow us to get the gradient of components in our model. It's how to say, it's more specific than the cost functions or the training procedure itself.
I see. It is more efficient, you are saying, in the system, right? To calculate
no,
this.
It's just without the parameter shift rule, it's not feasible to train quantum computers on real hardware.
Yes, so I'm just saying, like, there are many methods like where we don't need gradient, you know, like this Kobla method or this Powell method. Yeah. So I was just saying, like, how to compare those methods with this, you know, like this parameter shift rule, does it give us some advantage? I mean, if we calculate the gradient.
Yeah, so the parameter shift rule is analytic in nature. So for example, I'm more familiar, for example, with the SPSA optimization method. That would be something that is approximate in nature. So there would be some sort of a noise usually admitted, at least with SPSA. It's still useful in certain cases, but the promise of the parameter shift rule, which it really brings to the table, is that it is analytic. So if you can use the parameter shift rule, you will get more accurate results.
Okay, so that's what I wanted to hear. Thanks.
Sure thing. Okay, in interest of time, I might just go on with this presentation, but if you have any more questions, feel free to drop them in the chat section.
Yeah, sure.
Sure thing. Okay, so now we've actually covered what quantum differentiable programming is, or at least we've got a small introduction to it. So let's have a look at what Pennylane achieves and how you can use quantum differentiable programming using Pennylane. So first off, let's have a look at one of the first demonstrations that you might find when looking out for Pennylane demonstrations, and this is a qubit rotation demo. So this is the quantum circuit that we have at hand. Going from the left to the right-hand side, we have some sort of a zero state that we initialize on a single qubit. We rotate this single qubit along the x-axis with some Rx rotation using some phi 1. And then we rotate the same qubit along the y-axis using some phi 2 parameter. And at the end of the circuit, we perform a measurement in the poly Z basis. The key thing to do here is characterized by these two spheres that are referred to as block spheres. So on the left-hand side, what we see is that our initial qubit is pointing upwards along the z-axis because it is in the zero state. This is just a representation of single qubit systems. What we would like to then do is to transform this qubit such that the same state is going to be in the one state, so pointing downwards along the z-axis. In order to achieve this, we will then, as mentioned, do an X rotation followed by a Y rotation. So let's have a look at how you could code this up using Pennylane and how you could actually even connect to a quantum hardware. So first off, in Pennylane, you would just import the library and name it as QML. And you could also just import things from PyTorch, because we will be using later integration with PyTorch. Once you have your imports set up, you would create a device using Pennylane. To do that, you use the QML.device top-level function. You pass in the name of the specific device that you would like to use, and you also pass in the number of subsystems you would like to use. In this very specific example, we are using our integration with the AWS bracket, and we would like to gather one of the real quantum computers as the device. To do that, you would also have to just provide your authentication data, so some sort of a bucket name using Amazon, and the folder name where you would like your results to be stored. Using AWS bracket, you also provide some device ARN string. This will just refer to the specific device that you would like to use. In this case, we would like to connect to Rigetti's QPU that is called Aspen9. Once you have your device set up, you can create your quantum node. The quantum node will simply be a quantum function, which is a Python function. It will be a recipe for the quantum circuit that you would like to run. In this case, as previously mentioned, we had an X rotation gate on the first qubit with using some phi1 parameter, a Y rotation gate on the same qubit with some phi2 parameter, and we would like to then return the expectation value of the Pauli Z operator on the same wire, so on the first qubit. In order to create a quantum node out of this quantum function, we can use the QML.QNode decorator. In order to create a quantum node, we are decorating the quantum function, passing the device that we would like to use, which was Rigetti's QPU. And in this specific example, we would also like to use the torch interface. Once we have defined our quantum device, using that, our quantum node, we can just put classical optimization steps on top. So first, we will just define our cost function, which is going to be using the expectation value that we get from the quantum function. And we would like to just near this expectation value to our target expectation value, which is going to be the -1 expectation value. This is the eigenvalue that is corresponding to the one state when it comes to the Pauli Z operator. And just to measure this distance, we also give a numerical representation of the cost function. Once we have defined our cost function, we can use PyTorch data structures, so tensors from PyTorch, and we set them as trainable using the requires grad equals true specification. So we have two input parameters here, phi1 and phi2. We just also define an optimizer from PyTorch. We will be using an adaptive gradient descent optimizer. So we just use the ADAM optimizer, set the learning rate to 0.1. And at this point, we can start iterating over our training procedure by evaluating the cost function at each step and getting the gradient so that we can also update the parameters. So this is really a full-fledged example of how to define a hybrid optimization method in Pennylane. One thing we have already touched upon is the fact that Pennylane is framework and hardware agnostic. There are several quantum computing frameworks that you can connect to using Pennylane. These include Qiskit, Cirque, Forest from Rigetti, but also Strawberry Fields from Xanadu. You can easily just connect to new quantum devices by using the same QML.device function and just simply changing the device name that you would like to connect to. Apart from the quantum computing frameworks that you can use with Pennylane, you can also use machine learning frameworks as Pennylane interfaces with such frameworks. These include TensorFlow, PyTorch, JAX, and AutoGrad using NumPy. One of the key things that we have mentioned previously is that the capability of having hybrid models also comes with the fact that it would be great to end-to-end differentiate such hybrid models. So models that consist of classical nodes and quantum nodes, well, we would like to differentiate over the entirety of such models. And this comes out of the box with Pennylane. So everything you write is end-to-end differentiable in Pennylane. If you would like to run such hybrid models using real quantum computers, you can do so by getting analytic results using the parameter shift rule. If you are using a simulator, for example, with a machine learning framework, such as TensorFlow or PyTorch, you can even use backpropagation or automatic differentiation using these frameworks. One of the key factors when using Pennylane is how to get the gradient of quantum nodes. We've had a look at how you can get the gradient using the parameter shift rule, and this will be great when you are specifying a differentiation method to be run on hardware. So using Pennylane, when you define your quantum node, you can simply just also specify the diff method attribute when passing arguments to the quantum node, and you can just simply specify the parameter shift rule if you would like to get analytic gradients. If you are on a simulator, however, and you would like to use automatic differentiation with machine learning frameworks, you can just specify backpropagation as an option. This will get the classical this will get gradients using classical backpropagation, but it will be constrained to smaller systems that you can simulate on your devices. There is also another differentiation method that we allow, which is referred to as the adjoint differentiation method. This is very fast and memory efficient. It uses the state vector of the quantum system, and we allow this with one of our simulators, that is the basic default qubit simulator. If none of these methods apply to your use case, or you would just like to get numerical differentiation into the picture, you can even use the finite differences rule by setting the diff method attribute. I've briefly mentioned that we have a basic simulator in Pennylane, and we have actually a group of simulators that come built in with Pennylane. So the first one is called default qubit. It's a basic qubit-based simulator that is also a pure state simulator, and you can just use it for rapid prototyping. We also have a continuous variable simulator, default.Gaussian, and we have a plugin for strawberry fields as well, where you can get more simulators for the continuous variable model. We have another built-in qubit-based simulator called default.Tensor, which is in an experimental phase at the moment. It uses the tensor network library, and it is usually ideal for short and wide circuits. If you would like to get a mixed state simulator to simulate inherent noise as well, or you would like to just get channels into your quantum circuits, you can even use the default.Mixed simulator. It might be that you are completely new to Pennylane, and you might have used other quantum computing frameworks such as Qiskit. If that's the case, you can just simply define your quantum circuit in Qiskit and use one of our functions, the QML.FromQuiskit function, to convert your quantum function from Qiskit into a Pennylane quantum node. This is also great if you, for example, are familiar with Rigetti Spikeful. We provide a loading function for that framework as well. In Pennylane, we have a growing plethora of quantum recipes that are referred to as templates. These templates provide you with embeddings, layers, state preparations, and much, much more. You can just use these templates in your quantum nodes by calling on the template name itself, which will, under the hood, just apply quantum operations as per the definition of the template itself. So it can be used to embed the classical data or to get more general unitaries and apply multiple layers of such unitaries. Pennylane also comes with a quantum chemistry subpackage, and this is called Pennylane QChem. You can install Pennylane QChem using pip. It's a standalone subpackage. Once you've installed it, you can use it to get the molecular structure of molecules as Pennylane observables. It uses a PySCF or a Psi4, and it interfaces with OpenFermion as well. One of the upcoming features for the QChem module is going to be a dedicated Hartree-Fock solver that is differentiable in nature, coming up with the next release of Pennylane. It might be that you would like to learn more. So we have a big group of demonstrations for each of the use cases that have been used for Pennylane. If you would like to check these out, I encourage you to go to pennylane.ai and choose the demonstrations that you find interesting. There is also the opportunity to submit new demonstrations. So if you have some sort of an idea that you would like to use Pennylane with, feel free to just drop the tutorial on the GitHub page that we have for Pennylane. So at this point, there are a couple of things that we are really excited about that came up with the last release of Pennylane. The first one that I would like to note is something that is referred to as Lightning.Qubit. This is a new simulator that has been worked on for some time, and it is C++ based. Lightning.Qubit now comes pre-installed with Pennylane. You can use Lightning.Qubit just by using the same QML.device top-level function. You just have to define Lightning.Qubit as a short name. It comes installed on several architectures. So even though it's C++ based, you can use it on Windows, macOS, Ubuntu, and PowerPC as well, for example. It also implements, Lightning.Qubit also implements the adjoint differentiation method. And this small result just shows how much faster it can get when compared to default.qubit, which is Python based. Another thing we are very excited about is further integration with PyTorch. Earlier this year, PyTorch introduced complex numbers into its framework, and with the adequate support, we could also add this to Pennylane. So right now, if you would like to use backpropagation with the PyTorch device, you can do so with the latest release of Pennylane. Your entire computation will be in PyTorch, and there will be no conversions between PyTorch and NumPy. Another thing we are really excited about is the notion of quantum transforms. So these quantum transforms are useful to transform your quantum circuits into new quantum circuits or into quantities such as the metric tensor. The cool thing about quantum transforms is that they adhere to the differentiable everywhere sort of approach we take in Pennylane. So they are differentiable in their nature as well. We have a dedicated blog post for quantum transforms. So if you would like to check out more, I encourage you to check this blog post. So that was it for the quick introduction of Pennylane and quantum differentiable programming. Before we move into the tutorial session, I'm just curious if you have any more questions. We could address them right now, and then we can just get to coding.
All right, thanks, Antal. Do we have any questions? I see that there was a question, which file is this? I'm not sure, it's a question from Santanu. So probably this was an earlier part of the presentation. So Santanu, if you still have a question, then you can unmute yourself and ask directly to clarify. Okay, we don't see more questions now, so Antal, I think we can go on if it's fine for you. Maybe there will be some questions later.
Sure thing. Oh, thank you. So, yeah, Santanu, the example I've shown, it was kind of a mixture of one of the demos we have up on Pennylane.ai. So maybe you could check that out. It also was just showing the integration with Amazon Bracket. But yeah, if there are no more questions, I might just stop sharing my slides. And I'll just pull up the first tutorial that we could have a look at. So this first tutorial is going to be the simple circuits with Pennylane tutorial. So if you would like to follow along, I encourage you to open a Jupyter notebook and just maybe follow along as we code together, or you could just have a look at the solutions if that's something you would like to do. Okay, I might just quickly share my screen of the Jupyter notebook. Right. Sorry, can you see my notebook well? Is it does it appear well?
No, not yet.
No? Okay. Sorry, does the notebook appear now, or is still not there?
Still not there, yeah.
Oh, really? That's really odd.
Okay. I thought it appeared, and
How about now?
maybe it's taking time to appear. You know?
Okay.
Yeah.
Sure. Yeah, if you could just let me know if something changes, that would be great, because.
Yeah, sure. Yes, it's there. We can see.
It's there now.
Yeah.
Awesome. So it's just taking its time. Is it there for everyone, or is there maybe someone who cannot see it yet? Okay. I just. Awesome. Oh, that's great. Okay. Cool. So yeah, for the first notebook, we would just be looking at simple circuits in Pennylane. There are a couple of learning goals for this notebook. So we will write a quantum function in Pennylane. We will define a Q node that we have previously seen during the presentation as well. We will construct it in two different ways, and we will execute the Q node on several devices. So just as a reminder, we might have a hybrid model that consists of some classical nodes and some quantum nodes as well. And we would like to just execute such a model and use it in our optimization steps. In order to define such a model, first we would like to define something that is called the quantum node, so a Q node. In order to define a Q node, first we get a quantum circuit. We describe this quantum circuit by something that we refer to as a quantum function. This is going to be a simple Python function using Pennylane. Next to this quantum function, we will also just define a device, a quantum device. We've had a look at this previously, but we will also see this in action. And once we have a quantum function and a quantum device, then we have our quantum node ready. So let's assume that we have this following circuit on 3 qubits with certain rotations, C0 gates, and the Z operator measured on the first wire. Let's assume that we have this quantum circuit. So in order to create a Q node for this quantum circuit, first let's define a device using Pennylane. So first we can just import Pennylane, and we can also just create a device using Pennylane. I will be using the basic simulator, so default.qubit from Pennylane. Once we have this device, we can just define the quantum function for this quantum circuit. So in order to define this function, we will provide 3 parameters, theta, phi, and omega, which will be the rotation gate parameters in the quantum circuit. Once we have these 3 parameters defined, what we will do is define the rotation gates themselves. So here, what I'm doing is that I'm calling on a quantum operation from Pennylane. We are constructing this quantum operation and passing the input parameters of the operation along with the qubit numbers this operation will act on. In Pennylane, we call qubits wires. Once we have the X rotation gate, let's just define 3 other rotations as well. Define the qubits that they act on. So our second rotation is going to be the Y rotation gate, taking the phi parameter and acting on the second qubit. Since we are indexing from 0, this is going to be wires equals 1. The third rotation gate is going to be the Z rotation gate, taking the omega parameter and acting on wires equals 2, because it's the third qubit. So at this point, we have defined the rotation gates of our circuit. Let's define the C0 structure as well that we have here. So just as a hint, we have 3 C0s that act on from the first qubit to the second qubit, having the first as a control, second qubit to the third, and third qubit to the first. What the C0 structure does effectively is that it creates entanglement in the system. That is why we actually have these C0s in the system. And this will be really great when we are measuring on the first qubit, because the 3, each of the, any 2 of the systems in these 3 qubits are going to be pairwise entangled using the C0s. So we have defined our circular structure using the C0s. We would just like to return something in this quantum function. And what we would like to return is going to be an expectation value. We can just write this using the qml.xval top-level function. And we would like to get the expectation value of the poly Z operator on the first wire. We can write wires equals 0, but for these operators, we can also just emit this wires option and just pass 0 there. Once we have this, we have actually defined our quantum function. So just going back, we have our quantum device, we have our quantum function. We would like to just tie these together to create a quantum node. To create a quantum node, you can just use the qml.qnode top-level class, pass in the circuit that we have and the device, and just create the quantum node itself. In order to evaluate this quantum node, we will really just need to pass in the theta, phi, and omega parameters that are taken by the quantum circuit. Once we do that, we can simply just get the resulting evaluated quantity of the quantum node. In order to define these parameters, I will simply just import NumPy. Now, I will import NumPy in a tricky way, because what we do in Pennylane is that we just wrap NumPy, and I'll just import NumPy from Pennylane. The reason to do that is the following. When we define a NumPy array using Pennylane's NumPy, what we will then see is that this is going to be a tensor data structure. This is something that we provide definition for in Pennylane. And the reason why we provide this tensor data structure is that you can then set the requires grad attribute, just as in PyTorch, for any of the NumPy arrays that you use from Pennylane. So this is great when you would like to indicate that an array is going to be trainable or non-trainable. So this is just a a small example of why we provide this NumPy framework from Pennylane as well. So going on, we just define the same. We just define multiple other parameters as well. Once we have the 3 parameters defined, we can just pass them into the Q node to evaluate this Q node. So what happened here was that we had the Q node defined. We have passed the 3 parameters to evaluate the Q node. And what we've got was the expectation value of the poly-Z operator on the first wire. As you can see, this is also a tensor from Pennylane, which is trainable in nature. So you could just pass this into other components of your model and make it trainable. One of the neat things you can do with Q nodes is that you can draw these Q nodes. The cool thing is that then you can have a look at the structure of such Q nodes and see that we really recreated the quantum circuit that we would have liked to. So in order to draw Q nodes, it's great to print the outputted string just because it will render better. So at this point, what we see is that we have 3 qubits. We have an X rotation gate, Y rotation gate, Z rotation gate on the corresponding layers. We also see the parameters that we have passed into these rotation gates. And we have this CNOT structure. So the control X is actually the same as a CNOT. So we have this CNOT structure on the 3 qubits, and we have we are gathering the Z expectation value on the first qubit. One cool thing that I would like you to bear in mind is that before the end of the year, quite likely we will have a dedicated new circuit drawer that will be in Matplotlib. So it will be using Matplotlib to have a more designful circuit drawer capability. So yeah, if you're curious about checking Pennylane, then I really advise you to tag along for the next 1 or 2 releases. All right, so we have drawn our quantum circuit, and it really seems like, just to double check, it seems like we got the structure well. Now that we have drawn it, one other thing we can do is to use the Q node decorator to define the same Q node that we have defined previously. In order to do that, I will just copy the same quantum function, name it circuit2, and decorate this quantum function with the Q node decorator. When you are decorating the quantum function, you just have to pass in the device. So this device came from the very beginning of our notebook, where we have created a default qubit device. And once you have this device passed to the quantum node, you really just defined the quantum node using the quantum function and the device with a decorator. At this point, I'll just copy the parameters as well and evaluate the same quantum node using the new Q node. I made a syntactic mistake here, but correcting that, we see that we get the same expectation value of the poly-Z operator on the first qubit. So this is great because we have used a very basic device from Pennylane that comes pre-installed, but it might be that you would like to connect to other backends coming from other quantum computing frameworks. So one possibility can be that you would like to get a device from, for example, from the Qiskit plugin that will then not compute analytic statistics, but use several circuit runs to get average statistics. What I mean by that is that such a device can compute expectation values by running the same quantum circuit and averaging over these expectation value runs. To showcase this, let's define a new device. You can call def_shots. For example, it can be anything really. And you will get one of the devices from the Qiskit plugin. We will have the same number of wires, but at this point, we will also set the number of shots that you can that you gather to get statistics from your quantum node. At this point, I will just set this to shots equals 1,000 so that we will get pretty decent results, but we will be able to toggle this number later on. To get results for the same quantum node, I will just copy the previous definitions, pass the new device, and update the quantum node evaluation. And at this point, we have evaluated the same quantum node using a different device. And what we can see is that the result is actually slightly off from the analytic value. And the reason for this is really just that we've taken 1,000 shots of running this quantum circuit, and we have averaged over those results to get the expectation value of poly Z. Previously, using default.qubit, we actually got the analytic value of this expectation value. So this is just to show that there are other devices in Pennylane, and we encourage you to use other devices and use other plugins from Pennylane. So that might be it for this first notebook. Well, just as a quick recap, what we've had a look at was how to define quantum functions in Pennylane, how to define your devices in Pennylane, getting these two building blocks together, how you can define quantum nodes, how you can evaluate quantum nodes in two different ways. So first, just by using this QML QNode class, evaluating the QNode by passing in the parameters, but also using the decorator, you can create a QNode. So we had a look at how to use this decorator as well. You can draw your QNodes using the QML.draw function, but also you can use other devices such as the Qiskit.air device from the Qiskit plugin to, for example, use devices that are inaccurate in nature because they are using multiple executions of the same quantum circuit. So that's it for the first notebook. I will maybe just stop here for a bit if you have any questions. And I will just keep the notebook open, but let me know if you have any questions.
Yeah, actually, Jasmeer Wong just said that he's having some problem in dev source. So he's asking, like, do I need to include a plugin for this dev source? Like, because of the Qiskit, maybe he's having some error.
Yes, now I just see. So the Qiskit plugin should be installed. That is something that was in the requirements.txt file. You can install it just with, let me just type it in here. No, you don't need to install Qiskit because installing the Pennylane Qiskit plugin will also install Qiskit. Okay, so let me just go here. So if you hit pip install Pennylane Qiskit, the Qiskit plugin should be installed, and Pennylane will then know to use the device from the Qiskit plugin when you just define QML.device and get the Qiskit.air device name. I also see, Santanu, that you had some problems with the Dopplex. I'm sorry, but I'm not really sure what could cause this one. Oh, nice.
I think maybe the system compatibility, maybe 32-bit. Yeah, maybe need to use 64-bit or something.
Could be, yeah. Honestly, I haven't seen this warning before.
Okay, so Jasmer's problem is just resolved. Yeah, thanks.
Sure. So I see, Santanu, in the last output, I got this result from my 32-bit machine, which is better than the previous one. Is this wrong? The answer is 0.991, 0.009. I'm wondering how come you got two numerical values there. Maybe you've also defined another expectation value here or something like that. But one of the key things when you have a device that averages the results based on shots is that you will actually get different results based on different executions. So if you run the same cell multiple times, you will get a different approximated result for the same expectation value. The reason is that in the background, you get 1,000 shots for the same quantum circuit, but those shots will result in, those shots may result in different outputs. And we are on each time averaging over those results, those resulting outputs.
So I have a question, like it is possible to do the Pauli-Zinn measure on all the qubits, right? Like in an array of 0, 1, 2, or something like this in the expectation value, right? EXP value. Because we're doing only on the 0.
Yes, yes, you could do that. You could do it on all the qubits. So to do that, what you would do is to define something that is referred to as the tensor product of the Pauli-Z operator on all of the qubits. So you could use this multiplication symbol in between the operators, which is going to be in effect the tensor product operator. And you can just use it to get the tensor product of the Pauli-Z operator ranging from the 0th to the 2nd qubit. And you can just get this expectation value.
Okay.
Okay, so Santanu, is it looking good now, or would there be maybe something that seems off still?
I think it's solved. Yeah, he's saying that he got it. Yeah.
Awesome. Okay. All right. Maybe we could go on to the second notebook then. Let me just start sharing that. Likely it will just take some time. So this second notebook is going to be the gradients notebook. And as for the first one, we can just go through it together, but you could also just have a look at the solutions if that's something you would like to do. So I've shared my screen now. Please let me know if you start seeing the notebook.
Yeah, it was quick.
Say...
it was quick, yeah.
So now it's, oh really? Oh, that's amazing. Okay, so it's loaded now completely. Awesome. Okay, so the second notebook that we will have a look at is how to get the gradients of quantum circuits. So first off, there are a couple of learning goals here as well. So we will just get the gradient of a quantum circuit. We will optimize a quantum circuit, and we will familiarize ourselves with an optimizer from Pennylane. So first, let's have a look at the quantum circuit, very similar to the one that we had a look at just now. A small difference is that now we have the measurement on the 3rd qubit. But we have the same structure where we have rotation gates on each of the qubits, and we have this CNOT structure as well. So can you zoom the screen? For sure, yes. Maybe, is it better now, maybe, or? Oh, awesome, okay. Awesome, yeah. Okay, so just if you recall from the slides, what we can actually do is to denote this expectation value as some sort of a function that takes 3 parameters, in this case, theta, phi, and omega. And what we would like to do is to get the gradient of this function with regards to one of these parameters. So in this very specific example, we will pick theta, and we would like to get the gradient of the quantum circuit with regards to theta, which is the parameter to the X rotation gate on the 1st qubit. So first off, we could just import Pennylane once again, and we could import NumPy from Pennylane just to be on the safe side. Then we are later defining parameters. Once we have done that, what we can do is really just to define the same quantum circuit. So I might just do this slightly quicker this time, but first we define some sort of a device, which will be the same device as before. we will also just define some sort of a Q node. And we will also define a quantum function that represents this quantum circuit. One thing I didn't mention was that in Pennylane, by default, we initialized the 0 states. So that's why we didn't have any state preparations at the beginning of our circuit. But for example, if you have state preparations where you have, for example, the 1 state or other states here, you could have basis states of other operators as well, then you would have to add the basis state preparation steps to your circuit. We will actually have a look at this later as well when we have a look at embeddings. Okay, so just going through the circuit once again, we have an X rotation gate on the first qubit. We have a Y rotation gate on the second qubit, and we will have a Z rotation gate on the third qubit with the theta, phi, and omega parameters as input parameters. We also have the C node structure that we see in the circuit. This will be the same chain-like C node structure on 3 qubits, and this, as mentioned, just creates entanglement in our system. Once we have these operations defined, we will also just define the expectation value as before, but this time it's going to be the poly Z operator on the third qubit. Okay, so we've used the QML.QNode decorator to create our QNode at this point. Let's have a look if we can really just evaluate this QNode. So to do that, I will just define these 3 parameters, initialize them at some random values, and we will just evaluate our QNode, which is at this moment called circuit, using the parameters that we have defined. So one very small detail here is that since we have the expectation value on a different wire, we got slightly different results for this expectation value as in the previous notebook. But yes, we can just evaluate this quantum node. And at this point, we can turn to training the quantum circuit. So first off, what we would like to do is to set up some sort of a cost function. In our case, we will have a very simple cost function because we would just like to minimize the expectation, the value that we get from the quantum node. This will be minimizing the expectation value of the resulting quantum circuit. So what we would like to do here is to just get the expectation value, and this will give us the cost function value already. Once we have defined our cost function, we can simply just get one of the optimizers from Pennylane to optimize this cost function and get the ideal parameters that yield the minimum expectation value. To do that, I just use the gradient descent optimizer from Pennylane. And you can also just pass in the step size that you would like to use with this optimizer. Once you have the optimizer, we can start a for loop to step through the steps of the optimization method. And at this point, what we can do is to call on the, we can actually do 2 things, but in this case, we will call on the method step and cost, which will step the cost function and also get the value of the cost function. We pass in the cost function itself that we would like to get gradients for, and which we would like to step using the gradient descent formula. We pass in the trainable parameters, which were theta, phi, and omega. And as a result, what we will get is going to be 2 things. First, we get the updated trainable parameters, and we will also get some values for this cost function. So we are actually taking these 2 steps together, but once we have this, we can just execute it. And let me just, what I'll do I just copy the initial parameters here. I will print the Q node value before the optimization. And I will print the last value that we get. And what we could see is that we have started optimizing this cost function. Oh, okay. What I've done here was I've increased the number of steps just so that we start optimizing better. And at this point, we've actually started hitting the -1 minimal value. So I took 300 steps. It might be good to take 400 steps, but it seems like it's going to be converging to some -0.999 sort of value, but analytically it would be -1. So what we can actually do is the following. We can accumulate all the values that we have computed here. What I'll do, I'll just create a values list. I will append these values throughout the optimization into the values list. And here in this cell, I can just import matplotlib. And I can also just plot these values just to have a look at what happened. So what happened really was that we started off with some initial parameters that gave an expectation value of around 1. As we have gone through our training procedure, this expectation value started decreasing. And after around 250, 300 steps, we started converging towards the analytic value, the analytic minimal value, which is -1. So what happened here was that we've used the internal gradient computations of Pennylane. But when we have hardware devices, we cannot use simulators. If you recall, we used the default.qubit simulator previously. This is not something that you can do if you would like to compute your, if you would like to run your quantum circuits on a real hardware. So when we have a real hardware, what we would like to do is to get the parameter shift rule and to use the parameter shift rule to get the gradient. Here, what we can do is to compute the partial derivative of the quantum circuit with regards to one of the trainable parameters. In this case, that could be theta. And we can just shift this into the positive and negative directions and use some constant value to get the gradient. So there are a couple of values we can use here, which have been found in the literature. So since we have single qubit rotations in our quantum circuit, we can just use 1/√2 as a constant value here. And we will use a shift of pi/4 just to shift our quantum circuit evaluations. At this point, we will also just go back to the quantum circuit definition, which we had here. What I'll do is we could simply just get the quantum circuit, the evaluated quantum circuit results by using the circuit function. And we will be inputting theta, phi, and omega, but this time shifting theta into the positive direction, shifting theta into the negative direction. Once we have these two evaluations, we can recreate the gradient of the quantum circuit with regards to theta using the constant multiplier we've used, getting the difference between the two function outputs. In order to have this good enough value, I just copy the initial parameters here once again, so that we don't get the already optimized values here. But what we get is going to be this measure for the gradient of the quantum circuit with regards to theta. We could actually get the same quantity by using Pennylane only. So in this case, what we can do is we can use the QML.grad function to get the gradient function of our Q node. At this point, I might just redefine the Q node by getting the quantum circuit. So we get the quantum circuit. I define the Q node as Q node 2 equals QML.Q node circuit 2 dev for the device. And I'll also pass something that is something that we had a brief look at the beginning of the session, which is the diff method parameter. So I'll pass in the parameter shift diff method. I'll get the gradient function of this Q node. And what I'll also be doing is reinitializing the parameters once again, just for the sake of safety. And I'll pass in these parameters. So what we'll see is actually that we get 3 values. These 3 values will be the gradients of the quantum circuit with regards to each of the input parameters. So the first component is actually going to give us the gradient of the quantum circuit with regards to theta. And it matches the quantity that we have computed using the parameter shift rule just recently. So that should actually be it. If you would like to get the gradient with regards to other parameters, you can just reapply the parameter shift rule by not shifting theta, but for example, shifting phi once or shifting omega. Yes, so that's it for this notebook. As a quick recap, what we had a look at was how to define a cost function. We had a very simple cost function where the cost function really was just the expectation value received from the circuit itself. How to provide an optimizer from Pennylane. We used the gradient descent optimizer. We've used the step and cost function, which gives us the stepped parameters and the cost value as well. You could also use another variant that is only the stepped function. In that case, you will get the updated parameters and not the function, not the value of the cost function. But afterwards, we just had a look at what the values look like. And we could see that we have a nice converging monotonicity. We have a nice converging behavior here. We also got the gradient of the quantum circuit using the parameter shift rule. And yeah, as a final step, we got the same using purely Pennylane and by using the diff method attribute that you can pass to the Q node class. Okay, so that might be it for the second notebook. Do you have any questions? I see there were some things posted to the chat.
I don't see any questions on our chat, so I think we can go on.
Awesome, great. In that case, I'll just quickly stop sharing and I'll pull up the third notebook, which is going to be exciting if you are thinking about integrating Pennylane with a new framework. So in Pennylane, as we've mentioned, we have a couple of plugins, but the number of plugins we have is not extensive in the sense that there are always new frameworks you could integrate Pennylane with. So I just shared my notebook. This will be about creating a custom Pennylane device. And yeah, please just let me know if you start seeing my screen. Awesome, yeah.
See it.
Cool, that's amazing. Okay, so as mentioned, this will really just be a quick notebook about how to define your custom device in Pennylane. And a couple of goals. We will just have a look at how to support operations and observables using Pennylane and the quantum device. And we will also implement our own basic quantum-based device. This device will be a single qubit pure state simulator. It will be slightly more constrained, but it will give a good sense of how we can implement devices in Pennylane. So as a beginning, we actually get our imports already in the notebook. And there is also some sort of a textual description on one of the devices, this qubit-based class. So one of the things that is important from this text is that to create our own qubit-based device, what we will do is to inherit from this qubit device class. Once we inherit from the qubit device class, there will be many functionalities that we get for free. We will get computations of statistics for free, so we won't have to define how to get the expectation value of certain operators. Pennylane will take care of it under the hood when we are using the syntax of Pennylane. There are a couple of things which we do have to define, and the list of these things can be seen here. So we will just define the list of operations that the device supports. We will also define the list of observables that the device supports. These will actually be sets, Python sets. We also define the init and the reset method of the device. So these two methods will basically perform some sort of initialization and resetting of the device in case of devices that are stateful, so they have a state vector in the background. These will be setting this initial state. In most cases, this will be just a 0 state. Apart from these, there are two more things to define. One is going to be the apply method. This will simply just tell how the device applies certain quantum operations. In our case, this will be a simple version of getting the operations and evolving the state vector using those operations. And we will also just define the analytic probability method, which determines the analytic probability of getting computational basis states. This will really just be a simple way of providing what the outcomes of quantum computations using the device can be. Okay, so just as an intro to mostly defining these two methods, let's have a look at how we could evolve a very simple state, the 0 state, using the polyx operation, and how we could code this up in NumPy. So what we have here, once again, is just the 0 state. We have the polyx, and we would like to get the psi that is the evolved state vector. Sorry about that. So this will really just be the one state at the end. What we can do, since we have already imported NumPy, we could just create NumPy arrays. So these NumPy arrays can just coincide with the vectors and matrices that these state vectors and operators basically with which these state vectors and operators can be represented with. So you can represent the 0 vector with a 1, 0 NumPy array, and you can represent the polyx operator when it comes to its matrix representation with a 2x2 matrix, where you have 0, 1 in the first row and 1, 0 in the second row. If you have this matrix, then you can define how to get the 1 state using this matrix and the vector. And what we will do is we will just, let me just write it this way. We get the 0 state. We would like to evolve this state. So the way we evolve this is simply just by multiplying this vector with the matrix of the polyx operator. And once you have that, what we will effectively do is to flip this one single qubit into the one state. This is just a very small indication of how we can evolve state vectors using the matrix representation of quantum operations, and how we can do that on with a single qubit. The second step we would like to have a look at is how we can gather the probability of computational basis states. So these computational basis states can be the post-measurement states when we perform some sort of measurements of operators. This is something that we use under the hood in Pennylane, and that's why we would like to just provide a definition for the analytic probability method. So using the Born rule, what we can do is to provide the analytic formula for getting the outcomes of quantum circuit runs. So in this case, we are curious about computational basis states. These computational basis states are the 0 and the 1 states. So the probability that we measure the 0 eigenvalue can be determined by this formula here. So we basically multiply bra 0 with the ket psi. We get the absolute value, and then we square this quantity. This will then give us the probability of observing the 0 eigenvalue at the end of the quantum circuit run. When we have a look at the eigenvalue 1, the probability will be very similar. We just get the overlap of the 1 state and the psi state, and then we get the absolute value function and square this. This will just be a very good pointer to how we could get analytic probabilities later when we define our own device. Okay, with this small introduction, what we can do is to have a look at the device definition that we would like to use. So the implementation itself is in some form provided here, but there are things which are missing. So let's just have a look at the entire cell. We have some sort of a device class, which has class attributes here, and it has some instance methods as well defined here. These are the instance methods mostly that we already mentioned at the beginning of this notebook, but we will also have specific implementations for each of them. So going through this implementation, we have some imports. We have our class, which really inherits from this qubit device-based class that we have in Pennylane. And we have a couple of class-based attributes that are already pre-populated here. We just define a name for the device, so it will be a 1 qubit state vector device. We can provide a short name for the device. In this case, it's example.qubit. But if you would package your solution and put it into a Python package, installing it with Pennylane, alongside with Pennylane, using this short name, you could use the device itself. We have 2 attributes which are just for version control, and we also have an author attribute for this device. So once we have these attributes defined, we can just define the set of operations that we would like our device to support. So as the operations, as the common mentions, this will be a set, the supported operations. So we just create a set, and it will have to be a string, a set of strings for each of the operations that we define. So we just define poly x here, and we define the RY rotation here. These actually coincide also with the class names that we use in Pennylane. It will just be these names in a string representation. Okay, so once we have our operations defined, we will also just define our observables. In this case, we would like the polyz observable to be supported by the device. And that will be the only one for this small example. So just as a small recap, we have defined our operations and we have defined our observables that we would like this device to support. There are a couple of things we should fill in the initial method as well. So in the init method, we will define the number of wires that this device will be capable of supporting. In this case, what we do is that we hard code 1 in here just to allow a single qubit to be simulated by the device. But if you would like to, which is of course usually the general case, for this device to support multiple wires, you could just get this as the init methods argument. Get these numbers as an argument to the init method. Further to this, we will also define the number of shots this device has to support. If you have an integer value for the number of shots, so for example, is that we are running the quantum circuits multiple times and getting averaged outcomes, averaged statistics based on the outcomes that we have gotten. So in this case, what we would like to do is to get analytic computations. And for this reason, we will just set the shots to none. This is something that represents in Pennylane that our simulator is going to be analytic in nature, and every expectation value that we compute is going to be the analytic value. At this point, the last thing we have to define in this init method is going to be the internal state that we would like our device to be initialized at. This is going to be the 0 state. Once we have our 0 state defined for the init method, we can actually just copy it and put it into the reset method as well. What this reset method does is that it resets the device between quantum node evaluations. And this is also something that we can get many of the functionalities from the qubit device class. This was actually the same in the init method as well. So once we had defined the wires and the shots, we simply just called on the init method of the qubit device base class. And by calling this method, we are getting most of the device initializations from the base class itself. All right, so we use these two super methods from the qubit device class. We also provide a state property that really just returns the self.state attribute internally. And at this point, we would like to give the definition for the apply method. Looking at the signature of this apply method, we see that we will be operating on the instance of the device. We will get some sort of operations. And optionally, we could also get some rotations. In our example, these rotations are not going to be something interesting. But if you would like to create a more general device, these rotations are useful to rotate based on the eigenbasis of the operator you would like to get statistics for. So at this point, what we can do is to iterate through the operations. So this list of operations and evolve the underlying state that we have. We will do two things. To do this, we will get the matrix representation of each operation. So let me just iterate through the operations themselves. To get the matrix representation of each operation, we can just call on pop.matrix, which will return the matrix of the operation. And what we will do is to evolve our internal state vector using this matrix. As previously we've seen, we can just use matrix multiplication on a single qubit. So what we will just really write here is that we evolve the internal state vector using the matrix representation of this operation. And one other thing that's left is just to update the state vector by assigning the new evolved state to it. And this will really just be it. This will be how we apply operations using this very basic device. The last bit to define in the device is to define the analytic probability. So in this case, what we would like to do is to get the analytic probability of computational basis states. Well, when we get the overlap, which we had a look at previously, so when we consider this very specific formula, what we actually do is that we will get a distinct coordinate of this psi state vector. And when I say distinct coordinate, that's because getting the overlap of the 0 state with the psi state will effectively choose the first coordinate of the psi state vector. When we get the inner product of 1 with psi, we will basically choose the second coordinate of the psi state vector, which is where psi is a single qubit state vector. So what we can actually do using NumPy is to just compute all of these probabilities all together using broadcasting. So what we would then write is self.state. This will be the entire state vector. At this point, we can already just get the absolute value of the state vector. Once again, NumPy will broadcast this absolute value computation on each of the components of the state vector. And at the end, we can simply just, as in the formula, scrolling back up, we can just square these values to get the probability of measuring the eigenvalue of 0 or 1. So what we get here is going to be the vector of probabilities. So we can already just pass this as the analytic probabilities, and that's going to be something that we are looking for. So this is simply just going to be the definition for analytic probability. If we now just run this cell, we provide effectively a definition for the entire class. And at this point, we can start using the class itself. In the first example, we will just do some bit flips. We flip the same single qubit, first using polyx, then using it again. This will be actually an identity, and then flipping it again. And at the end, we get the expectation value of the poly-z operator, which will effectively be -1. We can also just fit this device into a more complicated training procedure. So if we have a quantum node that has a single Y rotation gate, which also gets an X parameter and gets the poly-z expectation value on the first qubit, we can just start an optimization using QML gradient descent optimizer once again, and step this optimization 30 times. If we do this, what we can have a look at is that first we got an expectation value nearing 1, and after the optimization, we get an expectation value that is near -1. So as a quick recap, we've used qubit device to inherit from one of the base classes of Pennylane. Lots of the functionality that we have used are built in. That's why we could use QML.xwell already with our device. And we just had to redefine a couple of methods in the device class itself. So that might be it for this notebook. Are there maybe any questions?
I cannot see there are any questions regarding this, like technical questions, but there is a question like, will we have this notebook for better understanding available somewhere?
So if it was true, I've actually shared these notebooks previously. Did you get them?
Yes, all the notebooks were shared. There is a link on the channel tutorial using Pennylane, and the link was also sent in the invitation email. So everyone who registered should have received it already.
Okay, that's perfect.
Awesome, great. That's perfect to hear. Okay, if there are no other questions, I might really jump into the last notebook. So will the slides be available after the conference? So likely not, but you could just have a look at the recording. If I'm not mistaken, the entire session is being recorded. So yes, you could just go back and have a look again. Okay, so at this point, I might just quickly jump into the fourth notebook so that we can also just have a look, at least to some extent, into that notebook. I'll just share my screen once again. And this is the last notebook we have for today. So bear with me. It is also one of the most exciting notebooks. So this is really just going to be a use case using Pennylane for quantum machine learning. So let me know if you can see my screen. Does it appear yet, or?
We can see.
Oh, okay, awesome, great. I will just jump right into it then. So we will be using Pennylane for a variational quantum classifier. So in this case, we will be embedding some classical data using Pennylane. We will also just create a model using templates from Pennylane, and we will solve a data classification problem in Pennylane. So having a look at the variational quantum classifier, we can just say that there are a couple of steps in this model. First, we have a quantum circuit that is initialized in the 0 states, and we would like to encode some sort of a data set, some features using this quantum circuit, and apply some sort of a unitary in the quantum circuit. At the end of the quantum circuit, we would like to conduct measurements so that we can label the features that we have encoded in this quantum using this quantum circuit output. So this is the main case. We have the features, we have some labels, we will also have some training data, and at the end of the classification, we would like to test that our trained model will actually perform well on test data as well. So there are a couple of questions that come up. First, how we can embed classical data into our quantum circuits. What type of architecture we should use in order to then train this structure. So basically, what could be this SX? What could be the U theta? And how we could get output measurements so that we determine labels in this circuit. First off, there's actually a data set that was provided to you, and this can be just loaded using this cell here, which should be already available in the notebook. Just to have a look, what we see is that we have some X-train data. These will be the features, and these features will be 3-dimensional. So each of the data points will have 3 different scalar values. We have a vector of such features, and we will have also corresponding labels. So if we get some elements from the Y train data structure, then what we will see is that these labels will range from -1 to 0 and 1. So there will be 3 distinct values, -1, 0, and 1. In order to have a better understanding of how these data points are related to each other in space, we can have a look at their first and second components. So what we see is that they are very well split in these 2 dimensions, and we can also compare the first and the third dimensions just to get another feeling. So they are very well split here as well. So there are a couple of decisions we can make based on the data that we see. We have 3-dimensional data, so we could use 3 qubits. We also just need a quantum circuit to input the data itself, and another quantum circuit, let's just say that a part of a quantum circuit should input the data, and another part of the quantum circuit should use the trainable parameters. When we compute the output of the quantum circuit, we will just need to create a meaningful cost. So here, we just use seeding. And what we will first do is, I might actually skip this one just for the matter of time. But what we could do is to rotate each of the qubit by some amount based on the data. And this is effectively what we will do with one of the templates that we have in Pennylane, which is the angle embedding template. So what we do here is that we will just define some sort of an embedding function. This will call on the angle embedding templates, and we will have 3 different qubits. So it will use wires 0, 1, 2. Once we have these templates, we will be able to, once we have this template set up, we will be able to use this in our structure for the quantum circuit. This is effectively just doing X or Y, just doing single qubit rotations under the hood on all of the wires using these features that we would like to encode. Then the next question is what type of variational architecture we could use. So this variational keyword really just refers to the fact that we will be varying the parameters while we are also training our network. So one of the basic architectures that we have already seen is to have single qubit rotations on each of the qubits and to have some sort of entangler, mostly a CNOT gates in a chain structure. As you see there, you can have multiple layers for this as well. So here we have stacked 2 layers side by side. But what we can do here is to get another function, layer function that gets some parameters. We will use one of the templates from Pennylane, and this template will be something that is called a basic entangler layers template, if I'm not mistaken. And we will just call this from QML templates. So at this moment, what we can do is really just get some initial parameters. So what we can do here is to get some random values for these parameters, and we can just simply get 3 times 3 initial parameters. Stacking these 2 parts together, so the feature vectors that we would like to input and the input parameters, we can just create our quantum function. So we will have our embedding here on X. We will have our layer passing the parameters. One thing I missed here was to specify the wires. So we will have 0 to 2 the wires. So we will have our wires for 3 qubits. And once we have this, we can just define the output that we would like to use. In this case, we will simply just use once again the expectation value of poly Z on the 0th wire. So let's have a look if we can actually just run these. So we got oh yes, we have some training data, and one thing I did forget at this point was to create a device and to create a Q node out of this circuit. So we have again default qubit device, 3 qubits, and we can just create a Q node, and we can just run the circuit itself with some initial parameters using 3 layers. So when we initialize the init parameters, we actually specify 3 layers here. So at this point, what we can do is we can run our circuit architecture, and we can also just have a look at how to how this looks. Yeah, it's slightly okay. Let's just decrease the number of layers. Okay. This is now better. So we see that we are embedding the features. We also have a single layer where we have X rotation gates and the CX operations in order to have the entire circuit structure. At this point, what we can do is label the outcomes. So what we know is that the expectation value of poly Z will be I see that there are a couple of questions. Maybe we could address them slightly later towards the end of the notebook, if that works.
Yes, that works, yeah. So please continue.
Yeah. Cool, okay. So at this point, what we can just gather is that we have an expectation value that ranges from -1 to 1. We have, however, 3 distinct labels. So what we could actually do is to define how we could get these 3 distinct values. So what we do here is that we will just create some sort of a label, and it will just get some Y prediction value. And what we can say is that if this Y prediction value is greater than 0.33, then we return 1, for example. If this Y prediction value is smaller than minus 33, then we can just return, for example, -1, and otherwise we will just return 0. So what this effectively does is that it will just label our outcomes based on the predictions that we do. So at this point, what we can further just do is to get some sort of a loss function. So if we have some Y prediction and we have some true Y values that we gather from the data set that we have defined, then what we can do is get some sort of a least squares cost here, and to define the least squares cost, what we can just say is we get the difference of the Y prediction and the Y true values, get the square of these, and then get the number of predicted values. So this will get us the loss function. To get the cost function, what we can really just do here is to get the parameters, the X and Y input parameters, where X is going to be the features, the parameters will be the trainable features, and what we can do is to create predictions based on the quantum circuit. So in this case, we will be passing some sort of X's and params into the quantum circuit. For the X that we pass into the cost function, we will get the predictions that we would like to see. And at this point, we can just return the loss of the predictions and the Y values that we have passed in. I'll just quickly run this through. But at this point, we can also create the accuracy of our predictions, such that we get some Y predictions, we get some Y true values, and once we have our predictions, getting from all these Y pred values, what we can do is to get the label for each of the predictions. And this will also just be useful to get the accuracy of the overall predictions that we have made. So at this case, we can just see what the true values were and average this with the predictions as well, predictions themselves. Okay, so once we have this defined, what we can do is really just to start training our model. So at this point, what we can just do is to create some layers, create some init parameters that we have done previously as well. So I'll just copy it from here, like as such. We can create a batch size so that we get the input features in batches. And at this point, we can just also get one of the optimizers, which will be, once again, the gradient descent optimizer. And we can just pass some step size here. All right. So at this point, we can start stepping our cost function. And what we will do is to get some sort of a batch index. This batch index will range from the size of the feature, of the size of the input features. So in this case, that will be X train. And we will get a batch size number of these integers. And we get a batch of the train features. we will get a batch of the y labels. And once we combine these two, we can simply just start stepping our function. Now, at this point, it's worth noting that when using the AutoCAD interface, which we will be doing by the opt.step function, we should create some sort of a new function such that we can pass in trainable parameters. So we had our cost function here. We will pass in v, and we will pass in the x batch and the y batch values. And we will also pass in these parameters. I will just call params. So here it's better to get maybe 2 layers. Let's see. Once we have this, what we can further just do is to compute the accuracy every 5 steps, for example. And what we can once again just do here is to get some predictions. So we will get these in X train. So we will get the X predictions with some parameters that we have already computed, get the accuracy of the Y predictions with the Y trainable, Y trained predictions, and print the accuracy. So I've actually created lots of code here. Let's see if there's going to be any problems, which there are. So we had cost function is missing one of the, yes, because that's not, this is going to be the circuit, my bad. But if we have actually set up things correctly, then we start increasing the accuracy by stepping further up and up. I see that we are slightly running out of time at this point. Oh, there are some. Well, the accuracy is going not too well at that point. So maybe I've set something up wrong here. It might also be that the step size is not too great. So I'll just, yeah. Let me just modify this one. And so I see that we are actually slightly running out of time already. So at this point, oh gosh, yeah. I might have really just set up something very wrong. So the idea really is just to get these accuracies from the predicted Y values. Maybe you could check it out in the solutions notebook as well, but I wouldn't want to take more of your time up, so I might just stop here. And I would just really advise you to get an idea from the solutions notebook. And on the Pennylane website, we also have a full-fledged example that goes through multiple data sets. And you can also have a look at how to use a variational classifier. Must be one extra parentheses. I might just stop sharing so that I wouldn't like you to stay too much further here either. But yeah, if there are any other questions.
Yeah, so I mean, if anybody have questions, and thank you for the amazing presentation and tutorial. It is very helpful. So if anybody has questions, please unmute yourself and ask, or just type. It would be nice. There are some of the questions like for loss function. Do you recommend using cross entropy function for classifiers involving discrete classes? Or do you recommend one-hot encoding beforehand?
So it's a good question. When it comes to choosing the loss functions, it really depends on the specific problem. So each of the problems might be, how to say, like, choosing a good loss function will very be dependent on the problem itself.
So the choice of the cost function depends upon the problem itself, right? Yes.
Yeah.
So there must be another question. Yeah.
Sorry, there was a question. Oh, yeah.
Okay, so sorry for the interruption. Can you explain in detail the embedding at the beginning?
Yeah, so that embedding was really just, we've actually drawn the circuit later. Maybe the question came before, but the embedding was really just X rotation gates on each of the qubits. But there are different embeddings as well coming with Pennylane. So really, you could just check out the templates page in Pennylane, and that will be helpful just to see what type of embeddings you can use. So we've used angle embedding, but you can, for example, use amplitude embedding as well, and we have further embeddings.
Okay, thanks. I think I missed one question. Like, it is a recent question. Can we use Optuna for hyperparameter training? Optuna, or, yeah.
Yeah. Frankly, I don't really have experience with Optuna, but perhaps yes. I'm not sure, honestly.
Yeah, Tomal says that I have used Optuna and it's good. So yeah. And there is a very large question written by Jismer. Would you like to unmute yourself and ask? Jismer? Because he says that seems like Grover's parameter can be optimized by directly calling the angle embedding plus basic entangled layers. Am I correct?
Yeah, I see the question.
Okay, yeah.
I must admit, I'm not sure. So likely you could use these two if you have. Frankly, I don't really see how we could use these to optimize Grover's parameters, but it might be that yes. Yeah, I wouldn't. At this point, I cannot say for sure.
Okay, so I think we had enough questions for now, and I think if you have any questions regarding this, then you can just put on the chat on the channel, and if you have time until then, you can just reply to them.
For sure, yes,
yeah.
And yeah, just sorry that we got slightly late with this session, but
no
yeah,
worries.
Thank you so much for everyone.
Okay. Great, fantastic. Thank you, Antal, very much for your presentation and tutorial. It was very nice, and the comments are also very positive. Yeah, so I think that Akash, Anshul, I think that we can wrap up. We can finish.
Yes, Paul. I think we can wrap up now.
Yes, that was the last session for today. The last session of the Quantum Machine Learning Conference. So we would like to thank everyone for attending, for participation. We hope that everyone enjoyed and your experience is positive. As we said, we'll try to upload the video recording on our YouTube channel and share the link with you. And what else? So we will try to organize similar events in the future. Most likely we'll also send you a Google Forms to ask you for your feedback, what was good, what we can do better in the future. So we already invite you to attend our future events. So not only organized by Q Poland or Q India or Christie University, but also QWORD in general. So I think that's all. At least that's all from my side. So I would also like to thank once again all the speakers, the participants, and also the co-organizers. So Akash, Anshul, it was a pleasure for me to collaborate with you. Very good job. And
same here.
Yes, I believe
the pleasure is all mine.
Yes, great, fantastic.
Akash has done a fantastic job moderating all the sessions.
Yeah.
Good luck, Akash. Yes.
Yeah, so I mean, I want to add something that not only we are organizing these events, but we also organizing events in the Q Cousins also, in Q Poland and Q India. So if you join these Q Cousins, then you will frequently get updates about this announcement and also these events. So it will be very much interactive for us to connect with you and share the quantum information.
Yeah, so as you can see, there are dedicated channels on our Discord, like Join Q India, QWORD, and also Quantum AI Foundation, QPoland. So I can see that already some people have joined. Yeah, I think that's all. There was just one private question sent to me in the direct message. It was shared any other notebook? No, Luis, that was, so the notebooks shared by Antal were the only notebooks here. So yeah, that's all. So I think if there are no more questions, then Anshul, I think we can stop recording now and just send me later the video or share later it with you, with me. And I think that's all. So we can officially close the conference. Thank you once again. Have a good day, evening, wherever you are. And
yeah, Paul, so I have one question, personal question. Like, this server is going to be there, or you're going to deactivate this server for this conference?
I will send the survey by email to all registered people.
Oh, okay, that's perfect.
I will try to prepare it probably now or later today. And also I will share it with you first before sending.
Okay, thanks.
Great. All right. So yeah, let's finish.
Thanks for joining and have a nice weekend.
Have a nice weekend. Bye-bye.
Bye.
Bye everyone. Thank you.